Hey everyone, I'm Morgan Willis, Senior Cloud Technologist at AWS, and I want to welcome you to this course. In this course, you will learn the key concepts behind cloud computing and explore AWS services using real-life examples, covering compute, networking, storage, databases, security, and more. This course is intended for people working in IT or IT-related fields, who have a general knowledge of IT topics, but have yet to learn much about the AWS Cloud. To kick off this course, we will cover the basics of what the cloud is, the benefits of the cloud, the AWS global infrastructure, and identity and access management. This will give you a solid foundation for learning the rest of the more technical topics contained in the course. Then we will focus on computing. And for this topic, we will dig into services like Amazon Elastic Compute Cloud, AWS container services like Amazon Elastic Container Service, and serverless compute options like AWS Lambda. Then we will discuss networking in AWS, using services like Amazon Virtual Private Cloud and other networking technologies used for creating, securing, and connecting to your own private network in AWS. For storage, we'll explore how and when to use Amazon S3, Amazon Elastic Block Store, and others. For databases, we will cover use cases around the many different database services AWS has to offer, but with a special focus on Amazon Relational Database Service and Amazon DynamoDB. Then finally, we will discuss monitoring and scaling your application. For that, we'll use Amazon CloudWatch and Amazon EC2 auto-scaling alongside Elastic Load Balancing. We aren't going to focus on theory alone in this course. Instead, we will use a hands-on example through a cloud-based application that will build over the duration of the course piece by piece. The app we will build is an employee directory application that stores images and information about fictional employees in a company. There is no coding requirement for this course. For all of the exercises, you'll use the AWS Management Console within your own AWS account. You will also have access to the source code if you do want to explore further. This course includes written segments we refer to as readings or notes to reinforce ideas, dive deeper into topics, as well as provide background information on concepts that we perhaps did not cover in the videos. Because of this, I highly suggest that you take the time to complete all of the readings to get the full benefit of the course. So again, welcome. And as we say at Amazon, work hard, have fun, and make history. Hey everyone, my name is Morgan Willis, and I'm a Senior Cloud Technologist with AWS. What that means is I essentially get to build things, learn AWS, learn about new and different technologies, and then I get to share my knowledge with you all. I had a career in software development before I started working in training and certification at AWS, and I also have a degree in computer science. I really love technology and have been in the field for about over 10 years at this point, in roles that range from technical support to database administration to web application development. And while it's true that I do love technology, I also have a regular life outside of work where I like to hike in the beautiful sun, rain, sleet, or snow, and I also like to ski. Pretty much any outdoor activity, all seasons of the year, I am here for it. And this here is Meowsy. He's my trusted sidekick. He spends time with me while I type away in my computer, and I think he's picked up a thing or two over the years. His knowledge of AWS at this point is pretty great for a cat, I must say. I think I can even hear him sneaking on my computer at night to build his solutions on AWS. I have a feeling that his knowledge will come in handy in this course. More on that later.
Hey y'all, I'm Alana Layton, and I'm also a cloud technologist here at AWS. I've been with AWS for a while now in a variety of different roles, but I love being an instructor in courses like this one. It's so much fun to bring this content to life and get everyone learning. In my spare time, I love being outside, hanging out with my family, which includes my 4-year-old wonder dog named Kiwi. Speaking of Kiwi, sometimes I think she knows more about AWS than she lets on. Every once in a while, I notice her drawing AWS architectures in a journal, and I wonder where she learned all of this. She can't bring me the ball back when we play fetch, but she always wags her tail when I mention cloud computing. I think these reactions will come up every once in a while, so stay tuned for some of her helpful tips and tricks.
Hey there. I hope you're excited to learn about cloud computing on AWS. I'm excited too, so let's go ahead and hop in. This week, we are going to cover some of the foundational concepts that you'll need to know about when working with AWS. Working with AWS is part theory, part technical knowledge, part vocabulary, and lots of practice and experimentation. This first week is going to help you establish a little bit from each of those categories. You will learn the theory behind cloud computing and the benefits of the cloud. This will help you make informed decisions about the cloud from a high level and give you some reasoning around why and when to use the cloud. Then we will dive into the AWS global infrastructure, covering both regions and availability zones, followed by lessons on how to interact with AWS resources. This portion of the week is going to give you the technical knowledge and vocabulary that you need to create and discuss AWS architectures and properly understand AWS documentation and examples. A lot of what AWS offers can relate back to concepts used on traditional on-premises computing. And getting started with AWS means comparing those concepts to AWS concepts. After that, we will begin to discuss security and identity and access management. This is important to understand when you're getting started because as soon as you create an AWS account, you'll have some actionable knowledge on how to secure that account right from the start. Starting off secure is a good place to be. Throughout all of the topics this week and over the duration of the entire course, we will be using a sample employee directory web application to demonstrate how AWS services are used, and we'll be using the same application to give you some hands-on experience through exercises done in your own AWS account. Let's go ahead and take a look at the employee directory application. You can see I am already in the browser and I have this employee directory application up and running. And what I want to do now is show you the functionality of this app. This is a basic CRUD app or a create, read, update, delete application. This app keeps track of employees working within a company. So the first thing I want to do here is create a new employee. So to do that, I'm going to go ahead and click add. And then I'm going to give the employee a name. I'm just going to add myself here. My location is USA. My title is Senior Cloud Technologist. And then you have the ability to add some badges to employees. So I'm going to go ahead and select Mac user, frequent flyer, and coffee snob for myself. So I'll go ahead and click save. And that you can see now we have the saved banner popped up and we're back on the home page. And I actually forgot to add a picture for myself. So I'm going to go ahead and click on the employee. And then I'm going to click the edit button. And now I'm going to select a file here, which is just a picture of me. And then I'll click save. And now we can see that this employee has a photo. One more thing that this app can do is we can delete employees. So I'll go ahead and do that. And now you can see we have an empty directory again. And then one final thing to know about is we have something called an info page. And this gives some information about where the app is hosted, and this will come in handy later on in the course. So those are the features of the app from a user's perspective. Time to review now how we will build this app using AWS services. This application will be built in a private network using Amazon Virtual Private Cloud or VPC. We will host the application's backend code on Amazon Elastic Compute Cloud or EC2, which is a service that essentially offers virtual machines on AWS. So let's go ahead and add those servers to our diagram as well. The employee data will be stored in a database, which will also live inside of this network. And this will be hosted using a service called Amazon Relational Database Service, or RDS, or we might be hosting it on Amazon DynamoDB. So we'll add both of these to our diagram. The images for the employees will be stored using the object storage service, Amazon Simple Storage Service, or what we call S3, which will allow the unlimited storage of any file type, like the images in this example. So these are the basic building blocks of our application, but we're not done yet. We are also going to use Amazon CloudWatch for monitoring this solution. And we want to ensure that our application is scalable and fault tolerant. So I'm also going to add an elastic load balancer here, which will distribute the traffic across the EC2 instances. And we will also add Amazon EC2 auto scaling to this diagram. So that way our solution can scale out with demand and scale in when demand decreases. For security and identity, we will be using Amazon Identity and Access Management, or IAM. So you can see that there are a lot of different pieces on this diagram, but don't worry. We're going to build this app step by step using the AWS Management Console. We will add to this diagram, reference it, and change it throughout the course to meet our needs, and we're going to let it evolve as new ideas and techniques enter our world. One more thing to note about this course before I let you go. If you hear this noise, it means that you are going to be seeing one of our informational pop-ups on the screen, which convey extra information like word definitions, AWS best practices, tips and tricks, or general commentary written for you by our lively furry sidekicks, Meowsy and Kiwi. They know all the tips and are very helpful little friends to have around during this course. So that's it for now. Have fun and make sure you complete both exercises for this week so that you can start working hands-on with AWS.
For our employee directory application, we'll be using photos of each of our employees. We have to store them somewhere safe. Currently, the only copy of these photos are saved on my laptop right now. But if my laptop breaks, then what happens? No more photos. I want to make sure this doesn't happen, so I'm going to upload the photos to AWS to ensure that the copies exist even if my laptop is destroyed. This also allows me to access my photos from anywhere. My home, my phone, a plane, on a train, everywhere. When I store these photos in an AWS service, unbeknownst to me, I'm storing it in a data center somewhere, and servers inside that data center. But if a natural disaster happens, or a fire, or let's say a giant lizard comes out of nowhere, stomps on the data center, then what do we do? Luckily, AWS has planned for this event and many others, including natural disasters and other unavoidable accidents. The way they plan for it is through redundancy. AWS clusters data centers together around the world. So here, AWS might have a second data center connected to the first data center through redundant high-speed and low-latency links. That way, if the first data center goes down, the second data center is still up and running. This cluster of data centers is called an availability zone, or AZ. An AZ consists of one or more data centers with redundant power, networking, and connectivity. Unfortunately, sometimes natural disasters like hurricanes or giant lizards might also extend to impacting an entire AZ. But AWS has planned for that too, with redundancy. Like data centers, AWS also clusters AZs together and also connects them with redundant high-speed and low-latency links. A cluster of AZs is simply called a region. In AWS, you get to choose the location of your resources by picking a region. Regions are generally named by location, so you can easily tell where they are. For example, I could put our employee photos in a region in Northern Virginia called the Northern Virginia region. And remember, AWS is not going to name a region in Germany after Northern Virginia. As a basic rule, there are 4 aspects you need to consider when deciding which AWS region to use: compliance, latency, price, and service availability. Let's start with compliance. Before any other factors, you must first look at your compliance requirements. You might find that your application, company, or country that you live in requires you to handle your data and IT resources in a certain way. Do you have a requirement that your data must live in the UK boundaries? Then you should choose the London region, full stop. None of the rest of the factors even matter. Or if you operate in Canada, then you may be required to run inside the Canada Central Region. But if you don't have a compliance or regulatory control dictating your region, then you can look at the other factors. For example, our employee photos are not restricted by regulations, so I can continue looking at the next factor, which is latency. Latency is all about how close your IT resources are to your user base. If I want every employee around the world to be able to view the employee photos quickly, then I should place the infrastructure that hosts those photos close to my employees. We are all bound by the speed of light. Applied to your business, that means if all your users live in Oregon, then it makes sense to run your application in the Oregon region. You could run it in the Brazil region, but the latency from Oregon to Brazil might impact your users and create slower load times. But maybe I really want to run my application or store my employee photos in Brazil. One problem I might run into is the pricing, which is the next factor we'll talk about. The pricing can vary from region to region, so it may be that some regions, like the Sao Paulo region, are more expensive than others due to different tax structures. So even if I wanted to store my employee photos in Brazil, it might not make sense from the latency perspective or the pricing perspective. And then finally, the fourth factor you'll want to consider is the services you want to use. Often, when we create new services or new features in AWS, we don't roll out those services to every region we have right away. Meaning, if you want to begin using a new service on day one after it launches, then you'll want to make sure it operates in the region that you're looking at running your infrastructure in. To recap, regions, availability zones, and data centers exist in a redundant, nested sort of way. There are data centers inside availability zones and availability zones inside regions. And how do you choose a region? By looking at compliance, latency, pricing, and service availability. When you own the infrastructure, it's easy to understand how you interact with it, because you can see it, touch it, and work with it on every level. If I have a server that I've stood up in my closet, interacting with that server is easy because it's mine. I can touch it. When I remove the ability for me to touch and see something, when the infrastructure becomes virtual, the way that I work with that infrastructure has to change a bit. Instead of physically managing my infrastructure, I now logically manage it through the AWS Application Programming Interface, or API. So now when I create, delete, or change any AWS resource, whether it's a virtual server or a storage system for employee photos, I use API calls to AWS to do that. You can make these API calls in several ways, but the three main ways we're going to talk about are the AWS Management Console, the AWS Command Line Interface, and the AWS Software Development Kits, or SDKs. When people are first getting started with AWS, they'll typically use the AWS Management Console. This is a web-based console that you log into from your browser. The great thing about the console is that you can point and click. By simply clicking and following prompts, you can get started with some of the services without knowing anything about the service. With the console, there's no need to worry about scripting or finding the proper syntax. When you log into the console, the landing page will show you all of the possible services that you can work with, organizing them into relevant categories such as compute, databases, storage, and more. On the upper right-hand corner is where you select the region you want to work in. Changing the region directs the browser to make requests to that region, represented by a different URL. If I change the region to Paris, you're making requests to eu-west-3.console.aws.amazon.com, or the Paris region's web console. After you work with the console for a while, you may want to move away from the manual creation of resources. For example, in the console, you have to go through multiple screens to set configurations to create a virtual machine. And if I wanted to create a second virtual machine, I would need to go through that process all over again. While this is helpful, it also leaves room for human error. I might miss a checkbox or misspell something or even skip important settings by accident. So when you get more familiar with AWS, or if you're working in a production environment that requires a degree of risk management, you should move to a tool that enables you to script or program these API calls. One of these tools is called the AWS Command Line Interface, or CLI. You can download this tool and then use the terminal on your machine to create and configure AWS services. Instead of having a GUI to interact with like the console, you instead create commands using a defined AWS syntax. For example, if I wanted to launch a virtual machine, I first type in AWS, which is how we know we interact with the API. Then type in the service, in this case, which is EC2, the service that allows us to create and manage virtual machines, which we'll learn about later, and then the command that we want to perform in that service, and then any other configurations we want to set. One command versus multiple screens you have to click through in the console can help reduce accidental human errors. But that also means you have to work with defined syntax and get that syntax correct in order for your command to run successfully. So there is some upfront cost in just understanding how to form commands. But after a while, you can begin to script these commands out, making them repeatable, which will save you time in the long run. The other tool that allows you to interact with the AWS API programmatically is the AWS Software Development Kits, or SDKs. SDKs are created and maintained by AWS for the most popular programming languages, such as Python, Java, Node.js, .NET, Ruby, and more. This comes in handy when you want to integrate your application source code with AWS services. For example, our employee directory application runs using Python and Flask. If I wanted to store all the employee photos in an AWS storage service, I could use the Python SDK to write code to interact with the AWS storage service. The ability of managing AWS services from a place where you can run source code with conditions, loops, arrays, lists, and other programming elements provides a lot of power and creativity. All right, that wraps up this video. To recap, you have three main options to connect with AWS: the console, the CLI, and the SDKs. And this course will mainly be using the console to interact with the services. But feel free to challenge yourself by using the CLI if you're a bit more advanced.
It's time for your first hands-on exercise with AWS. Before you can begin building an AWS, you'll have to have an AWS account. So, for your first exercise, we ask that you create an account with AWS, verify the account, and then you'll set up some billing alerts. When you create an AWS account, you can then begin using the services. And a lot of different AWS services offer a free tier. The free tier varies from service to service, and all of the services that we chose for this course do have a free tier where you can use the resources for free with a limited capacity for a limited amount of time. If you have an existing AWS account that you are trying to use, there's a chance that you won't qualify for the free tier and would incur costs for the exercises that you complete in this course. So, for this first exercise, it's going to be pretty straightforward, and we are building up to the more complex tasks involved with hosting our employee directory application. You'll create and confirm your new AWS account, log into that account, and then you'll explore how to do some basic management tasks like where to find your account information, how to change regions using the management console, and setting up those billing alerts. You will set up a billing alert just in case you create a resource and then you forget to turn it off or delete it. You'll at least be notified when you've hit a certain threshold in the account for cost. So that's it for now. And make sure you utilize the discussion forums to ask questions if you get stuck or want more information on a specific topic. In order to begin using AWS effectively, it's important to understand how security works in the cloud. You already know that by using AWS, you won't be managing every single aspect of hosting your solutions. You'll rely on AWS to manage portions of your workload for you, taking care of that undifferentiated heavy lifting, like running the day-to-day of the operations of the data center and managing the various virtualization techniques employed to keep your AWS account isolated from, say, my AWS account. So the question is, who is ultimately responsible for security in AWS? Is it A, you, the customer, or B, AWS? The answer? Well, the correct answer is yes. Both you and AWS are responsible for securing your AWS environment. Let's explore this concept a little bit more. AWS follows something called the shared responsibility model. We don't view solutions built on AWS as one singular thing to be secured. We see it as a collection of parts that build on each other. AWS is responsible for the security of some aspects, and the others, you are responsible for their security. Together with both you and AWS following best practices, you have an environment that you can trust. Let's take a look at the shared responsibility model diagram. You can see we have the responsibility of security broken into two groupings, you and AWS each being responsible for different components. We describe AWS as being responsible for security of the cloud. For example, one piece of the puzzle AWS is responsible for is the AWS global infrastructure. And when I say global infrastructure, I mean the physical infrastructure that the cloud is running on. This is iron and concrete, buildings with fences protected by security guards, and various other security measures. It also includes the AWS global backbone, or the private fiber cables that connect each AWS region to each other. Managing the security of these pieces is all on AWS. You don't need to worry about that as far as security goes. Then there is the infrastructure and various software components that run AWS services. This includes compute, databases, storage, and networking. AWS is responsible for securing these services from the host operating system up through the virtualization layer. For example, let's say you want to host some virtual machines or VMs on the cloud. We primarily use the service Amazon EC2 for this use case. When you create a VM using EC2, AWS manages the physical host that the VM is placed on, as well as everything up through the hypervisor level. If the host operating system or the hypervisor needed to be patched or updated, that is the responsibility of AWS. This is good news for you as the customer, as it greatly reduces the operational overhead in running a scalable and elastic solution leveraging virtualization. We will talk more about EC2 and elastic solutions in upcoming lessons. For now, let's get back to the security aspect. So, if AWS manages the underlying hardware up through the virtualization layer, what are you responsible for? Well, you are responsible for security in the cloud. Similar to how a construction company builds a building, and it's on them to make sure that the building itself is stable and secure. Then you can rent an apartment in that building. It's up to you to lock the door to your apartment. Security of the building and security in the building are two different elements. For security in the cloud, the base layer is secured by AWS. It's up to you to lock the door. So for our EC2 example, you are responsible for tasks like patching the operating systems of your VMs, encrypting the data in transit and at rest, configuring firewalls, and controlling who has access to these resources, as well as controlling how much access they have. The main thing to understand is that you own your data in AWS. You are ultimately responsible for ensuring that your data is encrypted, secure, and has proper access controls in place. In many cases, AWS services offer native features that you can enable to achieve a secure solution. It's up to you to actually use them. In other cases, you may devise your own solutions to meet compliance and security standards for your own specific industry or use case. So that's the shared responsibility model at a high level. I do want you to keep something in mind though. There is some amount of nuance that you should understand as we move through this course regarding the shared responsibility model. Each AWS service is different and serves a different purpose. and a different use case. Therefore, the shared responsibility model can vary from service to service as well. This is a good thing, as you get to decide how to build your solutions on AWS. When you create an AWS account, you sign up with an email address and you create a password. The email address you sign up with becomes the root user of the AWS account. This root user has unrestricted access to everything in your account. We will discuss in a later lesson what types of users can be restricted and how to do that. But for now, I want you to understand that when you log into your AWS account using an email address and password, it means that you are logging in as the root user. This root user can do whatever they want in the account. It has all of the powers that can be had. And with great power comes great responsibility, or something like that. So, knowing that the root user is all-powerful, you should do everything you can to make sure that no one can gain access to this root user. Let's say there's a nefarious actor of sorts, and they have an evil plan to log into your AWS account with your root user, gaining access to all of the powers and permissions that can be had, and they go and delete all of your valuable data and AWS resources. And in its place, they spin up a lovely and expensive cryptocurrency mining operation, leaving you with the bill and none of your data as they walk away with a full crypto wallet. Sounds less than ideal. Well, how can you prevent that from happening? You could, of course, create a hard-to-crack password, and that will give you some level of security. This, however, is an example of single-factor authentication, where all someone needs to do is match the password with the email address and they're in. We recommend as a best practice that right after you create your AWS account, you enable multi-factor authentication, or MFA, for the root user. MFA introduces an additional unique piece of information that you need in order to gain access to the account. There are a variety of devices, virtual or physical, that generate one-time passwords that can be integrated with your AWS account for MFA. For example, I personally use a virtual MFA device that's an app on my phone. This app produces a string of numbers for one-time use that I type into the console after I log in using my email address and password. Even if someone had guessed my password, they cannot gain access to the account without the numbers generated by the virtual MFA device. No matter what type of MFA device you choose to use, and I will include a link in the notes for supported devices, the most important thing is that you are using MFA at least on the root user. That way, even if someone, the nefarious actor, cracks your password, they still cannot gain access to your account, and all thanks to MFA. On top of enabling MFA for the root user, we strongly recommend that you do not use the root user for your everyday tasks, even the administrative ones. There are really only a few actions that require root user access. Coming up, you'll learn how to create an IAM user and then use that to log in to your AWS account instead of using the root user. Let's take a look at the application we are going to be building throughout this course. We've already gone over the design of this application, and what I want to do is focus now on the access control. There are multiple places on this diagram where we can identify the need for access control and credential management. The first being that we need to manage how users log in and use the employee directory application. We could require that people have a valid credential, like a username and password to log into the app. That is access management on the application level. Then there's the fact that we know the code running the employee directory application is running on a virtual machine being hosted by the service Amazon EC2. That code will need to make API calls to the object storage service Amazon S3 in order to read and write data like the images for the employees. Well, here's the thing. Just because both Amazon EC2 and Amazon S3 have existing resources in an account, it doesn't mean that the API calls made from the code running on the EC2 instance to S3 are going to be automatically allowed to be made. In fact, All API calls in AWS must be both signed and authenticated in order to be allowed, no matter if the resources live in the same account or not. The application code running on Amazon EC2 needs access to credentials to make the signed API call to Amazon S3. So that's another place with a need for credential and access management. Now, let's take this a step further. How are you going to build out this architecture? Well, you'll need access to an AWS account through the use of a login. Your identity within this AWS account will need permissions to be able to do things like create this network, launch EC2 instances, and create the resources that host and run this solution in AWS. Yet another place you need credentials. The root user, which you have already learned about in a previous lesson, has these permissions. But you don't want to be using the root user to administer your AWS resources. And also, let's assume that you won't be the only one working on building out this application. It's more likely that within one AWS account, there will be many people who need access to build and support your solutions. You'll have different groups of people responsible for different parts of the architecture. The people who would write and deploy the code might be software developers, whereas the people who would be responsible for making changes to, say, the network would be a totally different group of people. You wouldn't and shouldn't give everyone who needs access to the AWS account the root user credentials to log in. You instead would have unique credentials for each person logging in. This is where the service AWS Identity and Access Management comes in. We identified 3 places that we will need access and credential management for this solution. AWS Identity and Access Management, or what we call IAM, can help take care of these 2 spots on the diagram. AWS IAM manages the login credentials and permissions to the AWS account itself. And it also can manage credentials used to sign API calls made to AWS services. IAM would not, however, be responsible for the application-level access management. The code running on this instance would use separate appropriate mechanisms for authenticating users into the application itself, not IAM. All right, so let's start with the AWS account level. IAM allows you to create users, and each individual person who needs access to your AWS account would have their own unique IAM user. Creating users for everyone who needs access to the account takes care of the authentication piece. Authentication being verifying if someone is who they say they are because they logged in with the proper credentials. Now it's time to introduce authorization. Authorization is this. Let's say you've logged in and you are who you say you are. You've been authenticated. Now, you want to create and manage AWS resources, like create an Amazon EC2 instance, for example. So sure, you've logged in, but do you have the correct permissions to be able to complete that action? The idea that your permissions control what you can or cannot do is authorization. Are you authorized to launch an EC2 instance? IAM users take care of the authentication. And to take care of authorization, you can attach an IAM policy to a user in order to grant or deny permissions to take specific actions within an AWS account. And keep in mind, when I say action here, I'm referring to an AWS API call. Everything in AWS is an API call. IAM policies are JSON-based documents. Let's take a look at an example. This IAM policy document contains permissions that allow the identity to which it's attached to perform any EC2-related action. The structure of an IAM policy has an effect, which is either allow or deny. An action, which is the AWS API call. In this case, we have EC2:*, which that would include all of the EC2-related actions. You can restrict this to be specific API calls. For example, I can restrict this action to be just run instances. And then any user with this policy attached would be able to run EC2 instances, but perform no other EC2 related tasks. IAM lets you get very granular with your permissions in that way. We see the resource, which allows you to restrict which AWS resources the actions are allowed to be performed against. You can also include conditions in your policies that can further restrict actions. IAM policies can also be attached to groups. IAM groups are very simply just groupings of IAM users. You can attach a policy to a specific user or to a group. When you attach a policy to a group, any users that are a part of that group would inherit the permissions. We recommend that as a best practice, you organize users into groups and assign permissions to groups instead of individual users where possible. This makes it easier to manage when people change job roles or maybe multiple users need permissions to be applied or revoked. Another best practice to follow is that we recommend when you create your AWS account, you first set up MFA for the root user. Then create an IAM user with administrator permissions. Log out of the root user and then log in with the new IAM user that you just created. From there, you can use this user to create the IAM groups, users, and policies for the rest of the people using this AWS account. The reason we suggest that you do this is because you cannot apply a policy to the root user, but you can to an IAM user. Now, I've told you about IAM users, groups, and policies. So we addressed this part of access management that we needed for our application. But what about this part? The EC2 instance needs credentials to be able to make the signed API call to S3 for reading and writing employee images. Am I suggesting that you make an IAM user with a username and password for the application running on EC2 to use? No, I am not. This is where role-based access comes into picture. Coming up next, we will learn about the temporary access that IAM roles provide and how it can be applied in this use case. Stay tuned. In a previous lesson, you learned about IAM users, groups, and policies. Policies can be applied to AWS identities, like users and groups, to assign permissions. They also, however, can be applied to another AWS identity, IAM roles. An IAM role is an identity that can be assumed by someone or something who needs temporary access to AWS credentials. Let's dive into what exactly I mean when I say AWS credentials. Most AWS API calls that are made must be signed and authenticated. But how does that process work? Well, from a high level, when you send an HTTP request to AWS, you must sign the request. This signing process allows AWS to verify your identity when a request is made, and it's run through various security processes to ensure that a request is legit. IAM users have associated credentials like an access key ID and secret access key that are used to sign requests. However, with regards to our architecture, the code running on the EC2 instance needs to sign the request sent to S3 for the employee photos. I already told you that I do not intend for you to create an IAM user with credentials to be used by this app. I also do not intend for you to hard code credentials into this app at any point in time. So, how will the application gain access to the needed AWS Access Key ID and AWS Secret Access Key to sign the API calls? The answer? IAM roles. IAM roles are identities in AWS that, like an IAM user, also have associated AWS credentials used to sign requests. However, IAM users have usernames and passwords as well as static credentials like the access key and secret access key. Whereas IAM roles do not have any login credentials like a username and password, and the credentials used to sign requests are programmatically acquired, temporary in nature, and they are automatically rotated. In our example, the EC2 instance will be assigned an IAM role whenever you launch it. This role can then be assumed by the application running on the virtual machine to gain access to the temporary credentials needed to sign the AWS API calls being made. A role can be assumed by many different identities, and they have many use cases. The important thing to know about roles is that the credentials that they provide expire, and roles are assumed programmatically. To get an idea of this, let's go ahead and create a role using the AWS Management Console. I'm already logged into my AWS account, and now what I'm going to do is navigate to the IAM service by just typing IAM in the toolbar here and selecting this. And now what I want to do is create the role that our AWS EC2 instance is going to use for the employee directory application. So to do that, I'm going to click on roles over here in the left-hand side, and then I'm going to click create role. From here, you have to select what trusted entity is allowed to assume the role, because again, remember, these roles are being assumed programmatically. So we are going to go ahead and select EC2 as the trusted entity to assume this role, and then we will click next. And now we can attach permissions to this role. On this screen, you can look through the AWS managed policies, which are policies that are created and maintained by AWS, or you can create your own policy where you can get really specific and granular with the types of permissions that you want to give to this role. For this specific example, I need this application to be able to read and write to Amazon S3, and we're also going to need to give this application access to Amazon DynamoDB, which is a database. So what I'm going to do is I'm going to use the AWS managed policies here. So I'm going to type in S3, and then I'm going to select the Amazon S3 full access role. And if we open this up, you can see what the policy looks like. This policy here has one statement where we are allowing the action of S3:*, so that is all S3 actions, against all S3 resources. So this is a very broadly scoped permission. For our simple proof of concept, we're going to use this. In real life, you probably want to create custom policies that really narrow down the scope of those permissions. But I'm going to go ahead and select S3 full access. And then I'm also going to look up DynamoDB, and we will select Amazon DynamoDB full access. Next, we will click tags. And from here, we can add tags. Tags are just user-defined key value pairs that are associated with a resource. These can come in handy for billing and resource management and all sorts of things. So we are going to go ahead and give this a name, and this will just be employee directory app. That's the value of our tag. Next, we will click review, and now we will give this role a name, the name being EC2 S3 DynamoDB full access. And now we can click create role, and we can see that that role has now been created. The role that we just created is going to be used in future lessons and demos when we build out our employee directory application. It's very common for roles to be used for access between different AWS services. Just because two resources exist in the same AWS account, it doesn't mean that they can send API calls to each other. If one AWS service needs to send an API call to another AWS service, it will most likely use role-based access, where the AWS service assumes a role, gains access to the temporary credentials, and then sends the API call to the other AWS service, who then verifies the request. Another identity that can assume an IAM role to gain access to AWS is external identity providers. For example, let's say you have a business that employs 5,000 technical employees, and they all need access to an AWS account. You already have an identity provider in place that allows these employees to log into their laptops and access various corporate resources. Should you also now go create 5,000 IAM users for these employees to access AWS? Well, you can, but that doesn't sound very efficient. You can leverage IAM roles to grant access to existing identities from your enterprise user directory. These are known as federated users. AWS assigns a role to a federated user when access is requested through an identity provider. We also have AWS services that can make this process a little bit easier, such as AWS Single Sign-On. These are a couple of examples of role-based access in AWS. And this is just the introduction. Check out the class readings for more information, and don't worry if you don't quite grasp this concept yet, as we will use roles in our demos throughout this entire course, and you will also gain experience using IAM roles in your own account through our hands-on exercises. Let's keep the momentum going, shall we? Time for another hands-on exercise. This time, since you have already created your AWS account and you've learned about some of the best practices for securing AWS accounts, let's put those best practices into practice. First, you'll log into your AWS account with the root user and you'll enable multi-factor authentication. Next, you'll find the root access keys, which provide unlimited access to your AWS resources. And as stated in a previous lesson, it's not recommended to use these unrestricted keys in normal situations. So you're going to go ahead and delete yours from the account. Then, once that is taken care of, you'll create an IAM user with administrator privileges. Then you'll log out of the root user and log in with the new IAM user. This user will be used to manage your AWS account from this point forward, unless the root user is specifically needed, which again will not be very often. The first task you'll complete with this new IAM user is you'll create an IAM role with more limited privileges that will come in handy in future exercises. Have fun. All right, you've learned some AWS vocabulary, some of the concepts behind cloud computing, as well as some specifics around cloud identity and access management. As a refresher, let's take a look at the architecture diagram we'll be building out. You can see here it's fairly complicated at a glance. There are many different services working together to host this solution, and to get this entire thing built out will take some time and understanding. You'll get the opportunity to build out each individual piece in your own account. What I want to do now is show you how we are going to host our employee directory application using a service called Amazon EC2, which I have mentioned briefly in previous videos. I find that the best way for me to explain to you how these services work is just to show you how they work. So what we are going to do is we are going to call Alana in to launch an Amazon EC2 instance and host the employee directory application using the defaults provided by AWS. AWS provides you with something called the default VPC, which is a private network for your AWS resources. Every EC2 instance you launch using AWS must live inside of a network. So, in order to complete this demo with the limited information that we've shown you about AWS services, we will be using the default network provided by AWS, and we will accept most of the default values for launching an EC2 instance. Let's call in Alana to help us out. Hey Alana, where you at?
Oh, hey Morgan. Is it time to launch our first EC2 instance?
It is. We will be using the default VPC to launch this first instance, and we will configure the bare minimum to get our application up and running. Sound good?
Yep, I got it. Let's get started. I'm already in the AWS Management Console, and I will go ahead and navigate to the service Amazon EC2. As Morgan already mentioned, Amazon EC2 is a compute service that allows you to host virtual machines. You'll learn a lot about this topic coming up soon, but for now, we are going to simply create an EC2 instance to try to help you wrap your mind around using AWS services on demand. From here, we will go ahead and launch a new EC2 instance, and an instance is just what we call one single virtual machine. Now we have to select the configurations for this EC2 instance. You will go over these configurations in detail later. But for now, we will select the free tier eligible options using a Linux AMI, and then also a T2 micro instance type, and then click Next. Then we will select the network we want the instance to be launched into, and as we discussed earlier, we'll be using the default VPC. The default VPC has configurations in place that make this experimentation process a lot easier when you're first getting started with AWS. If we scroll down, we will also select the role that will be used by the application. though this won't come into play until later when we have our S3 bucket created. Then we are going to accept the defaults and scroll down some more. In this box here, we're going to paste in a script. This script is going to run when the instance boots up. The script will download the source code to the app, start the web server, and kick off the application code so it's ready to start handling requests. While you could have launched the instance, then connected to it via SSH, configured and started your application manually, we have decided to use a script to automate this process on launch. This is called user data for future reference. Then we will click Next. Through the defaults for storage, click Next again. And then here we're going to go ahead and give our instance a name. So I'm going to click Add Tag, put name for the key, and then the value will be employee-web app, and then click Next. Then we will create a new security group, which is an instance level firewall that will allow HTTP and HTTPS traffic to reach the instance. We will cover this in detail in future lessons. Then we will go ahead and click Review and Launch. Click Launch again, acknowledge the key pair, and click Launch. Now, it can take a few minutes for the instance to boot up, so let's go ahead and wait for that. And now it's up and running. To access the instance, I first select it, then I'll bring up this tab here, and then I'll go ahead and copy the public IP address. All right, now we can paste it into a new tab. And there you go, it's up. Morgan, what do you think?
That looks good. It's exactly what I would expect at this point. Because there is no data being served from a database, I expect to just see the home page with no info. So that's great. Thank you, Elena, for walking us through that. Coming up next week, we will discuss the specifics of not only EC2, but also networking on AWS, and you'll understand how everything we just kind of glossed over actually works. You'll also have a chance to build it out yourself in your own account, so stay tuned.
Hey everyone, and welcome to week 2. Last week was all about the setup, making sure you understand AWS, the global infrastructure, as well as setting up an account and providing yourself the right level of permissions. But you may also remember that we ended last week by launching an EC2 instance to host our application. An EC2 instance is simply just a form of compute, meaning it gives our application power in the form of CPU, memory, and networking capacity so that we can process our users' requests. This concept of compute leads us into this week, where we discuss your compute options on AWS. Of course, you've already seen one of those options, EC2, but we'll also discuss other common solutions, such as container services, like Amazon Elastic Container Service, or ECS, and Amazon Elastic Kubernetes Service, or EKS, as well as serverless options like AWS Lambda. By the end of the week, you'll not only understand each of these services, but you'll also be able to compare them to one another. That way, you'll know when and how to apply each service to different use cases. You'll also get an opportunity to be hands-on with Amazon EC2. In the middle of the week, you'll complete an exercise to launch an EC2 instance to host the employee directory application. But as you imagine, we can't just launch the EC2 instance into space. We have to put it somewhere. And where do we put it? In a network that we'll need to customize for our application. Every EC2 instance needs to exist inside of a network, and on AWS, these networks are called VPCs. At the end of this week, you'll be testing your knowledge on networks in a hands-on exercise where you build a VPC. You'll then launch another EC2 instance in the VPC to host your application. But rest assured, this won't be too hard. You'll have everything you need to complete this. Remember that if you get stuck at any point, you can always ask questions in the class discussion forums. Our team will be monitoring those and getting you answers shortly. Also, make sure you're checking out the readings that follow the videos. There's additional information in those readings that you won't see in the videos, like use cases, features we didn't have time to cover, and more. All right, I think it's time for us to get started. Enjoy the week, and I will see you soon.
Let's talk about compute. Every business needs raw compute capacity to run applications. These applications could be web servers, batch jobs, databases, HR software, machine learning, or just about whatever you can think of. The time, money, and effort it takes to get up and running with on-premises computing resources is fairly high. When you own your own fleet of physical servers, you first have to do a bunch of research to see what types of servers you want to buy and how many you need to buy. Then you purchase that hardware upfront. You'll wait multiple weeks or months for the servers to be delivered. Then you take them to a data center space that you either rent or own, and you install them, rack them and stack them, and wire them all up. Then you make sure that the servers are secured, powered up, and ready to be used. Only then can you begin to host your applications on top of those servers. And the worst part is, once you buy these servers, you are stuck with them, whether you use them or not. It's not easy to just suddenly provision more physical compute capacity when you need it. And it's even harder to get your money back on servers that you no longer need. Impossible to get the time back. Following a compute as a service model is much easier to get started and easier to support operations over time. AWS took care of the hard part for you already as far as getting started goes. AWS already built and secured the data centers. AWS has already bought the servers, racked them and stacked them, and they are already online, ready to be used. In a previous lesson, we showed you how to launch the employee directory application with Amazon EC2. We didn't really talk about the details, how EC2 works, what configurations exist for it, and we definitely didn't discuss any other compute options that exist on AWS. AWS has different services for different use cases. And Amazon EC2 is one of the AWS services that is important to understand. We will be spending most of our time in these upcoming lessons exploring EC2. That being said, though virtual machines like EC2 are great, there are other compute services out there too, like container services and serverless compute. You'll learn about these other compute options and their use cases. Don't always assume that VMs are the default and correct answer. Sometimes it makes sense to architect applications for serverless compute or containers from the start, depending on what you are building for and what you are optimizing for. EC2 instances give you a lot of flexibility and control in the cloud, and you can configure them to meet your needs. You can provision one or many EC2 instances easily, and at the end of the billing cycle, you only pay for what you use, either per second or per hour, depending on the type of instance. When you no longer need an instance, you can terminate or stop the instance and you will stop incurring charges. Not all servers are the same, and you are probably looking to run a specific type of operating system on your EC2 instance. AWS supports a range of operating systems, including Linux, macOS, Ubuntu, Windows, and more. To select the operating system for your server, you must choose an Amazon machine image or an AMI. The AMI contains information about how you want your instance to be configured, including the operating system, possible applications to be pre-installed on that instance upon launch, and other configurations. You can launch one or many instances from a single AMI, which would create multiple instances that all have the same configurations. Some AMIs are provided by AWS, whereas others are provided by the community and can be found using the AWS Marketplace. For example, Amazon Linux 2 is the AMI we selected when we launched our employee directory application. This AMI is provided by AWS, and it is essentially a pre-built EC2 optimized Linux image that has long-term support provided by AWS. Beyond the properties determined by the AMI, you can also configure the instance type and size, which correspond to the amount of compute, memory, and network capabilities available per instance. Different applications have different hardware requirements, and choosing the instance type for your application gives you the ability to pick the hardware that it runs on. It's also really nice that you have a wide variety of choices for instance type, as it's hard to achieve the same level of variety with on-premises resources. The instance type you choose are grouped for use cases like compute optimized, memory optimized, storage optimized, and more. There is a list of instance types that you can find in AWS documentation, and you can expect that this page will be updated regularly as new instance types are released. For example, the G instance family are optimized for graphics-intensive applications, which would work best for use cases like 3D visualizations or video encoding. Whereas the M5 general purpose EC2 instance family provides a balance of resources and are great for applications that use these resources in equal proportions, like web servers, our employee directory application, for example, or things like code repositories. When you are launching an EC2 instance, you will see something like this when selecting an instance type and size. The T3 or A1 is the instance family that determines the blend of the hardware capabilities. Then there's the dot. Then there's the size, like small, medium, large. It goes down to nano and up to many, many extra large sizes, depending on the instance type. The great thing about this type of selection existing right at your fingertips is that you are no longer locked into hardware decisions up front. You can choose an initial EC2 instance type, evaluate its performance for your specific use case, and then later you can change to a different type that is better suited for your application. EC2 is also resizable with a few clicks in the console or can be done programmatically through an API call. All of these configurations being available to you via API enables you to embrace change over time easily as your workloads mature and change. So, all right, virtual machines are cool and totally not new. So how does this impact your business? The important thing is this: the flexible and low-cost nature of EC2 instances, as well as the ease of provisioning servers, allows for programmers and businesses to innovate more quickly by spinning up servers for a short amount of time to run experiments and find optimal configurations for your applications. EC2 offers a wide variety of hardware options to choose from, so you can optimize for your solutions by selecting the right EC2 instance type for your application, and then you can optimize even further by right-sizing the resource, or selecting an instance size that is appropriate for your application and not over-provisioning like is often done on premises. This type of optimization is hard to achieve on your own because with traditional on-premises deployments, you are working with hardware constraints that simply don't exist in the same way in the cloud. The ability to adapt changes and choose really specific configurations for your virtual machines all through a couple of API calls is very powerful. And really, EC2 is just the beginning of the story. One of the main reasons why EC2 provides so much value is the fact that you can provision new EC2 instances on demand, and just as easily, you can get rid of instances that you no longer need. In most cases, you only get charged for instances that are currently running. EC2 allows you to stop and start instances at will, which enables you to treat your fleet of EC2 instances as elastic, scaling them in or out. Then, at the end of the billing cycle, you only pay for what you use. We are building up to the idea of scaling your fleet of EC2 instances in and out to serve demand. But before we get there, it's important to understand some of the basics of EC2. Let's talk about the EC2 lifecycle. An Amazon EC2 instance transitions through different states from the moment you launch it through to its termination. You launch an EC2 instance from an AMI, as you learned in a previous lesson. And once the EC2 instance is launched, it enters a pending state. This state is essentially your VM booting up. Once the instance is ready for use, it enters the running state. In the running state, you will be charged for the EC2 instance. From running, you have a couple of different options. You can reboot the instance, which is similar to rebooting, say, your laptop. It turns off and then it turns back on. Pretty straightforward. You also can choose to stop your instance. it will enter a stopping phase, and then it will enter the stopped phase. Stopping an instance is like powering down your laptop. You can always turn it back on, and it will go through the usual boot sequence, moving through the pending state and then back to the running state. Another option, which is similar to stop, is stop hibernate. This also enters the stopping phase and then the stopped phase. You can compare this to how you lock your laptop and just shut the lid, but when you open it back up, everything is still in place exactly where you left it. There's no boot sequence required. You are back up and running after a couple of seconds of the computer waking up. Since the state of the machine was written to memory when you stopped it, the state of the machine can be drawn from memory and put back into place. Then you're back up and running. Now, the last option depicted here is the terminate option. When you terminate an instance, it enters the shutting down phase and then the terminated phase. Terminating an EC2 instance is like taking your laptop out for a long boat ride on the coast and then throwing it in the ocean, getting rid of it forever. It's now lost to the great blue sea. There is no hope in finding your laptop on a shipwrecked island one day, having been saved after spelling SOS in the sand. Anyways, I hope any data that you had stored on an EC2 instance that you did terminate, you had backed up somewhere, because whenever you do terminate an instance, anything on that instance goes with it. That being said, there is a feature called termination protection that you can enable if you're worried about instances being terminated accidentally. You also will learn about persistent storage in EC2 in future lessons. So don't fret. We will show you ways where you can make sure that any data that you have sticks around, even if the EC2 instance doesn't. So that is the EC2 instance lifecycle. It's definitely a good idea to remember how all of this works if you plan on using EC2 to host your applications. And don't think of terminating instances as a bad thing. If your EC2 instance is having technical trouble for one reason or another, or maybe it needs an update or a patch, instead of logging into the instance to fix it or install software, you can launch a new one with the new changes in place, and then you could terminate the old instance, having the new one take its place. You, of course, can do in-place updates as well, but just know that you have the option to decide how to handle these sorts of tasks. You can also launch or terminate EC2 instances to meet demand. So as demand for your application increases, you can launch more instances, and then as it decreases, you can terminate instances. This keeps your EC2 instance fleet in line with demand. So again, terminating an instance isn't a bad thing, and it should not be feared. Now, let's discuss the cost aspect of this. You only get charged for an EC2 instance if you are in the running state or if you are in the stopping state preparing to hibernate. This means that you can stop instances when they aren't in use. Say, if you have applications that are only really used during the work week, run them when your employees are clocked in, and then stop them when they aren't. Remember, you can always start from a stopped state, allowing them to resume working when necessary. In this next exercise, you are going to put all that new EC2 knowledge to good use. You're going to launch a new Amazon EC2 instance into your default VPC, just as we did for our demo in a previous lesson. You'll select an AMI, an instance type and size, configure the instance, and then you'll launch it. Part of the configuration will be to paste a user data script into the advanced configurations. This user data script is a script that runs when an EC2 instance is booted up for the first time. This is most commonly used to download and configure any software packages or dependencies that are needed to run the application on the instance. It's good for you to pay close attention to these sorts of details as you move through the exercise, especially if you plan on using EC2 outside of a classroom environment. Once your EC2 instance is booted up, you'll be able to send a request to the employee directory application and view its response in the browser. This EC2 instance will not yet be connected to any backend database to store employee information. So the expected result for this is simply to load the home page with no data displayed. If you are having trouble, please write your questions in the discussion forums. I also encourage you to help others troubleshoot their technical issues in the discussion forums if you were successful yourself. Once you are done verifying your EC2 instance is up and running and configured correctly, you will then stop the instance so that you can view the state change. Then finally, you'll terminate the instance as some cleanup. In a future exercise, you will relaunch this application, but using your own private network or VPC. The default network settings we are using for this lab are not secure, and I do not recommend that you continue to use these settings outside of this course. It is simply a proof of concept so that you can have experience going into the next lesson, making it all a little bit easier to wrap your mind around. EC2 is great for all sorts of different use cases, from running basic web servers to running high-performance computing clusters. That being said, though EC2 is incredibly flexible, reliable, and scalable, depending on your use case, you might be looking at alternatives for your compute capacity. For example, let's say you are looking for a way to run containers at scale on AWS. Containers provide you with efficiency and portability. And in this context, I'm specifically referring to containers like Docker containers. If you aren't sure what containers are, please review the readings on containers. AWS offers container services like Amazon Elastic Container Service, otherwise known as ECS, or Amazon Elastic Kubernetes Service, otherwise known as EKS. Both of these services are container orchestration tools. When you use containers on AWS, you need processes to start, stop, restart, and monitor containers running across not just one EC2 instance, but a number of them together that we call a cluster of EC2 instances. The process of doing these tasks is called container orchestration, and it turns out it's pretty hard to do it on your own. If you have a few containers, it's not so bad. But once you get to hundreds or thousands of containers that you are managing, it can be quite complex. Orchestration tools were created to help you run and manage containers. ECS is designed to help you run your containerized applications at scale without the hassle of managing your own container orchestration software. EKS does a similar thing but uses different tooling and has different features. We aren't going to go too much into this now. However, I did include a link to more learning resources around containerized applications on AWS in the readings following this video. The way you interact with these container services is you manage the containers running on a cluster through the orchestration tool's API. And then the orchestration tool carries out the management tasks. You can automate scaling of your cluster hosting your containers, as well as automate the scaling of the containers themselves. Containers have a shorter boot up time when compared to virtual machines. So if you need super fast response to increasing demand, then containers might be the service for you. So you can choose to host containers on top of clusters of EC2 instances as your hosting options for either ECS or EKS. However, what if you were looking for an alternative to hosting your containers? Because you either don't need access to the underlying operating system of EC2, or you don't want to manage that cluster of EC2 instances. Well, you can use a compute platform called AWS Fargate, which handles most of the underlying details for you. Fargate is a serverless compute platform for ECS or EKS, and we'll talk more about what serverless is coming up next. When using Amazon EC2 or container services running on top of EC2 as a compute platform, you are required to set up and manage your fleet of instances. This means that you are responsible for patching your instances when new software packages come out or when new security updates come out. You're responsible for setting up the scaling of those instances, as well as ensuring that you've architected your solutions to be hosted in a highly available manner, which means deploying instances across at least 2 availability zones. This is less management and less operational overhead than you would have if you hosted the same solutions on premises. But management processes will still need to be in place, and it's your responsibility to create those processes to fit your specific use case. This is actually really great, and in many cases, exactly what you want because it gives you a great deal of control over your solutions. Whatever happens on your instances and with your instances is in your hands. You can create simple or complicated setups that run and scale on AWS exactly to your specification. That being said, not every single solution requires this level of control over the environment. Oftentimes, you might be looking to focus on your own business solutions and let somebody else take care of the undifferentiated heavy lifting for you. Or perhaps you just simply don't want to fiddle around with scaling controls and fault-tolerant designs, but you still want all the benefits of doing so. This is where the term serverless comes in. A lot of AWS services are serverless in nature. Serverless means that you cannot see or access the underlying infrastructure or instances that are hosting your solution. Instead, the management of the underlying environment from a provisioning, scaling, fault tolerance, and maintenance perspective is taken care of for you. All you need to do is focus on your application. The rest is taken care of, or more accurately, the rest is abstracted from you. This means that serverless offerings are very convenient to use. You get to focus on the value of the service and what that service delivers, and not the underlying implementation details, thus reducing the number of operational support processes that you need to have in place. Remember the shared responsibility model that we had covered in an earlier lesson? This idea of serverless impacts that as well. So, for example, with Amazon EC2 instances, you are required to patch the operating system and security updates as they are released. With serverless offerings, the line between what you are responsible for versus what AWS is responsible for moves up. You do not have access to the underlying operating system that is running the service. Therefore, you are not responsible for carrying out tasks like patching. You are, however, still responsible for things like data encryption and access management. One example of serverless compute is AWS Fargate. AWS Fargate, which we mentioned briefly earlier, is a serverless compute platform that you can run either ECS or EKS on top of. Previously, you learned that ECS and EKS run on clusters of EC2 instances. And in that case, you are using EC2 as the compute platform for your containers. And you also have tight control over those instances. With AWS Fargate as the compute platform, you run your containers on a managed serverless compute platform. The scaling and fault tolerance is built in, and you don't need to worry about the underlying operating system or the environment. Instead, you just define your container, how you want your container to be run, and then it scales on demand. All right, let's wrap this up. I like to think of AWS services as existing on a spectrum. On one side of the spectrum, you have convenience, and on the other, you have control. Many services exist to give you control, like Amazon EC2, whereas other services exist to give you convenience, like the container hosting platform Fargate and the serverless compute AWS Lambda. We'll dive deeper into AWS Lambda coming up. AWS Lambda is one of the serverless compute options you have available to you on AWS. Lambda allows you to package and upload your code to the Lambda service, creating what's called a Lambda function. Once you create a Lambda function, it isn't always running all of the time. Instead, Lambda functions run in response to triggers. You configure a trigger for when you want your function to run, and from there, the Lambda service waits for the trigger. There's a long list of available triggers for AWS Lambda, and new ones are being supported frequently, so I won't run through them all now. However, a couple of common examples of triggers for Lambda functions are an HTTP request, an upload of a file to the storage service Amazon S3, events originating from other AWS services, or even in-app activity from mobile devices. When the trigger is detected, the code is automatically run in a managed environment, an environment you do not need to worry too much about because it is automatically scalable, highly available, and all of the maintenance of the environment itself is done by AWS. You do, however, get to choose the language your Lambda function is coded in, the amount of memory and CPU your function is allocated in the environment, its permissions, dependencies, and many other aspects of how the function runs. If you have 1 or 1,000 incoming triggers, AWS Lambda will scale your function to meet demand, each in its own isolated environment. Lambda is currently designed to run code that has a runtime of under 15 minutes. So this isn't for long-running processes like deep learning or batch jobs. You wouldn't host something like a WordPress site on AWS Lambda. It's more suited for quick processing like a web backend for handling requests or a backend report processing service. One of the best things about Lambda is that you aren't billed for code that isn't running. You only get billed for the resources that you use down to 100 millisecond intervals. To understand Lambda more, let's run through a quick demo. In this demo, I will create a Lambda function that resizes images uploaded into the employee directory application to be a uniform thumbnail size. It makes sense to create this sort of logic with the Lambda function. You don't need an application to be running 24/7 on EC2 to resize photos uploaded to the application. You really only need the resize logic to run when a new photo is uploaded. So here's our diagram for the app. What I want to do is add this. When a new photo is uploaded to Amazon S3, it triggers a Lambda function that resizes the image and uploads it to the same S3 bucket, but to a different location than where the original image is stored. Okay, let's go ahead and build this out. You can see that I'm already in the AWS Management Console, and I'm going to go ahead and click Create Function. From here, you have a couple of choices of how you want to create this function. We are going to author this one from scratch, and I already have the code written and downloaded to my local machine. So we're going to author from scratch. We'll name this resize photo, and then we get to select the runtime, and that's basically the language that you've coded your function to be. So for us, we coded this in Python, so I'm going to select the Python runtime. And then I'm also going to expand this permissions section here, and I'm going to use an existing IAM role for this code. The Python code that we wrote is using the AWS SDK to make API calls to S3. Therefore, those API calls must be signed and authenticated as we discussed in earlier lessons. So, in order for this code to gain access to the temporary credentials needed to sign the request, we are going to associate an IAM role with the appropriate S3 permissions to this Lambda function. So I'm going to go ahead and select the existing role, which is called AWS Lambda S3 Access, and then I'll click Create Function. At this point, we are now seeing the designer view, and I'm going to add a trigger for this Lambda function. I will select a trigger, and you can see here as I scroll down all of the different triggers that are available for Lambda. There are quite a bit, and there are also partner event sources powered by a service called Amazon Event Bridge, but I'm going to go ahead and select S3. Then I will select the employee photos bucket, which is the bucket that our app is using, and then I will use the prefix employee pick, because I know that that is the prefix where the function is uploading the images. And then I will scroll down, and I'm going to acknowledge this recursive invocation piece here. And this is essentially just letting us know that if I were to have this Lambda function read from the employee pick prefix, which is what triggered the event, and then process the image and upload it to the same spot, it would trigger another Lambda function run, and that would kind of just go on forever. So you want to make sure that you are using a different place for the output than you are for the input. So I'm going to go ahead and click Add. And now I will scroll down, and we are going to add the source code. So if you have source code with no dependencies, you can just type it right in here, which is really nice for experimentation. But for us, we're using some outside dependencies for resizing the image in Python. So I'm going to upload a zip file from my local machine. Then I'm going to click Save. Then I'm going to scroll down and change this Lambda handler. Go ahead and check out the class notes if you want to learn more about Lambda handlers and how this works. I'm just changing this so that it's referring to my actual file, and then I'll click Save. And now what I want to do is test this through the employee directory application. So I'm going to add a new employee. We'll name this Alana, locations USA, role is cloud technologist. She is a Mac user. And then we will upload her photo and click Save. So now it's been saved. I want to then test to see if this worked. So I'm going to click Monitoring here. And then I want to view the logs in CloudWatch logs. So CloudWatch logs is where the output goes from your Lambda function. I'm going to scroll down and click on the latest log stream, which is just the latest collection of log files from the Lambda function. And we can see that we did get the image resized output here, so I know that this code ran in response to the incoming event from S3. And that's it. That's how you create an AWS Lambda function at a high level. You could host the entire employee directory application's backend on Lambda with some refactoring, but I think I'm going to save that for a later conversation. If you're interested in the code that we used and more information about how Lambda works and handlers and how you write code for Lambda, I'll go ahead and include some resources for you in the reading section following this video. At this point, you've covered a few different AWS Compute services. The services covered so far can handle a wide variety of use cases. So, how do you know when to use each one? To figure that out, I think it's time to play a game. Welcome to the Which AWS Compute Service Should I Choose for My Use Case game show. We're your hosts, and you are the contestant.
We will present 3 different use cases that require compute on AWS, and it's up to you to choose the right service for the use case. You'll have 5 seconds to answer each question. Ready?
I'm ready, and I hope you are too. So let's do it. First question is up. Consider a scenario where you are a developer who is tasked with creating a new feature for a web application being hosted on EC2. The web application is an online store, and right now, all of the items being sold in the store are loaded into a database manually behind the scenes. By manually, I mean there is a person who adds each row into a database for each new item to be sold in the store. This process takes a long time and isn't very scalable, and on top of that, it's also prone to error. You are tasked with automating this process of getting new item information loaded into the inventory database. The goal is to have a person upload an inventory spreadsheet into Amazon S3, the object storage service, then have a process automatically load the data into the inventory database. What compute service would you use to host the processing logic to load the items from the file into the database? You have 5 seconds on the clock.
All right, let's discuss how you could have answered this question. You could have decided to use Amazon EC2 here. You could spin up a new instance specifically for this process and write some code that pulls the location of the spreadsheet for a new upload every so often, updating the database when it finds a new file. That would work. But before I make my answer final here, I have a question. How often does new inventory get added to the database?
New inventory gets updated 1 time per quarter.
Good to know. So it's not very often, which means this process would only run once a quarter. And that does change my answer. Here's why. Amazon EC2 charges per second or per hour. So if I have an instance running all the time to serve a request that happens once per quarter, that seems like a lost opportunity to optimize for cost. I would be spending money on a resource I rarely use. It certainly would work, but maybe not the best fit for this use case. I could automate the process of starting and stopping the instance when needed, but instead, what about using AWS Lambda?
Bingo. AWS Lambda is the correct answer for this one. There are a few reasons. First of all, to address your concern on cost, AWS Lambda only charges you for the compute you consume when the code is actually running. And the code is run in response to triggers or a direct invocation. So here's my suggestion. You know that the goal is to have someone upload an inventory document to S3, which should kick off the process of updating the database. You also learned that AWS Lambda has triggers that run your Lambda functions code. AWS Lambda integrates with many AWS services to act as triggers, and Amazon S3 is one of them. So my suggestion would be to create an AWS Lambda function, configure a put event as the trigger from Amazon S3. Then, when the inventory is uploaded to Amazon S3, it will trigger the Lambda function to run, and the code in the function will parse the inventory document and add each item into the database.
Time for the next question. Let's say you have an application currently hosted in your on-premises data center, which needs to be migrated to AWS. It's currently running on Linux servers in the data center, and you want to minimize the amount of refactoring needed to migrate to AWS. It's important that this workload is elastic and can support varying demand. What compute option would you choose? 5 seconds on the clock.
Time's up. Now, I'll go over the answer. Considering the fact that minimizing refactoring is an important aspect of this workload, I would architect a solution using Amazon EC2 as the compute service. EC2 instances can be launched from Linux-based AMIs, and the application could be hosted on the EC2 instance the same way it would be hosted on a Linux server on premises. Amazon EC2 also has the ability to scale in or out based on demand. So I think EC2 is the best service for this one.
That is correct. So if you answered EC2 at home, good work. Before we move on to the final question, let's dive into this answer a little more. Morgan, can you explain the thought process behind eliminating the other compute services we covered as answers to this question?
Sure thing. So, AWS Lambda could work, but you can't just upload the same code you would run on an Amazon EC2 instance into a Lambda function. There would be a decent amount of refactoring in order to take advantage of that service. Same idea with any of the AWS container services like ECS or EKS. Again, you'd have some amount of rework required to migrate to using containers. Therefore, Amazon EC2 is the best option for this migration. Now, time for one final use case. And this one is for all the marbles. Imagine a scenario where you are planning to write a brand new application using microservices or a service-oriented design. And you want to architect the application where it can scale up or down quickly, and you want to lower the risk of deploying new changes to production. Which AWS Compute service would you use? 5 seconds.
Okay, time's up. The answer for this use case is AWS container services like Amazon ECS or Amazon EKS.
Correct. The answer is either ECS or EKS for this one, because using containers makes it easier to support microservices or service-oriented designs. Containers boot up quickly, so scaling is quicker than with EC2 instances, and the use of containers helps with code portability. Meaning, if I write the code on my laptop and I run it in a container, then I test it in QA in a container, I can then expect that the same container would behave the same way once deployed to production, thus reducing the risk of any issues that might occur because of environmental issues.
All right, there you have it. out different use cases for a few of the AWS Compute services. Make sure you read up on AWS's other compute offerings and make informed decisions when architecting your solutions. You'll find there are a lot of options.
Remembering that these services exist to best suit different use cases helps. Don't try to use the same compute service for all of your use cases. Instead, pick the right one for the job and consider reevaluating choices for existing workloads as AWS continues to release new services and improve offerings.
If we look back at the architecture diagram for our application, the part that we want to focus on for this section of the course is this part, the network, or VPC, and its many components. But before we dive into networking on AWS, let's first put this into context. In the exercise you completed earlier, you launched an instance and connected to that instance over the internet. But to launch this instance, you needed to select a network. How you configure this network, or VPC, is actually what helps enable internet traffic to flow into your application. You might be asking, Alana, how did we select a VPC when we haven't even built a VPC yet? You're right, we haven't built a VPC, but fortunately, AWS creates VPCs for us in every region by default. When we launched our EC2 instance earlier in the course, we simply chose the default VPC. These default VPCs are meant to provide an easy way for you to get started with EC2 instances quickly and view your applications over the internet. However, you have to be careful what you put inside these default VPCs, as these resources will be subject to, well, the internet. And with internet access comes potential dangers. If we didn't select this default VPC, we would have needed to select a VPC that we custom built. In this section of the course, we'll focus on doing just that, building a custom VPC for our application that is more secure and provides more granular access to the internet than the default option we originally chose. While viewing this section, keep in mind that this information is geared towards EC2 related services. If you're using a different kind of compute, such as a Lambda function, you might not need a network at all. However, that doesn't mean that this isn't important. Networking on AWS is the basis of most architectures, so consider this information highly valuable. Coming up, we'll dive into some key VPC concepts. But for now, take some time to review the upcoming notes, which will cover some important networking basics that you should know before jumping into networking on AWS. In this video, you'll be learning how to create a VPC. With Morgan's help, we'll be both conceptualizing and building a VPC throughout the next few videos. The idea of a VPC is similar to how you think of walls around a data center. In a data center, walls act as the boundary between the outside world and all of your infrastructure. A VPC in AWS acts the same way. It creates a boundary where your applications and resources are isolated from any outside movement. So nothing comes into the VPC, nothing comes out of the VPC without your explicit permission. When you create a VPC, you have to declare two specific settings: the region you're selecting and the IP range for the VPC in the form of CIDR notation. For our VPC, we'll be locating it in the region where the rest of our infrastructure will be, the Oregon region. And our IP range we'll say is 10.1.0.0/16. All right, so currently our VPC just looks like a box. But with Morgan's help, we're going to build this out. All right, let's call Morgan. Hey Morgan, are you there?
Yep, I'm here. What do we need?
I was hoping you could build us a VPC that matches this diagram.
Sure, let's do it. If you're looking at the console, you'll first check to make sure that you're in the correct region by clicking in the upper right-hand corner. Alana mentioned that we're going to run out of the Oregon region, so we'll go ahead and make sure that this says Oregon. Once we choose the right region, we can now build our network. You'll type VPC in the service search bar, and that will bring up your VPC dashboard for this region. From there, you'll click on your VPCs and then Create VPC. Now we have a few settings to configure. We'll put in the IP range, which is 10.1.0.0/16, and the VPC name, which we'll say is app VPC. We'll leave the rest as default and then click Create VPC. Easy as that. Okay, Alana, what's next?
Nice, that was fast. After you create your VPC, you then divide the space inside the VPC into smaller segments called subnets. You put your resources, such as your EC2 instances, inside of these subnets. The goal of these subnets is to provide more granular controls over access to your resources. So if I have public resources, like our employee directory app, that we want to be accessed over the internet, I could put those resources inside a subnet with internet connectivity. If I have more private resources, like a database, I could create another subnet and have different controls to keep those resources private. To create a subnet, you need three main things. The VPC you want your subnet to live in, which is this one. The AZ you want your subnet to live in this case we'll choose AZA, or in other words, US West 2A, and then the IP range for your subnet, which must be a subset of the VPC IP range. For this, we'll choose the IP range 10.1.1.0/24. We'll call this our public subnet for public-facing resources. Then we'll create another subnet for our private resources. We'll place it in the same AZ, specify a different non-overlapping IP range, say 10.1.3.0/24, and then name it our private subnet. All right, now that we've got two subnets added to our VPC, it's time to put Morgan to the test again and have her build these out. And this time, I'm timing her.
Okay, we're on a time limit here, so let's create these subnets. Let's go ahead and start creating the public subnet. Back in the console, we'll click on Subnets in the side panel and then select Create Subnet. Then we'll select the VPC we're working with. In this case, it's the app VPC that we just created. Once you do that, you'll be prompted to provide a name. We'll call this Public Subnet 1. Then we choose the AZ, which Alana mentioned was US West 2A. And then the IP range of this subnet will be 10.1.1.0/24. We'll leave the rest as the defaults, scroll down to the bottom, and click Add New Subnet. Now we're going to repeat the same steps for our private subnet. Give it a name, such as Private Subnet 1, put it in the same availability zone, US West 2A, and then type in the IP range 10.1.3.0/24. Now we can click Create Subnet, and both subnets will be created. All right, Alana, what was my time?
Well, that was so fast that my watch didn't even register it. Wow. Okay, moving on. As we mentioned earlier, when you create a new VPC, all the resources you put in it are isolated and only have access to other resources in that VPC by default. For websites like our employee directory application, we want users to access our site over the internet. To enable internet connectivity, we need a component called an internet gateway. Think of this gateway as similar to a modem. Just as a modem connects your computer to the internet gateway connects your VPC to the internet. When you create an internet gateway, you then need to attach it to your VPC. If you create an internet gateway and don't attach it, it won't do anything except sit there. Okay, Morgan, show us how it's done. Create an internet gateway and attach it to our VPC.
All right, so let's hop back in. Back in the VPC dashboard, you'll click on Internet Gateways in the side panel. Then create Internet Gateway. You'll give the Internet Gateway a name and then click Create. On the Details page, you'll then select the Actions drop-down box and select Attach to VPC, choosing the app-VPC we've been working with, and then you'll click Attach. Back to you, Alana.
Sorry. I thought I'd have a bit more time to drink my tea. Right, okay. What's next? So we have an internet gateway that we can use to allow access from the internet. but what if we had a VPC with all internal private resources that we want to reach only from our on-premises data center? If we only want traffic to flow between AWS and our data center, and we don't want to allow direct access from the internet, what do? Luckily, there's another gateway designed for this very purpose, called a Virtual Private Gateway, or VGW. It allows you to create a VPN connection between a private network, like an on-premises data center or internal corporate network, to your VPC. With the help of a VGW, you can establish an encrypted VPN connection to your private internal AWS resources. We won't be using a VGW for our application, but it's good to know anyway. All right, so we have one VPC, 2 subnets, and an internet gateway attached to the VPC. Now, every time you look at an architecture, you should begin to think, how do I make this better? You're not going to have all the answers right away, but I do want you to take 10 seconds and think about some solutions. Okay, well, one option to make this better is the idea of having high availability. What that means is if this AZ goes down for whatever reason, what happens to our resources in that AZ? They go down too. So ideally, we would have resources in another AZ to take on the traffic coming to our application. To do this, we'd need to duplicate the resources in this AZ into the second AZ. So that means we need to create 2 additional subnets, each within another AZ, say AZ-B. All right, you get the point. You'll be able to create these additional subnets yourself later on in the exercise. But in the meantime, Morgan is going to build these out in the background for the rest of our demos. She's also going to launch an EC2 instance, hosting our application, and one of the public subnets. Sound good, Morgan?
Sounds good. I'll get right on that.
Okay. We'll see you next time. Let's take a look at our current VPC state. In the last video, we left off with a VPC with an internet gateway attached to it and 2 subnets, one public, one private, and one availability zone. However, Morgan was kind enough to build additional resources in the background to make sure our application was highly available. So now we have 2 additional subnets, one public, one private, and a different AZ, for a total of 4 subnets. She also created an EC2 instance hosting our employee directory inside of the public subnet in AZA. But we're missing one large component here. Say we have a user, and that user wants to access our employee directory. Eventually, that internet traffic would flow through the internet gateway, but then where would it go? Just because the traffic entered through the door of the VPC, it doesn't mean it ever made it to the right room. What we need to do is provide a path for the internet traffic to not only enter the door, but also make sure the traffic reaches the right room. Or, in other words, enter the internet gateway and find the right subnet. The way that we provide that path is through route tables. A route table contains a set of rules, called routes, that are used to determine where network traffic is directed. These route tables can be applied at either the subnet level or at the VPC level. When you create a brand new VPC, AWS creates a route table called the main route table and applies it to the entire VPC. AWS assumes that when you create a new VPC with subnets, you want traffic to flow between those subnets. In the last video, when we talked about VPCs being isolated, this is what we meant. The default configuration of the main route table is to allow traffic between all subnets local to the VPC. Let's get a quick look at the main route table of the VPC we just built out in the last video. Hey Morgan, do you mind showing us a quick example of the main route table?
Sure thing, Alana. Let's hop into the console. Here in the VPC console, we'll click on Route Tables on the side panel that will bring up all of the route tables that exist in this region. If we scroll to the side, you can see the main column and the VPC column. We're going to look for the main route table for the app VPC, which is this one here. When we click on it, we can bring up the bottom panel and then click on Routes. Here we can see the local route that has a destination of the VPC IP range. This means that all of the components inside of our VPC can communicate with one another locally by default. This local route will be present in every route table that you create. All right, that's the main route table. Okay, what's next, Alana?
While the main route table controls the routing for your entire VPC, you may want to be more granular about how you route your traffic to specific subnets. Remember we mentioned that subnets can be used to group your resources together based on whether they are publicly or privately accessible? Well, the subnet itself doesn't provide that access. Whether a subnet has access to the public internet or not depends on its associated route table. If a route from the internet gateway to the subnet exists, it has public access. If the route table doesn't have a route between the subnet and internet gateway, then it doesn't have public access. So we call subnets public or private, but it's really the route table that provides that access. So for your subnets, you'll create custom route tables. Inside these custom route tables, you'll have that default local route inside of it that allows traffic to flow freely within the VPC. But then you'll need to create additional routes. So the subnet with the internet-facing resources, in this case our EC2 instance with the employee directory website on it, will need a route to the internet gateway. All right, Morgan, we need your help again. Do you mind creating a custom route table and associating it to our public subnet?
Sure can. Let's go ahead and get started. Let's create the route table for our public subnet. Back in the VPC console once again, we'll click on Route Tables on the side panel and then Create Route Table. We'll give it a name, such as App Route Table Public, choose the App VPC, and then click Create. Okay, our route table is now created. But we're not done yet. We still have to edit the routes to allow traffic to flow from the internet gateway. To do this, we'll click on the ID of the route table and then we'll go to the routes section in the bottom summary table. We'll click Edit Routes, Add Route, put 0.0.0.0/0 for the destination, meaning it can take and deliver traffic from anywhere, and then we'll specify the target as an internet gateway. This will bring up available internet gateways to attach it to, and from here we'll select the app IGW. We're done with the routes, so we'll click Save. Now the route table is created, but we need to associate it with a subnet. If we only want this route table to apply to our public subnets, we'll need to associate it with our 2 public subnets only. To do this, we'll click on the Subnet Associations tab, select Edit Subnet Associations, and choose the public subnets we created earlier, then click Save. So you can see here that the subnet itself isn't providing the public access, it's the configuration of the routes. All right, we've hooked up our public subnets to a route table that allows internet traffic from the IGW to our employee directory application. If we wanted to create a route table for the private subnets, we would follow similar steps. You'd create the route table, make sure there's no route to the internet gateway this time, and then associate it to the private subnets. We'll let you do this part in the exercise at the end of this week. Okay, now we've configured a route to the internet gateway. We'll configure additional firewall rules later on. Okay, back to you, Alana.
Nice job, Morgan. So this is our final state of the diagram. 1 VPC, 4 subnets, 1 public, 1 private, in both availability zones. Our 2 public subnets are associated with a route table that allows traffic flow from the internet gateway. Our private subnets don't have a route table associated to them yet, so they follow the rules of the main route table. Local traffic only. Now we have a complete network that enables internet traffic flow to our public subnet. But how do we know it's secure? Well, at the base level, we know that any new VPC is isolated from internet traffic, so that prevents risk. But when you start allowing internet traffic by opening up routes, you need other options to keep your network secure. In AWS, you have 2 options to secure your VPC resources: Network Access Control Lists, which are often referred to as network ACLs, and security groups. We'll start with network ACLs. You can think of a network ACL as a firewall at the subnet level. With network ACLs, you can control what kind of traffic is allowed to enter and leave your subnet. So if I were to draw network ACLs in our diagram, they are placed around each of our subnets by default. The default network ACL allows all traffic in and out of your subnet. Using this default configuration is a good starting place, but if needed, you can change the configuration of your network ACLs to further lock down your subnets. For example, if I only wanted to allow HTTPS traffic into my subnet, I can do that. I can create a rule in my ACL that allows HTTPS traffic from anywhere on port 443 and denies everything else. However, just because I allow inbound HTTPS traffic does not mean my job is done. If I don't open up the corresponding outbound port used for that protocol, then that means the traffic is allowed in, but the web server's response will never leave the subnet. This is because network ACLs are considered to be stateless. I need to include both the inbound and the outbound ports used for the protocol. What that means for our HTTPS example is that I need to allow outbound HTTPS traffic from the subnet to the internet by creating an outbound rule. The other security feature is security groups. These are firewalls that exist at the EC2 instance level. Security groups are not optional, so anytime you create an EC2 instance, you'll need to place that EC2 instance inside a security group that allows the appropriate kinds of traffic to flow to your application. In our diagram, if I were to draw security groups, I would draw them around every EC2 instance in the VPC. In our case, we simply just have one EC2 instance, so we would need a security group around that instance. You know what? I think it's time for a demo. Let's get Morgan back in here. Hey, Morgan.
Hey, Alana. What's going on?
Do you have some time to build out a security group for our employee directory application? I think we need an example.
Sure. Let's get started. The default configuration of a security group blocks all inbound traffic and allows all outbound traffic. If you want your EC2 instance to accept traffic from the internet, you'll need to open up inbound ports. If you have a web server, you might need to accept HTTP and HTTPS requests to allow that type of traffic through your security group. You can create an inbound rule that will allow port 80 HTTP and port 443 HTTPS as shown here. The beauty of security groups is that I don't need to open up an outbound port for traffic to be able to leave the instance. That's because security groups are considered to be stateful resources. They will remember if a connection is originally initiated by the EC2 instance or from outside and temporarily allow traffic to respond without having to modify the inbound rules. All right, Alana, is that everything?
That's all for this one. Thanks, Morgan. Remember that security groups and network ACLs are powerful tools to filter network-wide traffic for a single instance or subnet's traffic. With security groups, everything is blocked by default, so you can only use allow roles. Whereas with network ACLs, everything is allowed by default, but you can use both allow and deny roles. To round out this week, it's time for an exercise. In this exercise, you'll be building out a custom VPC for your application. You'll then spin up an EC2 instance, place it in the network, and then connect to it to see your app. So you'll first create the VPC, and then you'll create 4 subnets, 2 public and 2 private. You'll then want to provide internet connectivity to your public subnets. To do this, you'll create an internet gateway and attach it to your VPC. You'll then need to create 2 custom route tables. The first will be a public route table, where you will add a route to the internet gateway. You'll then associate it with your 2 public subnets. The second route table will be the private route table, which will only have the local route. And you'll associate it with your 2 private subnets. Next, you'll launch an instance hosting your application. When selecting the network for that instance, you'll choose the VPC you just created and one of the public subnets to place it in. From there, you'll access your application through the browser. Note that because the application isn't hooked up to a database, you won't be able to actually interact with it yet. That's coming soon. Remember, if you get stuck, make sure you check out the class discussion forums. Have fun.
Hello again. I'm so happy to see that you've made it to week 3 of the course. So far, you've learned about compute and networking on AWS. It's time to move on to 2 other major categories: storage and databases. The employee directory application that we are building out currently has a solid network in place using Amazon VPC, and it's being hosted on top of Amazon EC2. The only issue is the app doesn't actually work yet because we haven't set up anywhere for it to store the employee information or the employee photos. This week, we are going to fix that. We will start off by learning about the different storage offerings AWS has, and we will compare and contrast them. Then you will create an Amazon S3 bucket in your account that the employee directory app is going to use to store the employee images. Then we will explore the different database services AWS has, and there are a lot. Though not to worry, we are going to focus on 2: Amazon Relational Database Service, otherwise known as RDS, and Amazon DynamoDB. You will then complete one final exercise for this week by creating a DynamoDB table where the employee information will reside. As always, make sure that you are utilizing the class discussion forums to ask any questions that you may have along the way. Take your quizzes, and please take a good look at the readings that we have placed between the video lessons. There's a lot of extra information in there that could be useful to you as you continue your journey with AWS. So, great work so far. Keep it up, and I'll see you in a bit.
Let's recap the architecture for our employee directory application. We've created the VPC and launched the app on an EC2 instance. The next thing we need to configure is the storage. Our application requires several types of storage for its data. For one, we need to store the operating system, software and system files of our app. We also need to store static assets like photos for the employee headshots. And then we have more structured data, such as the name, title, and location of each employee as well. All of that needs a home. The structured data usually requires a database, which we'll talk about later this week. So for now, we'll focus on storing the application files as well as the static content. There are 2 main types of storage that we can use to store this data: block and object. Here's the difference. Let's say that I have a 1 GB file with text in it. If I'm storing this in block storage, what happens is that this file is split into fixed size chunks of data and then stored. Object storage, on the other hand, treats each file like a single unit of data. This might seem like a small difference, but it can change how you access and work with your data. For example, let's say I want to change one character out of that 1 GB file. If my file is stored in block storage, changing that one character is simple, mainly because we can change the block, or the piece of the file that the character is in, and leave the rest of the file alone. In object storage, if I want to change that one character, I instead have to update the entire file. Let's take these 2 types of storage and access patterns and try to apply them to the data we want to store. For example, our static data, like the employee photos, will most likely be accessed often but modified rarely. Therefore, storing it in object storage is fine. For more frequently updated data, or data that has a high transaction rate, like our application or system files, block storage will perform better. In this section of the course, we'll discuss both block and object AWS storage services and how they interact with our employee directory application. Before we do that, take a look at the notes to get a refresher of the different types of storage. That way you can easily match the storage type to the AWS storage services that we talk about. When you launch an EC2 instance, you're going to need some kind of block storage to go with it. This block storage can be used as a boot volume for your operating system or as a separate data volume. For example, think about your laptop. With a laptop, you store your data in drives, and those drives can either be built in internally to your laptop or connected externally. EC2 instances have the same options as far as block storage goes. This internal storage is called Instance Store, and the external connected storage is called Amazon Elastic Block Store or Amazon EBS. Let's talk about Instance Store first. Instance Store is a form of directly attached storage, which means the underlying physical server has at least one storage unit directly attached to it. This direct attachment is also the main advantage of using this form of storage. Because it's so close to the physical server, it can be very fast and respond very quickly. But while it can be very fast, there is also one big downside. Because Instance Store is directly attached to an EC2 instance, its lifecycle is tied to the lifecycle of your instance. That means if you stop or terminate an instance, all data in Instance Store is gone. It can no longer be used or accessed. Over time, customers wanted the ability to keep their data even if they shut their EC2 instance down. So to provide that ability, Amazon created another storage option for EC2 called EBS volumes. These volumes, as the name implies, are drives of a user-configured size that are separate from an EC2 instance. The drives are simply network-attached storage for your instance. You can think of it as similar to how you might attach an external drive to your laptop. EBS volumes act similarly to external drives in more than one way. For example, I can plug in my drive to only one laptop at a time. The same goes for EBS. Most EBS volumes have a one-to-one relationship with EC2 instances, so they can't be shared or attached to multiple instances at one time. When I connect that EBS volume to my instance now has a direct communication line to the data in that volume. Nobody else can directly talk to that volume so that it maintains secure communication. If I decided I want to use that EBS volume with another instance, we can stop the instance, detach the volume, and then attach it to another instance in the same AZ, much like you can unplug your drive from your laptop and plug it into another one. Or depending on the instance type and EBS volume we're using, we may be able to attach it to multiple instances at a time, which is called EBS multi-attach. And perhaps the most important similarity is that an EBS volume is separate from your instance, just like an external drive is separate from your laptop. That means if an accident happens and the instance goes down, you still have your data on your EBS volume. This is what we refer to as persistent storage. You can stop or terminate your instance and your EBS volume can still exist with your data on it. EBS is often the right storage type for workloads that require persistence of data. However, the question typically comes down to, which EBS volume type do I use? That's right, there are many different types of volumes, but they're divided into two main types: SSD-backed volumes and HDD-backed volumes. In the readings, you'll learn more about both of these types. The last thing we'll need to talk about here is backing up data. Things fail, errors happen, so you need to back up your data, even in AWS. The way you back up EBS volumes is by taking what are called snapshots. EBS snapshots are incremental backups that are stored redundantly. The idea here is that if something goes wrong, you can create new volumes from your snapshots and restore your data to a safe state. All right, so we figured out block storage for our application. Now we need to figure out where to store our employee photos. A natural question is, why can't we just store these photos in Amazon EBS? Well, there's a few reasons. Number one, most EBS volumes can only be connected to one EC2 instance at a time. Eventually, as my app scales, I'll need to figure out how to access those photos from all of my instances. That's an issue. The second consideration is that an EBS volume has size limitations. That means that eventually there will be a limit to how many HD 4K photos I store of my employees in one drive. Ideally, I'd store these photos in a more scalable solution. So EBS probably isn't the right choice. Fortunately, AWS has a service called Amazon Simple Storage Service, or Amazon S3, that was designed to be a standalone storage solution that isn't tied to compute, meaning you don't mount this type of storage onto your EC2 instances. Instead, you can access your data through URLs from anywhere on the web, which gives this service its nickname, Storage for the Internet. S3 also allows you to store as many objects as you'd like, with an individual object size limit of 5 terabytes. This makes it ideal for our employee photos. Now let's talk about how we store things in S3. The underlying storage type for S3 is object storage. That means that all of the same characteristics of object storage are also characteristics of S3. So S3 uses a flat structure. It uses unique identifiers to look up objects when requested. You get the idea. S3 is also considered distributed storage, meaning that we store your data across multiple different facilities within one AWS region. This is what makes S3 designed for 99.99% availability and gives it 11 nines of durability. All right, let's learn about some S3 concepts. The first concept is a bucket. In S3, you store your objects in buckets. You can't upload any object, not even a single photo, to S3 without creating a bucket first. You then place your objects inside these buckets, and if you want to organize and arrange those objects, you can also have folders inside of the buckets. Let's create a bucket in the console. When you log in, you'll type in S3 in the service search bar. Once you click on it, you'll see the S3 dashboard, showing you all the available buckets for every region. I'll then select Create Bucket. And what I want to point out here is that buckets are region specific. So what that means is we can choose where we want to place our bucket. In this case, we want to place our bucket close to our infrastructure for our application, which is in the Oregon region. So we'll go ahead and leave it as Oregon. Next, we have the name of our bucket. Even though our bucket is specific to one region, our bucket name has to be globally unique across all AWS accounts and must be DNS compliant. Once you create your bucket, AWS will construct a URL using this name, so it has to be something that can be reachable over HTTP or HTTPS, meaning there can be no special characters, no spaces, etc. So for this bucket's name, let's choose employee-photos-buckets-al-001, which is DNS compliant. Now we can leave the rest as defaults, scroll down, and click Create. To work with this bucket, I'll need to find it in the list and click on its name. Here we can start uploading our objects. To do this, I'll click Upload, and then click Add Files. Find the file I want to upload, and click Open. Then scroll down and click Upload. So, as you can see, the object upload was successful. If I click on the name of my object, I get to see quite a bit of detail here. I can see the owner, region, and size. But most importantly, we can see the URL of my object. The first part of this URL is simply just the bucket URL that AWS created using my bucket name. Then AWS appended the name of my object, also referred to as the object key, to the bucket URL. Now what happens if I click on this URL? Access denied. That's weird, right? Well, not really. That access denied message leads us to a bigger question that most people have when they start out on AWS, and that's who can access my data. Earlier, I mentioned that you can retrieve your data from anywhere on the web. and people often think that means that anyone can retrieve that data. But by default, it's actually the opposite. Everything in S3 is private by default. This means that all S3 resources, such as buckets, folders, and objects, can only be viewed by the user or AWS account that created that resource. That's why I get that access denied message, because I was acting as an anonymous user on the internet trying to access an S3 object that's private. Now, that's not to say that no object or bucket can be open to the world. They absolutely can be, if you explicitly choose that option. And it's actually kind of a process to make something public. The reason it's difficult to make your objects public is to prevent accidental exposure of data. Let's try it. Okay, so if we want to make the object we created public, we need to do a few things. First thing is, from the object detail page, we'll want to click on the Actions dropdown, and then select Make Public. Then click it again. Now, once we do that, a message will pop up saying that our setting is blocked. So to ensure that we allow public access to our objects, we'll click on this link in the message. From here, we'll go ahead and click Edit Block Public Access Settings. Uncheck the top box, and then click Save Changes. Type in Confirm, and confirm it. Now we'll go ahead and go back to our object by clicking on Objects, clicking on the object name, click Object Actions and Make Public again. And then we can go ahead and click on our object name again. And then click on the object URL. Now we can view our photo. That's how you make an object public. That being said, most of the time, you don't want your permissions to be all or nothing, to where either nobody can see it or everybody can see it. Typically, you want to be more granular about the way you provide access to resources. As far as access control, you can use IAM policies attached to users, groups, and roles to access your S3 content, and you can also use a feature called S3 bucket policies. S3 bucket policies are similar to IAM policies, in that they are both defined using the same policy language in a JSON format. The difference is IAM policies are attached to users, groups, and roles, whereas S3 bucket policies are only attached to buckets. S3 bucket policies specify what actions are allowed or denied on the bucket. For example, you might want to attach an S3 bucket policy to it that allows another AWS account to put objects in that bucket. Or you might want to create a bucket policy that allows read-only permissions to anonymous viewers. S3 bucket policies can only be placed on buckets and cannot be used for folders or objects. However, the policy that is placed on the buckets can apply to every object in that bucket. All right, to recap, S3 uses containers called buckets to store your objects, and you have several options to control access to those objects through the use of IAM policies and bucket policies. Thank you, and welcome back to everybody's favorite game show, Which AWS storage service do I use for my use case? Today we have one contestant during the final round of our show, and that's you.
In order to win the grand prize, you must answer the next 3 questions correctly. There will also be a bonus question, so there's an opportunity to get extra points. All right, once we read the question, you have 5 seconds to answer and earn some points. Okay, let's get started.
All right, this is the first question. Let's say you're a developer and you plan to build out an application to transcode large media files like videos. You'll be using an AWS Lambda function to perform the transcoding, but you need a place to store both the original media files and the transcoded media files. Due to regulations, you need to store these files for at least a year. Which of the storage services that we've talked about in this course should you use? You have 5 seconds to answer. The answer is Amazon S3. Why is S3 the best solution here, Morgan?
Well, first off, the question says they're using a Lambda function. Because of that, I'm already ruling EBS out, as EBS volumes can only be attached to EC2 instances. Even if they were using EC2, video files are typically large in size, so you may have to use multiple EBS volumes to store that data, which might not be cost-effective in the long run. So EBS is out. Instance storage is also out for the same reason. We're not using EC2 here. But also, we want to make sure that this data will persist for a year, and instance storage is considered ephemeral.
All right, S3 it is. Let's put some points on the board for those who got it right. Morgan, tell us the next question.
The next question is, you're an architect for an e-commerce company. They want to run their MySQL database on an EC2 instance. This database needs a storage layer to store their order and customer information. The database will be frequently accessed and updated, so the storage layer needs to respond quickly. It's important that the storage is fast and durable. Which AWS storage service should you use? You have 5 seconds. And the answer is Amazon EBS. Add 30 points to your score if you got that right.
It seems like we're looking for storage attached to compute here. So why not Amazon EC2 Instant Store?
Right, that's also an option, but it's not ideal. Since it's an e-commerce company, their order and customer data is what drives the business, which means that the persistence and durability of that data is really important. Using EC2 Instance Store would definitely give us the speed that we're looking for, but it wouldn't give us the durability needed to store this data long term. So EBS is the right option.
That makes sense. All right, moving on. 2 more questions. You have a web application that needs to write to disk in order to perform certain calculations. The application will store temporary data during the calculation. The most important aspects of this architecture are speed and cost. With 5 seconds on the clock, which storage solution would you choose? And the answer is EC2 Instant Store.
Elena, would you mind telling us how we chose Instant Store and not EBS?
Sure. Once again, we're looking for storage attached to compute in this case. The first thing I want to point out is that this is temporary shuffle space we're talking about. So we're not looking at a huge amount of data, and we also don't necessarily care about the durability of that data. If the instance fails mid-calculation and you want to plan for failure, you can just restart the calculation from scratch. So durability doesn't matter, but cost does. By not using EBS and instead using Instant Store, you may save yourself some cost. That's because Instant Store is included in the overall EC2 instance price. So Instant Store is the best option in this case.
Okay, 30 more points on the board for those of you who got it. Now, the final bonus question for an extra 10 points is next. This is a tricky one, and you might have to think outside of the storage options that we've talked about so far. Okay, let's try it out. Let's say you're creating a WordPress site on multiple instances. By default, WordPress stores user uploads on the local file system. Since you want to use multiple instances, you'll need to move the WordPress installation and all user customizations into a shared storage platform. Which storage option would you use? 5 seconds to go. And the answer is Amazon Elastic File System, or Amazon EFS. We haven't talked about this service yet, so if you got points for this, great job. For those of you who didn't, no worries.
Let's go ahead and talk about the options. Morgan, typically when we talk about shared storage systems that multiple instances can access, we think Amazon S3. Why wouldn't we use it in this case?
Well, S3 isn't a file system. It actually uses a flat structure for storing objects instead of a hierarchy. Because S3 is a different type of underlying storage, it's actually not right for this WordPress use case. So, by moving the entire WordPress installation directory onto an EFS file system and mounting it to each of the EC2 instances when they boot, your WordPress site and all of its data is automatically stored on a distributed file system.
Wow, good to know. Well, you answered all 4 questions, and you win the grand prize of getting to do an exercise next. Congratulations, and that's it for today's show. Remember to check out the readings after this video. Now that you have a better understanding of storage on AWS, it's time for a hands-on exercise. In this exercise, you'll be working with Amazon S3. You'll have the opportunity to create an S3 bucket, upload an object, and create a bucket policy. Let's quickly go through what you'll be doing in the console. The first thing you'll need to do is create an S3 bucket. To do this, you'll find Amazon S3 in the search bar. And then in the S3 dashboard, you'll click Create Bucket. We'll name this bucket employee-photo-bucket. And then at the end of the bucket name, we'll append your initials and also a random number. This is to ensure that the bucket name is unique across all AWS accounts. We'll also locate this bucket in the Oregon region. Once you create a bucket, you can then upload your photos. I'll do this by clicking on my bucket name and then click Upload. From here, I'll click Add Files, find the object I want to upload, and then click Open. And then upload once more. From there, you should get a message saying you successfully uploaded your photo. Now, just because you uploaded a photo in S3 doesn't mean your application can read it by default. You'll need to give it permission to do so by creating a bucket policy that allows access from your application. The next step is we'll click Exit, which will take us back to our bucket, and then we'll click on the Permissions tab. From there, we'll scroll down and click Edit Bucket Policy. We'll supply you with the correct bucket policy, so you'll just need to copy and paste, and then click Save. The next thing you'll need to do is modify your application so that it knows which S3 bucket to access. To do this, we'll launch a new EC2 instance hosting your application and change the user data. So we'll first find the EC2 service. Click on Instances. Find the instance you launched earlier, then click on Actions, Images and Templates, and then click Launch More like this. This will use the exact configuration of your instance that you had before. However, you need to modify the user data. So you'll click on Step 3 from above, scroll down to the bottom where it shows your user data, and then where it shows Export Photos Bucket, you'll type in the name of your bucket. All right, once you're done with that, you'll click Review and Launch, click Launch, and then click Launch again. Your application will now use the S3 bucket you created and has access through the bucket policy to your objects. That's it for this one. If you get stuck, remember you can always post questions in the discussion forums. All right, have fun.
The employee directory application that we've been building out lets you keep track of employee data like their name, location, job title, and the different badges. The app supports adding new employees, viewing existing employees, as well as editing and deleting employees. All of this data will be stored in a database, which we haven't created yet. According to the architecture diagram you've chosen, Amazon Relational Database Service, or Amazon RDS, is used to store this data. So let's talk about databases for a moment. Relational databases are widely used across all industries, and it's likely that your company has many databases supporting a variety of applications and solutions. You can install and operate database applications on Amazon EC2 instances. And this is a good option for migrating existing databases into AWS. By running databases on EC2, you are already simplifying things from an operational perspective when you compare it to on-premises. And it's also a very common use case for EC2. When migrating a database from on-premises to EC2, you are no longer responsible for the physical infrastructure or operating system installation. But you are still responsible for the installation of the database engine, the setup across multiple availability zones with data replication in place, as well as the database server management tasks like installing security patches and updating database software when necessary. So EC2 makes it easier, but there is a way to lift even more of the operational burden of running relational databases on AWS. What if, instead of managing a database on EC2, you use one of the managed AWS database offerings, like Amazon RDS? The big difference between these two options is instead of taking care of the instances, the patching, the upgrades, and the install of the database, AWS takes care of all of that undifferentiated heavy lifting for you. The tasks that you are then responsible for is the creation, maintenance, and optimization of the database itself. So, you are still in charge of creating the right schema, indexing the data, creating stored procedures, enabling encryption, managing access control, and more. But all of the rest of the undifferentiated heavy lifting that goes into operating relational databases, AWS takes care of. To start off this section of lessons on databases, we will first focus on RDS. The upcoming reading after this video will dive into the history of enterprise relational databases and explain what relational databases are and how they are used. If you aren't familiar with databases, the readings coming up will give you some of that useful background information. Amazon RDS is a service that makes it easier for you to set up, operate, and scale a relational database. Now, instead of just telling you the features of RDS, I'm going to show you. As you can see, I'm already in the Amazon RDS dashboard. We are going to create the relational database our employee directory application can use to store the employee data. First, we will click Create Database, and then we are going to select the Easy Create option. This gives us the ability to accept the standard best practices for things like backups and high availability. You could select the standard create if you wanted to have more of a granular control to pick these sorts of features for your database setup. Next, we can scroll down and you will see the different database engines to choose from. What you see here on the screen is currently what is supported at this time of filming for database engines on RDS. There are the common engines out there like MySQL, PostgreSQL, Microsoft SQL Server, or Oracle, and then there's this one, Amazon Aurora. Amazon Aurora is an AWS-specific database that was built to take advantage of the scalability and durability of the AWS Cloud. Aurora is designed to be drop-in compatible with either MySQL or PostgreSQL. It can be up to 5 times faster than a standard MySQL database, and it can be up to 3 times faster than a standard PostgreSQL database. So if you have some use cases that require large amounts of data to be stored with high availability, durability, and low latency for data retrieval time, maybe consider using Amazon Aurora over a standard MySQL or PostgreSQL RDS instance. You can also compare this with other enterprise database options. In our case, we really only need a simple database without any high performance or large storage requirements, so I'm going to go ahead and select a standard MySQL instance. Next up, we need to choose the database instance size. This database instance is what we call one instance of RDS. You can think of it similar to an EC2 instance. And also similar to an EC2 instance is that you can choose the size of your database instance. Since this is just a demo, I'm going to go ahead and select a free tier eligible instance. Now we'll go ahead and scroll down and we'll give this database a name. We'll call this employee database. And then we will give the database a password for the admin user that would be used to connect to the database. We'll go ahead and just give this a simple password. Then we will scroll down and we're going to accept all of the rest of the defaults, which you can see here if you wanted to review. And then we will click Create Database. You can see the DB instance is in the process of booting up. You can see it's in this creating status. So that's going to take a couple of minutes to complete. In the meantime, let's talk about high availability and RDS. When you create an RDS DB instance, it gets placed inside a subnet inside of a VPC, very similar to an EC2 instance. As you learned in a previous lesson, subnets are bound to one AZ. And as a best practice for production workloads, we recommend that you always replicate your solutions across at least 2 AZs for high availability. With RDS, one DB instance belongs to one subnet inside of one AZ. So that isn't meeting the criteria for best practices. Now, before you get worried about managing all of this on your own, just know that you can easily configure RDS to launch a secondary DB instance in another subnet in another AZ using an RDS multi-AZ deployment. And RDS will manage all of the data replication between the two instances so that they stay in sync. The other cool thing about RDS multi-AZ deployments is that RDS also manages the failover for the instances. One instance is the primary, and the other is the secondary. Your app connects to one endpoint. If the primary instance goes down, the secondary instance gets promoted. The endpoint doesn't change, so no code change is needed. All the failover happens behind the scenes and is handled by RDS. All you need to do is make sure that your app can reconnect to the database if it experiences a momentary outage by updating any cached DNS lookups and reconnecting to the endpoint, which now points to the secondary instance. That's pretty cool if you ask me. All right, now let's hop back into the console. All right, and we're back, and you can see that the instance is up and running because the status is now available. At this point, you could connect to this database instance using something like MySQL Workbench, and then you could load your database schema onto it, ready to go, and much simpler than trying to install and manage this all on your own using something like EC2, for example. Using services like RDS makes operating databases significantly more accessible and lowers the operational overhead that comes along with relational database management. Before we move on to learning about Amazon DynamoDB, I want to touch on an idea that is important when you're making architecture decisions for your AWS solutions. Choosing the right database to fit your business requirements, rather than forcing your data to fit a certain database choice. There is no one-size-fits-all database for all purposes. You should pick a database that fits your specific use case. And with AWS, you have many choices for databases. We covered Amazon RDS and relational databases, and that was the default option for businesses for a long time. But relational databases aren't the best choice for all business needs. AWS creates services to support purpose-built databases, meaning that there are many database services AWS offers, and they each were built with specific use cases in mind, and therefore they are optimized for those use cases. Let's think about the employee directory application. We had originally decided that we would use RDS for the database, but now, after thinking about it some more, RDS might not be the best fit for our needs. all we are really doing is storing one record in a table for each employee. There are no complex relationships that need to be managed, and it's essentially just a lookup table. Relational databases offer all sorts of features that are great for complex schemas and relationships. But those features add overhead that is unnecessarily complex for simple things like lookup tables. On top of that, the RDS option we chose charges per hour of instance runtime. So we will get charged for the instances regardless of if we are using them or not. Our employee directory application will have much higher usage during the week and no usage on the weekends. Is there an AWS database offering that better fits our needs? Introducing Amazon DynamoDB. Amazon DynamoDB is a non-relational database that is great for storing key value pairs or documents or non-relational data. This service works great at a massive scale and provides millisecond latency. It also charges based on the usage of the table and the amount of data that you are storing in that table, not by the hour or by the second. This is a better option for our simple employee lookup table. Now, besides the employee directory application, there are other use cases that require databases of varying types. What if you are writing an application that needs a full content management system? Neither RDS nor DynamoDB would be the best solution for that. Luckily, AWS has quite a number of other database offerings. For this use case, you might look into Amazon DocumentDB. It's great for content management, catalogs, or user profiles. Now let's think of another use case. What if you had a social network that you were trying to keep track of? Keeping track of those kinds of social webs, figuring out who is connected to who, and querying that sort of data can be difficult to manage in a traditional relational database. So you could use Amazon Neptune, a graph database. This graph database is engineered for social networking and things like recommendation engines, but it's also good for use cases like fraud detection. Now, perhaps you have a supply chain and you need to keep track of everything with assurances that nothing is lost. Or maybe you are a banking or financial institution with records that require 100% immutability. What you really need is an immutable ledger. So perhaps look into Amazon QLDB or Quantum Ledger Database as a better fit for this use case. It's an immutable system of record where any entry can never be removed, and therefore it's great for industries that need to be audited for regulatory and compliance reasons. So, that was a quick rundown of some of the database offerings AWS has that are purpose-built. It can take a lot of experience and expertise to operate databases at scale. And that's why it's so beneficial to utilize one of the AWS database offerings. You don't need to be an expert on running a graph database to get to use one. Instead, you can just use the database service that is best for your use case and focus on your application and providing value to your end users. You don't need to build up a ton of in-house expertise to operate a highly scalable, immutable ledger database. You can just use AWS QLDB instead. The key thing to understand is AWS wants to make sure that you are using the best tool for the job. Coming up next, we will explore Amazon DynamoDB and get a look at more of the details. Let's talk some more about Amazon DynamoDB. At the most basic level, DynamoDB is a database. It's a serverless database, meaning you don't need to manage the underlying instances or infrastructure powering it. With DynamoDB, you don't create a database with tables that relate to each other like a relational database. Instead, you create standalone tables. A DynamoDB table is just a place where you can store and query your data. Data is organized into items, and items have attributes. If you have one item in your table or 2 million items in your table, DynamoDB manages the underlying storage for you, and you don't need to worry about scaling the system up or down for storage. DynamoDB stores the data redundantly across availability zones and mirrors the data across multiple drives for you under the hood. This lessens the burden of operating a highly available database. DynamoDB, beyond being massively scalable, is also highly performant. DynamoDB has a millisecond response time, and when you have applications with potentially millions of users, like an online game, having scalability and reliable, lightning-fast response times is important. Now, DynamoDB isn't a normal database in the sense that DynamoDB doesn't require a rigid schema or manage complex relationships or constraints. Relational databases work great for a lot of use cases and have been the standard type of database historically. However, these types of rigid SQL databases can have performance and scaling issues when under stress. The rigid schema also makes it so that you cannot have any variation in the types of data that you store in a single table. So it might not be the best fit for a dataset that is a little bit less rigid and is being accessed at a very high rate. This is where non-relational databases like DynamoDB come in handy. Non-relational databases have flexible schemas. With DynamoDB, you can add or remove attributes from items in the table at any time, and not every item in the table has to have the same attributes. This is great for datasets that do have some natural variation from item to item. The types of queries you run on non-relational databases tend to be simpler and focus on a collection of items from one table, not queries that span multiple tables. This, along with other factors, including the way the underlying system is designed, allows DynamoDB to be very quick in response time and highly scalable. So, things to remember. DynamoDB is non-relational. It is purpose-built, meaning it has specific use cases, and it isn't the best fit for every single workload out there. Taking a look at our architecture, we modified it to be using DynamoDB. We are now going to need to create an employees table for the app to write to and read from. We will create this DynamoDB table using the console. And you know what? Let's call Alana in here for this one. Hey Alana, can I get some help in here?
Hey y'all!
We changed our minds about using RDS and decided to change it over to DynamoDB. It's only one table, and it's essentially a lookup table for the employees. How hard do you think it would be to make this change?
Well, our app is actually designed to handle either RDS or DynamoDB as the backend database, so this won't take long at all. Here, I'll show you how. I'm in the console, and I'll go ahead and navigate to the DynamoDB service. From here, all you need to do is create a new table. Tables in DynamoDB require you to designate certain attributes as keys that make an item unique. We will select employee ID as the unique identifier for the items in this table. So we'll call the table name employees, and the primary key will be ID. Then we will just accept the defaults and create the table. Our app was coded to look for a table specifically called employees, so this actually should all work now that the table is created. To test it out, let's head over to the website hosted on EC2 and try to add a new employee. Click Add, and I'll go ahead and add myself. My name is Alana Layton. My location is Seattle. My job is a cloud technologist. And then let's see, I'm a Mac user. We'll say I'm employee of the month. Sorry, Morgan. And I am also a Seattle fan. Then I'll go ahead and add my picture. Click Open. And then click Save. All right, so now I'm added on the website. Now let's go back into DynamoDB and refresh the page. Then we'll click on Items to view all the items in the table. And there you can see my item. It's really that simple for a lookup table like this one. Back to you, Morgan.
Well then, that was easy. Nice. Now, not every use case is this simple. In the readings after this video, there will be more information about how DynamoDB works, use cases, how to create indexes, some information on table design, and links to further learning materials on DynamoDB. Let's put your new database knowledge to use. So far, the employee directory application is operating on EC2, and you have already created the Amazon S3 bucket from which the application will read from and write to for the employee photos. But you aren't really able to test that out without the database also being in place, since adding a new employee needs to store both employee photos and employee data. So let's go ahead and fix that. In this upcoming exercise, you will create a DynamoDB table called employees. And you will configure this table to store the employee ID, first and last name, location, title, and badges for the employees. You will then open the application from the browser and attempt to add a new employee, edit the employee, and delete the employee. After each step, you will verify that the data is being updated in the DynamoDB table using the AWS console. After you're done creating the table and populating it, you'll have a working app. The DynamoDB table you will use is automatically scalable and highly available. So there really isn't that much to do for this exercise. So have fun.
Hello everyone, welcome back to the final week of the course. You're almost done. Now that we've added a storage and database layer, the employee directory application is fully functional. But we have two more issues. The first issue is that we have no insight into how our application is performing and how it utilizes resources. So to fix this, Morgan will start off this week with a discussion of a monitoring tool called Amazon CloudWatch. After we understand what the demand for your application looks like, we'll address the second problem, scalability. You may find that your application demand isn't always constant. So in the last section of the course, you'll learn how to automate the process of adding resources as demand increases and reducing capacity as demand declines to reduce cost. You'll also learn how to deliver traffic and balance load across changing amounts of resources. And if you made it this far, you already know we have discussion forums to help keep you on the right track, and readings after every video if you want to learn more. Let's get started with week 4.
When you have a solution built out of many different pieces, like how we build solutions on AWS, it's important to be able to see how different services are operating over time and to react to operational events as they are happening. Let's consider the employee directory application. It's Monday morning, and the users are seeing a latency on page loads. It's probably not good enough to wait until the user sees a slowdown, calls, or enters a ticket saying, "Hello, your application is running slow." If you receive a call or ticket from your users, you can then react and troubleshoot the issue. However, waiting for users to notice and report issues to investigate will generally lead to unhappy end users. Ideally, you'd be able to respond to operational issues before your end users notice. On top of that, the end user can only provide information about their experience, and they cannot give you insight into the inner workings of your solution. So, they can report the issue to you, but where is that issue stemming from? Is it an EC2 problem? Is it a database problem? Is there a code change that was recently made that's causing some issues? Without monitoring, you have to do some digging to figure that out. So, what do we need to do? The first step is to put proper monitoring in place. Monitoring is a verb. It's something that we do. We collect metrics, we collect logs, and we watch network traffic. The data needed to help you pinpoint problems comes from the different services and infrastructure hosting your application. And monitoring tools help you collect the data being generated by these systems. In a cloud environment that is ever-changing and ever-scaling, it's even more important to collect various types of information about the systems as they scale up and down and as they change over time. The different services that make up your solution generate data points that we call metrics. Metrics that are monitored over time are called statistics. A metric is a data point, like the current CPU utilization of an EC2 instance, where other data you could monitor might come in different forms, like log files. For example, Your network will generate data, like flow logs, so you can see how network traffic is coming into and out of your VPC. The servers will be generating metrics, such as how much CPU is currently being used, or how much network traffic the instance is accepting at any given moment. Then finally, one more example is your database layer, which will generate metrics such as the number of simultaneous connections. So you need a way to collect all of this information. Once it's collected, it can then be used to establish a baseline. And this baseline can then be used to determine if things are operating smoothly or not. If the information collected deviates too far from the baseline, you would then trigger automatic alerts to go out to someone or something to try to remediate the issue. A good monitoring solution gathers data in one centralized location, so that you can proactively monitor and operate your system to keep your end users happy, as well as allow for automated tasks to be triggered based on the data coming in. This is where Amazon CloudWatch comes in. CloudWatch allows you to monitor your solutions all in one place. Data will be collected from your cloud-based infrastructure, so you can see things like database metrics coming from RDS or DynamoDB, alongside EC2 metrics, as well as metrics coming from other services making up your AWS solution. Coming up next, we'll dive into some CloudWatch features and use cases. In this video, I'm going to run through some of the features that Amazon CloudWatch has to offer. We've already deployed resources into our AWS account for the employee directory application. So, to get a handle on what CloudWatch is and how it works, let's dive into the AWS console and see what we can see. The end goal of this demo is to set up a dashboard that shows us the CPU utilization of the EC2 instance that we launched hosting our employee directory application. And then we also want to set up an alert that will be sent out if the CPU utilization of the instance goes over 60% for a period of time. Something to note about CloudWatch is that a lot of AWS services begin reporting metrics to CloudWatch automatically when you create the resources. So let's go ahead and hop in the AWS console now, and let's explore what types of metrics are available from the resources we have already created in previous lessons. You can see that I'm already in the AWS Management Console, and what I want to do now is navigate to CloudWatch and select this service. And this brings me to the CloudWatch dashboard. And so now what I want to do to view the metrics that were created by the resources from previous lessons, I'm first going to create a dashboard. So I'm going to go ahead and click Dashboards. A dashboard in CloudWatch is a customizable page in the console that you can use to monitor different types of resources in a single view. This includes resources that are spread across different regions. I want to create a dashboard that shows me the CPU utilization over time for the EC2 instance. So now what I'm going to do is I'm going to create a dashboard. We're going to click Create Dashboard, and then we'll name it My Dashboard and click Create Dashboard. Next, we then select what we want to add to this dashboard, and we call them widgets. So I want to add a line graph as a widget on this dashboard because I want to compare the CPU utilization over time. So a line is going to be good for this one. Then I'll click Next. And then it asks from which data source would you like to create the widget. You can select metrics or logs. I'm going to go ahead and select metrics in this case. And then we'll click Configure. And now down here, it's listing all of the metrics and it groups by service because, again, AWS resources do often automatically post metrics to CloudWatch when it's created. So I'm going to go ahead and select EC2 for the service. And then I want to select per instance metrics. And now I'm going to filter the instances in this account by the instance ID for our employee directory application, which I just had copied in my clipboard. And now we can scroll down and see all of the different metrics that are available for this CPU instance. I'm going to go ahead and select CPU utilization here, and then I'm going to select Create Widget. All right, so now we can see that we have this widget, this line graph showing us the CPU utilization, and this gives us visibility into one aspect of the health of our EC2 instance. You can explore in your own account what other metrics are available to you through CloudWatch by default, but you also can report custom metrics to CloudWatch programmatically. This is good to know because with EC2 and CloudWatch, you only get visibility into the health of the instance by default, which doesn't really give you a holistic picture of the health of your application. The application running on the instance might not be operating correctly, but the CPU utilization could be fine. So keep in mind that you may choose to use custom metrics to get a more detailed and accurate view of health in these dashboards. So now, once a dashboard is created, you can then share it with others on your team so that everybody can get a good view of the health of your application. So now that we've created this dashboard, we're going to go ahead and click Save Dashboard, and that saves the widget here. And if you just hover, you can see the different data points and what the CPU utilization was. So you can see we hit a spike where we really maxed out our CPU for a couple of minutes here earlier today, and then it came back down. So this would have been indicative of some sort of operational event going on. So next what we want to do is move on to another feature of CloudWatch, and that is Amazon CloudWatch Alarms. So now I'm going to go ahead and click Alarms here. And notice I have no alarms in this account. What I want to do is create a CloudWatch alarm that will notify me whenever the CPU utilization goes over a certain threshold. So just in general, CloudWatch alarms allow you to create thresholds for the metrics that you are monitoring. And these thresholds can define normal boundaries for the values of the metrics. If a metric crosses a boundary for a period of time, then the alarm would be triggered. And you can then take a couple of different automated actions after an alarm is triggered. In our case, I just want to notify someone via an email when the CPU utilization spikes over 60% for some period of time, say 5 minutes. So let's create an alarm to do that. So now what we will do is click Create Alarm, and then we will select the metric for this alarm. We'll select EC2, per instance metrics, just as before, paste in that instance ID, and then select the CPU utilization metric and click Select Metric. From here, you can give this a specific name if you would like, and then you also have to select what type of statistic this is. We're going to leave it as average because we want to view the average CPU utilization over a time period. In this case, we are going to leave the time period to be 5 minutes. You want to make sure that you pick a reasonable time period where you don't wait too long to respond, but you also don't respond to every short-lived uptick in CPU utilization. There is a balance to strike here, and it will be highly dependent on your specific situation and your desired outcome. Okay, so now I will scroll down and I'm going to then type in 60 for the defined threshold here. And we are looking for the alarm to trigger when the metric crosses the threshold of 60% for more than 5 minutes. So now I'm going to go ahead and click Next. And this brings us to the Configure Actions page. And so for this one, you can now decide, okay, what are we going to do once this alarm is triggered? For CloudWatch alarms, there are 3 states an alarm can be in. Either in alarm, okay, or insufficient data. An alarm can trigger an action when it transitions between these 3 states. In our case, I want to have this send out an alert to an email address when it transitions from OK to in alarm. AWS has a service called Amazon Simple Notification Service, or SNS, which allows you to create a topic and then send out messages to subscribers of this topic. You can imagine a scenario where we have system admins or developers on call for our employee directory application. And if something goes wrong, we want to send them an email paging them, letting them know that something is wrong with the app that they need to look into. So, in order to make that happen, what we're going to do is we are going to select Create New Topic, and then we can give the topic a name. All we have to make sure here is make sure that it is unique. So I'm going to go ahead and name this employee app CPU. And then we are going to select the email endpoint that will receive the notification. In this case, I'm going to go ahead and just put my email address, and then we'll click Create Topic. Now that that is created, we will scroll down and then click Next. We'll give this alarm a name. This will be Employee App CPU Util, and then click Next. And now we can preview this alarm. So notice the red line here. We set the alarm at 60%. We would have triggered an alarm earlier, but we didn't have anything in place. So we didn't know that anything was going on. After this, if it spikes again, we should be able to get an email sent out to our admin, which in this case is me. All right, so I'll scroll down and then just click Create Alarm. And there it is. This will remain in the insufficient data state for a little while until it gathers enough information about the CPU utilization to be able to correctly read if this is okay or if it is in alarm. All right, so what we've done now is we've created a dashboard that is monitoring the CPU utilization of our instance, and we've created a CloudWatch alarm that will send out an email using Amazon SNS whenever the metric crosses the threshold. There are also other actions that you can take when an alarm is triggered, and we will go over that in upcoming lessons. So that's it for now. We will continue to use CloudWatch in upcoming lessons to make our solution elastic through EC2 autoscaling. For now, you know the basics, and I encourage you to explore CloudWatch in your own account and create dashboards for your employee directory application.
At this point, you know how to set up alarms to notify you when your infrastructure is having capacity, performance, or availability issues. But we need to go one step further. We don't just want to know about these issues, we want to either prevent them or respond to them automatically. In this section of the course, you'll learn how to do just that. Currently, our infrastructure looks like this. We have one EC2 instance hosting our employee directory application in a single availability zone, with DynamoDB as its database and S3 for storage of static assets. If I wanted to evaluate the availability of our infrastructure, I have to look at each individual component. I know that both DynamoDB and Amazon S3 are highly available by design, so that leaves one issue: this singular instance of our application. If that instance goes down, employees have no way to connect to our application. So how do we fix this? Well, as you already know, to increase availability, we need redundancy. We can achieve this by adding one more server. But the location of that server is important. If instance A goes down, we don't want instance B to go down for the same reasons. So to avoid the unlikely event of, say, an AZ experiencing issues, we should ensure that instance B is put in a different AZ. So now we have two instances that we've manually launched. But let's say our company grows rapidly, and the employee directory application is constantly being accessed by thousands of employees around the world. To meet this demand, we could scale our instances vertically, meaning we could increase the size of the instances we have, or we could scale our instances horizontally, meaning we could add more instances to create a fleet of instances. If we scale vertically, eventually we'll reach the upper limit of scalability for that instance. But if we scale horizontally, we don't have those same limitations. I can add as many instances to my fleet as I'd like. But if I need, say, 15 more instances to meet demand, that means I'd have to manually launch those 15 instances and manually shut them down, right? Well, you could do it that way, or you could automate this process with Amazon EC2 Autoscaling. This service will allow you to add and remove EC2 instances based off of conditions that you define. With this service, you can also maintain the health of your fleet of instances. But with more EC2 instances comes a bigger issue. How do we access those servers? Before, we were simply using the instance public DNS name or public IP address. But when you have multiple instances, you have multiple IPs to route to. Instead of maintaining the logic to send requests to your various servers, you could use a load balancer to distribute those requests across a set of resources for you. And since you can connect from your load balancer to access the application, you no longer need to use the public IPs of your EC2 instances. Before the next video, I'll spin up another instance hosting our employee directory application in a different subnet in a different AZ. See you soon. Now that we have multiple EC2 instances hosting our application in public subnets, it's time to distribute our requests across our servers using the Elastic Load Balancing, or ELB, service. Conceptually, how this works is a typical request for the application would start from the browser of the client and is then sent to the load balancer. From there, the load balancer determines which EC2 instances to send the request to. After it sends the request, the return traffic would go back through the load balancer and back to the client browser, meaning your load balancer is directly in the path of traffic. Now, if we're looking at the architecture, the ELB looks like one thing. It looks like a single point of failure. But ELB is actually, by design, a highly available and automatically scalable service, much like S3 is. What that means is that A, the ELB is a regional service, so you don't have to worry about maintaining nodes in each availability zone or having to configure high availability yourself. AWS maintains that for you. And B, the ELB is designed to handle additional throughputs and will automatically scale up to handle the traffic coming in, without you having to configure that feature. Now, there are several types of load balancer that you can choose. There's the application load balancer that load balances HTTP and HTTPS traffic. There's the network load balancer that load balances TCP, UDP, and TLS traffic. And there's the gateway load balancer, which is mostly for routing traffic to third-party applications. For our employee directory application, we'll be load balancing web traffic, so we'll be using the application load balancer, or the ALB. When you create an ALB, you'll need to configure three main components. The first component is a listener. The goal of the listener is to check for requests. To define a listener, a port must be provided as well as the protocol. For example, since we're routing web traffic and we set up our application to use port 80, we'd want our load balancer to listen to port 80 using the HTTP protocol. Additionally, we could set up a listener for port 443 using the HTTPS protocol. The second component is a target group. A target is the type of backend you want to direct traffic to, such as EC2 instances, AWS Lambda functions, or IP addresses. A target group is simply just a grouping of these backend resources. Each target group needs to have a health check, which is how the load balancer can check that the target is healthy so that it can start accepting traffic. The ALB operates on the application layer, which is layer 7 of the OSI model. This gives the load balancer a lot of cool features, and one of those is the third component, which is a rule. A rule defines how your requests are routed to your targets. Each listener has a default rule, and you can optionally define additional rules. So if we had two target groups, A and B, we can set up an additional rule that says if traffic is coming to our /info page, we can deliver that traffic to target group B. So because of the fact ALB operates on layer 7, you can customize paths for your traffic. Okay, now it's time to put this into practice. Let's create an application load balancer in the console. If you want to find the ELB service, you'll need to go to the EC2 console. So we'll type in EC2 in the service search bar. And then on the side panel, we'll go ahead and select load balancers. Once we bring up our load balancers dashboard that shows all of the load balancers for this region, we'll then click Create Load Balancer. Here is where we choose which type of ELB we want, and you can see the three main types. We'll be using the ALB. From here, we'll choose a name and call it app-ELB. The next setting asks if we want an internet-facing or an internal-facing load balancer. An internet-facing load balancer does what you might expect, which is route requests from clients over the internet to your backend servers or your targets. An internal load balancer, on the other hand, will route requests from clients with a private IP to targets with a private IP. For example, if you had a 3-tier application with a web, app, and database tier, you could use an internal-facing load balancer to route traffic from your web tier to your app tier. For this app, we'll be routing internet traffic, so you can leave it as internet-facing. Then we select the listener. Currently, the default setting is to allow HTTP traffic on port 80. If we wanted to allow or limit to HTTPS traffic, we can click Add Listener, choose HTTPS, and we'll be good to go. But for this demo, we'll stick with the defaults. After that, we choose which availability zones we want to route traffic to. First, we'll choose the VPC. Then we'll select both availability zones, and then we'll choose the 2 public subnets. Then we'll go ahead and click Next, and then Next again. Now you choose your security group for your load balancer. This is where you decide which traffic you want to allow in. Here we'll choose a security group that will allow traffic on port 80 from anywhere. Next, we'll go ahead and configure routing. Here is where we create a target group for our backend instances. We'll give it a name such as app-target-group-2, and then we'll go ahead and leave all the defaults and click Next. This is where we'll be choosing which instances we want to live in the target group. So I'll go ahead and choose the 2 instances I have here, click Add to Registered, and then click Next, and then click Create. After the load balancer has been created, we can then select it in the menu, and then find the DNS name in the details page below. We can then pull that DNS name, copy it, and then paste it into a new tab. And from here, you can see our app. If I go to the /info page of our application, you can see which availability zone we're currently in. If I refresh the page a few times, you should see eventually that I'm being directed to both my EC2 instances in both AZs. And there you have it.
As more people visit our application, the demand on our 2 web servers is going to increase. At some point, our 2 instances aren't going to be able to handle that demand, and we're going to need more EC2 instances. Instead of launching these instances manually, we want to do it automatically with EC2 autoscaling. Autoscaling is what allows us to provision more capacity on demand, depending on different thresholds that we set, and we can set those thresholds in CloudWatch. Okay, so we're going to draw a high-level example of how this works, and then Alana is going to build it out for us. So, looking at our application, traffic coming in from the outside can come down to either EC2 instance. In this video, these EC2 instances will be part of an auto-scaling group. Each of the EC2 instances that we launch will be completely identical. Then, we're going to run code to simulate stress on our employee directory application that will make the instances think that they're overloaded. When this happens, the instances will report to CloudWatch and say that their CPUs are spiking. CloudWatch will then go into an alarm state and tell autoscaling, hey, give me more EC2 instances. As each instance comes online, they'll pass ALB health checks, they'll start receiving traffic, and give us the horizontal scalability that we need. As each instance comes online and accepts traffic, we should see the CPU utilization go down across the entire fleet. All right, Alana, did you hear that? Do you mind building this out for us?
Let's make it happen. So to get this built out, the first thing we need to create is a launch template. This is going to define what to launch. So it's all about setting the configurations for the instances we want to launch. Morgan said we want our instances to be identical, and that's what we'll be configuring here. First thing we're going to do in the EC2 dashboard is find launch templates on the side panel. And then click Create Launch Template. You'll first provide a name and description. I'll call this app Launch Template. And then the description will be a web server for the employee directory application. Then you'll notice this handy checkbox here that asks if you're going to use this launch template with EC2 autoscaling. We are, so we'll check it and then scroll down. We'll then choose the AMI. Again, the launch template is all about what we launch. So what we want to do is create mirrors of the web servers hosting our app that we already have running. That way, whenever we scale out, we just have more instances with the exact same configuration. When we launched the instance hosting our app earlier, we used the Amazon Linux 2 AMI and a T2 micro instance type. So we'll select both of those options. We'll also select the same key pair that we used earlier, called the app key pair. Next, we choose the security group for our new instances. We'll use the same security group you created in the course, which in this case is the web security group. And then we can scroll down and expand the advanced details section. In the instance profile dropdown, we'll choose the same role we used previously, which is this one. Once we do that, we'll scroll all the way down and paste in our user data. This is what grabs our source code and unzips it so that our application runs on EC2. Now we're done and we can click Create. Now that we've configured our launch template, which again defines what we launch, we now have to define an autoscaling group, which tells us where, when, and how many instances to launch. To create an autoscaling group, I'll go ahead and back out of this. And then we'll select autoscaling groups on the side panel. And then we'll click Create Autoscaling Group. Then we'll enter a name such as app-asg, and then choose the launch template we just created. And then we can click Next. Then we'll select our network. We'll choose the same VPC that we created earlier in the course, app VPC, and then we'll select both of the public subnets, public subnet 1 and public subnet 2, and then we'll go ahead and click Next. We then need to select Attached to an existing load balancer to receive traffic from the load balancer we created earlier, and then choose our target group, App Target Group 2. Then we can click Enable ELB Health Checks, so that the load balancer will check if your instances are healthy, and then we can go ahead and click Next. Now we'll choose the minimum, maximum, and desired capacity. The minimum we'll say is 2. That means that our autoscaling group will always have at least 2 instances, 1 in each availability zone. The maximum we'll say is 4, which means that our fleet can scale up to 4 instances. And the desired capacity, which is the number of instances you want running, we'll also say is 2. Next, we can configure the scaling policies. With scaling policies, you define how to scale the capacity of your autoscaling group in response to changing demand. For example, you could set up a scaling policy with CloudWatch that whenever your instance CPU utilization, or any other metric that you would like, reaches a certain limit, you can deploy more EC2 instances to your autoscaling group. So what we want to do is use autoscaling policies to adjust the capacity of this group. Earlier, Morgan created a CloudWatch alarm that resulted in the action of sending out an email. Here we're going to create a CloudWatch alarm, much like Morgan did, but this time it will result in the action of triggering an autoscaling event. So we'll go ahead and enable target tracking. We'll name this CPU utilization. Leave the metric type as CPU utilization. And then we'll say that we want to add a new instance into our fleet whenever the target value is 60%. We'll also say that instances will need 300 seconds to warm up. Then we'll click Next to configure notifications when a scaling event happens. This is optional, so for now we're going to skip past it, but you'll do it in the exercise coming up. You can also configure tags as well, but we'll skip past that too. All right, so we're here and we can review this and then click Create Autoscaling Group. Now all that's left is to stress our application and make sure that it actually scales up to meet the demand. To do that, I'll open up a new tab and paste the endpoint for our Elastic Load Balancer. So here's our application. I'm going to go to the /info page by appending it on the URL. And you'll notice here that we built in a stress CPU feature. This is going to mimic the load coming onto our servers. In the real world, you would probably use a load testing tool, but instead we built a stress CPU button as a quick and easy way to test this out. Then we can watch our servers scale with that autoscaling policy. So as the CPU utilization goes up, our autoscaling policy will be triggered and our server groups will grow in size. So I'm going to go ahead and select 5 minutes for the stress test. All right, some time has passed, we've stressed our application, and if we take a look at CloudWatch, we can see what happened. So let's find CloudWatch. And if we click on our OK alarms, and click on the Alarm High alarm, we can see our alarm summary. As you can see, we went over our 60% CPU utilization across our instances, and that was our threshold for our autoscaling group to launch new instances. So ideally, what would have happened is autoscaling launched more instances to handle this load. Because we've launched more instances into our autoscaling group, there were more hosts to accept traffic from our Elastic Load Balancer, and the average CPU utilization then went down across our servers. And you can see that here in the alarm summary. All right, so let's go ahead and look at the EC2 instances that were launched into the autoscaling group. I'm going to go to the EC2 dashboard. I'm going to scroll down to target groups, and then select the app target group. Click on targets, and as you can see here, we launched one more instance to help handle the load. So we have 3 healthy targets for our autoscaling group. So now we have an environment with an autoscaling group and our launch template. We've set up an alarm in CloudWatch that whenever our CPU utilization goes over 60%, we're going to launch more instances into that group. Okay, Morgan, back to you.
Thanks, Alana. Now, if we wait around long enough, what we would see is as the CPU load dropped off, then one by one, each instance would get terminated because we no longer need them, bringing our state all the way back down to the basic 2 servers that we need, which is the minimum number for this particular autoscaling group. All of that done without any human intervention. If for some reason you are doing this in your AWS account, don't forget to delete the autoscaling group instead of just the instances. Otherwise, guess what will happen? Well, the autoscaling group is going to say, hey, we need a minimum of 2 instances. So if you go in and just try to terminate the instances in that autoscaling group, it's going to notice that you are not meeting the minimum. It's going to spin up 2 more in its place. So in order to clean up in your account, make sure that you delete the autoscaling group or you set the minimum to be 0. So that way it doesn't go recreating resources that you're trying to delete.
Welcome to the final exercise of the course. And this exercise will be optimizing our employee directory application by using Amazon CloudWatch, ELB, and EC2 autoscaling. The first thing you'll do is create an application load balancer. You'll use this load balancer to distribute requests to your EC2 instances that host your application. Next, you'll use autoscaling to launch the instances. To do this, you'll first create a launch template to specify your instance configuration. You'll then use this launch template to create an autoscaling group. You'll specify a minimum of 2, maximum of 4, and a desired capacity of 2 instances. You'll also configure your autoscaling group to use the application load balancer you created. You'll configure your autoscaling group to scale based off of CloudWatch alarms, and trigger autoscaling to add a new instance when CPU utilization reaches 60%. Finally, you'll be able to go to your application and test this. By going to the /info page of the employee directory app, you can trigger an increase in CPU load and see your application horizontally scale in real time. Enjoy, and feel free to post in the discussion forums if you have any questions. And since this is your final exercise, remember to tear down all the infrastructure you created for this course. That way you can minimize future costs.
Nice work getting through this course. Let's take a look at how the architecture you built turned out. The employee directory application is currently being hosted across multiple EC2 instances inside of a VPC in private subnets. The EC2 instances are part of an EC2 autoscaling group, and traffic is being distributed across them using an application load balancer. The database is being hosted on Amazon DynamoDB, and the images are stored in S3. Beautiful. Looking at this from a maintenance perspective, you would need to ensure that your autoscaling policies are working well with your expectations. And it would likely take some amount of tweaking over time to get it right. You also would need to install any security patches and updates for EC2 as they come out, as well as keep an eye out for new instance sizes and types that might help you further optimize your solution. Now, this is really a great solution, but as with everything built on AWS, there are multiple ways you can architect a solution and have success. It really depends on what you are optimizing for and what you are trying to do that will determine how you architect an application. That being said, what I want to do now is present you with an architecture that could be a wonderful serverless redesign of the employee directory application, taking full advantage of cloud-native services like AWS Lambda. I'm going to touch on some services we haven't covered in this course also to give you ideas of alternative architectures. So, this employee directory application is a great example of a standard 3-tier application, where you have the presentation layer, the application layer, and the data layer. The presentation layer is the user interface. The application layer is the business logic, and the data layer is the database. As things are right now, the Amazon EC2 instances are hosting both the presentation layer as well as the application layer. This is true because the EC2 instances have a web server running that is serving the content for the website, like the HTML, CSS, and the JavaScript, which is the presentation layer. Then, the same instances are also handling requests for the backend logic for viewing, adding, updating, and deleting employees, which is the application layer. What I want to do now is separate these two pieces entirely, having the front end of the website hosted separately from the back-end application logic. It's important to separate the presentation layer from the application layer so that the instances are not overloaded by handling different types of requests at the same time. We are going to move the presentation layer to be hosted on Amazon S3. S3 supports static website hosting, and therefore, this is a great place for us to host the HTML, CSS, and JavaScript for our website. When you're hosting a static website with S3, you may think, well, my website isn't static. It's dynamic. It's pulling data from a database. So this isn't a static website, and therefore S3 wouldn't work for this use case. This is where JavaScript comes in. JavaScript files and scripts have the ability to make HTTP requests and load dynamic content, modifying the static page to display results that come back from the requests. So this should work well for us. The presentation layer is taken care of now on Amazon S3. Now what I want to tackle is the application layer. It used to be hosted on Amazon EC2, but let's go ahead and change this to AWS Lambda. This means that our employee directory application code would only be run in response to events being triggered by the front-end presentation layer. Now, you don't really want your front-end talking directly to your back-end code. So instead, you would expose your back-end Lambda functions using an API. We would use the service Amazon API Gateway to host this API. Each action that you could take on an employee would have its own method on the API. This API, hosted on API Gateway, would act as the front door to trigger the backend code, which we host on AWS Lambda instead of EC2, as discussed. We could have one Lambda function to handle all of the requests for employee data, or we could have one Lambda function per each action that you can take. We would keep DynamoDB for the database or the data layer, and we would also keep S3 for the employee photo storage. All of the access between these services would be handled via role-based access using IAM roles. One really nice thing about this is notice how because we built this solution in a more modular way, we were able to swap out how we were handling the presentation and application layer while leaving the data layer totally intact with no modifications. That is the type of flexibility that can help you innovate and adapt to change quickly. So now, for completeness and clarity, let's focus on the new architecture and fill it out a bit more. I will add some other AWS services to this diagram that you can explore on your own. I'm going to add Amazon Route 53 for domain name management for our website. And I'm also going to add Amazon CloudFront here as well, which will allow us to cache the static assets like the HTML, CSS, and JavaScript closer to our end users by taking advantage of the AWS Global Infrastructure's AWS Edge locations. If a user wants to visit the employee directory application website and view all of the employees, here is the flow. The user would first type in the domain for the website, which would get sent to Amazon Route 53. Route 53 would then send back to the client the address of the static website being hosted on S3, and then S3 would send back the content to be rendered in the browser. This website has JavaScript making the API calls to the backend to load the dynamic content. So the API call to load all the employees would be made and it would hit API Gateway first. API Gateway would validate the request and then trigger the backend Lambda function. The Lambda function would then send an API call to DynamoDB to query the employees in the table, and then it would then return that data to API Gateway, which would then be returned to the JavaScript, which finally would be rendered on the page. All right, and that's that. With this architecture we just laid out, we have optimized for scalability, operational overhead, and depending on your usage, it could also already be optimized for cost. The serverless aspects of this make the operations for support much less than compared with Amazon EC2-based solutions. There is no patching or AMI management when you use serverless solutions like AWS Lambda. Also, notice how it was not required that I create a VPC, subnets, security groups, or a network access control list for this solution. The networking aspect of this is managed for you, though you can integrate serverless services with your VPC if you need to for compliance reasons. However, it's not required to get a solution up and running. You have many options to choose from when designing your application. You can imagine a scenario where you redesign the same application to be hosted using AWS container services, and then this entire diagram would change. There are a lot of ways you can build on AWS, and that's really the beauty of it. You can swap certain pieces of your solution out as AWS services are released or gain new features. And because everything in AWS is an API call, you can automate the process along the way. That's it for this course. From me, Alana, Meowsy, and Kiwi, thank you so much for learning with us. Please remember to check the course notes after the video for links to other courses where you can learn more about the AWS Cloud. Also, one more reminder to please remember to delete any resources you created in your AWS account for this class to avoid incurring costs. Thanks again, and we'll see you next time.
Hello, and welcome to the first course of the DevOps series, the course that will talk about the code, build, and test parts of the DevOps workflow. My name is Rafael Lopez, but you can call me Ref, and I will be one of your instructors for this course. Russ and Alana will also join the party with videos, screen captures, virtual whiteboards, and hands-on activities. I'm pretty sure it will be fun for you to watch, as it was for us to create and record this content for you. If you work on writing software that gets in front of customers and wants to get a better understanding on how to apply some DevOps practice to your current workloads, this course is for you. You will explore AWS services that will help your application delivery, like AWS Code Commit, AWS Code Build, and AWS Code Pipeline. When developing code, we always have to ask ourselves questions such as, are the current practices quickly getting stable, innovative software in front of your customers? And can we leverage DevOps automation to gain the competitive advantage that comes from better workflows? We know that software is a critical component for many organizations that want to optimize their products and solutions by reducing time to market and create more robust code. Adopting the culture of automation is the key to achieve that. So in this first course of the DevOps series, we will focus on the code, build, and test aspects of the DevOps operation. We will get into topics like source control, best practice for continuous integration, and how to use the right tools to measure code quality by identifying workflow steps that could be automated. With automation comes confidence, and with confidence comes the optimization of time-consuming processes, resulting in better quality software that can be built faster. Join me, Alana, and Russ for the first course of the DevOps on AWS series on this platform. Let's talk about code, build, and test.
Hi, I'm Alana, and this is Carlos. He's a developer. His job is to create new, interesting features and write code. When Carlos is done creating a new feature, he hands it over to Martha in operations. Martha takes care of building and deploying that code, while Carlos starts creating another new feature. However, sometimes bad things happen. One time, one of Carlos's features that worked fine in his development environment brought up new errors and issues in the production environment. It was up to Martha, once that code was deployed, to solve these errors that were caused by the new changes. This wasn't very fun for Martha, as she was now managing this asset that she had no part in creating. And because she doesn't know it as intimately, it takes longer for her to troubleshoot it. It's not fun for Carlos either, as he may feel like he's juggling this pending feature, as well as the new features he has to create. They both feel like there's a wall between their two teams, when ultimately they both want the same thing. They want the code to be deployed with no issues. So how do the developers and the operations teams work better together? Well, this very question is why DevOps is now so popular, and why it's turned into a buzzword that's getting everyone's attention. Rightfully so. But unfortunately, with all the press, DevOps gets confused with a lot of other technical concepts. For example, some think that DevOps is synonymous with infrastructure as code, or the same thing as Agile, or it's just automated testing and delivery. But really, what is DevOps? DevOps is a way for the development teams and the operations teams to work better together and ultimately share the responsibility for the software they build. DevOps is just a bridge over the gap between development and operations. And DevOps isn't any one of these technologies. It's really more of a cultural shift in thinking. For example, with Carlos and Martha, they need to increase their collaboration, transparency, and their communication. They'll also both be taking on responsibilities outside the scope of their current position. Martha taking responsibilities on the development side, and Carlos taking responsibilities on the operations side. As they work to bridge the gap, they'll need clear expectations on both sides and to define who does what and how they'll work together. All of that is cultural. That being said, the cultural shift in thinking is only half the equation. The other half is the tooling. This is where things like Agile and infrastructure as code and automated test and delivery come into play. The idea is that you take the application of engineering practices and tools and apply them to operations tasks. In turn, this should help you deliver applications and services faster and at a higher quality. There are a few key tools and practices that are becoming more and more common. The first is the idea of making things smaller. For example, a common practice is to perform very frequent but small updates to an application. This practice leads to significantly more deployments, with each deployment being less risky. That's because when things are small, it's easier to troubleshoot, identify issues, and in general, you have a smaller external impact. The second concept is to automate everything. This helps keep computing resources elastic and responsive to those frequent changes. And if you make a mistake, you can very quickly go back and reliably reproduce the previous state. And then the last one I'll talk about is practicing continuous integration and continuous delivery. Often, when you're moving very quickly, there are new operational issues you have to solve. It's true you want to deploy quickly, but you also want to deploy in a safe and gradual manner. That's what CI/CD is all about, and we'll talk at length about this throughout this series of courses. Now, with the cultural shift side of things and the tooling you need to achieve DevOps, it's not just a one-time process that you set up at the beginning and it will always work. It's a continuous practice, and to showcase this, technologists often use an infinity loop to represent all the steps of the lifecycle and how they relate to one another. As you can see, what's needed for development is on the left side of the loop, and what's needed for operations is on the right side of the loop. They're combined, and you can't have one without the other. If you'd like to learn more about this culture and some of the core practices, check out the resources that are posted for the end of this week. You'll also learn some of the key components of DevOps throughout the next few weeks. Stay tuned. Hello, and welcome back. Now let's take a deep dive on the application we'll be working with in this course. As you might already know, this course will focus on the processes and practices you would use in a software development team. Our focus isn't really on the application itself. We'll focus more on the steps it takes to get high-quality software in front of users and getting the best possible availability or uptime of the application. But yes, we do have an application. We've created one so we can get hands-on with a close to real-world application. And here's my coworker Russ to show you that app.
Let's see the application. From the application homepage, I can click Create a New Game. I'm now presented with a link I can share with anyone who wants to join the game. And over on the right-hand side, I see a random color as my player name. I can share the link with other players. These players see a button to join the game. They can click Join Game, and we see the updated player list on the right. Returning back to the initial players screen, I click Start Game, and we now get presented trivia questions. I can click an answer on the list, and when the time runs out, I see the scores get updated on the right. The game gives everyone 10 questions, then shows us all a game over screen. Pause for a second and think about how you would architect an application like this. It will be interesting to see if we arrive at similar solutions. Feel free to share your ideas in the discussion forums. Let's talk about the architecture we use for this application. Think of this conversation like your first day on a new project. You may not be familiar with all the technology that is being used to build and host this application, but don't let that worry you. We will explain a lot of the technology as we progress. All of the code is supplied, and remember our focus here will be the processes and practices. Let's start with front end. The web application is a React front end served from an Amazon Simple Storage Service or S3 bucket. For this application, S3 is acting as our web server. We create several infrastructure resources to host the back end of the application. The front end communicates to an API Gateway hosted WebSockets API. API Gateway is a fully managed service where we will host the application's API. When you click Create a New Game, a WebSocket message is going from the browser to the WebSockets API. The backend compute resources are hosted in Lambda functions. Lambda is a serverless compute service where we can invoke our function code without having to provision or manage servers. We have 6 Lambda functions that are used to create, join, and start games, plus the logic to send questions to players, accept answers, and calculate the scores. Where will we be storing the data for our application? For this, we'll use an Amazon DynamoDB table. DynamoDB is a fully managed key value service and document database. When you create a new game or join a game, the application creates a new item in the Trivia Connections table. When you answer a question, the application is updating your item to remember the answer. We've started a game. We have rows in the Trivia Connections table for each connected player. Now we need to track the state of the running game. What questions are players up to? Pausing for players to answer. Moving to a state to update player scores. For this, we will use an AWS step function state machine. The state machine has 5 states. When a game is started, we start a state machine execution and pass input data that contains a list of questions. The state machine execution starts at the question state. This calls the question lambda function, which sends the current question to all the players. Next, we enter into a wait state while we allow players to submit their answers. Clicking an answer in the front end sends a WebSocket message to the API, which calls the answer lambda function. The lambda function updates the DynamoDB item with the player's answer. Our wait state completes, and we move to the scores state, where the calculate score function loops over the answers in the DynamoDB table, updates scores, and sends the scores to all the connected players. The state machine loops over the question, wait, and scores state until we run out of questions. Now we enter into the game over state, where the state machine execution completes. We're using AWS Services API Gateway, S3, Lambda, DynamoDB, and step functions. We supply all the code. If you're familiar with Python for backend or React for frontend, you are more than welcome to pull apart the code and see how everything works.
Hello, and welcome back. Usually, writing the code is the first thing we think about when doing software development. When you join a project, no matter if it is a brand new one or something running for a while, the goal is usually the same. Project managers want to add features to the code, and developers want to get those features in front of users in a quick, secure, and reliable way. With this goal in mind, there are usually 4 frequently asked questions, which are: where is the code? Where should I be committing updates? How often should I be committing and integrating? And when do changes get deployed for end users? These questions that are up to the team to come with conventions to answer. So the answers vary case by case depending on their needs. I say that ultimately because your requirements or your team's culture may be different. As part of this course, we will take one approach to answer them, which could give you ideas and best practices in order to figure out the answers in your own scenario. But remember, ultimately, it's up to you to answer them according to your needs. Allow me to take each question at a time, starting with the first one: where is the code? If you are working as a team and want to integrate your changes to code repository and have those changes available to other team members, AWS Code Commit is an AWS managed service that can be a good choice. Code Commit is a managed source control service that hosts private Git repositories, where all of the standard Git functionalities are supported. So if you are familiar with Git repositories, you will also be familiar with AWS Code Commit. Once the repository is created in AWS Code Commit, you can do a Git clone and get the code into your dev environment. From now on, you can securely interact with the repository hosted in Code Commit with the benefit of being able to use an AWS credential to authenticate and interact with the codebase in an encrypted way. Now, the second question: where should I be committing my code updates? When working as part of a team, eventually multiple people will work on features that may require changing the same files. The most common approach for this is to decide on a branching strategy. You can send those commits to a feature branch, When the changes are ready, you can integrate them by doing a merge with the main branch, where code can be evaluated and tested with automated tools. We will talk more about branching strategies later. But working with branches raises another question, which is, how often should I be committing and integrating? Well, there are some big advantages on deploying code regularly. When you push things to code commit, it gets stored in the AWS Cloud, which has good durability levels. And because it is durable, if your laptop gets damaged or lost in a taxi, your work is saved. Now the fourth question, when do changes get deployed and put in front of end users? As you can expect, the answer is also regularly. The more frequently we integrate code, the sooner bugs can be identified by the testers. When things get deployed to test environments more frequently, testers can quickly validate if the code is behaving according to what is expected. If a feature has to wait for weeks to be deployed, we could potentially deliver something that is outdated on day one. For many businesses, quickly deploying new features is very important, and having automation in the continuous integration pipeline is key for that to happen, as you will see in this course. Russ will now demonstrate how easy it is to start with AWS Code Commit.
Let's take a look at Code Commit in the console. I've navigated over to Code Commit. I can click Create Repository and give my new repository a name. Now I want to clone this empty repo on my laptop. How does authentication and access control work here? When authenticating my IAM user to Code Commit, I have three options. I can ask IAM to generate Git credentials for my IAM user. The generated credentials can be used like a username and password when you access your repository over Smart HTTPS Git protocol. IAM can also associate an SSH public key with your IAM user. When you authenticate using this, you use the private portion of your key when we're using Git SSH protocols. Lastly, Code Commit supports signed credentials for authentication. This is made very easy if you use the Code Commit remote helper. I have the remote helper installed on my laptop, so I can clone from a URL with a Code Commit prefix. That has cloned. This is using exactly the same identity that my AWS CLI is configured with. I can also build a URL that contains a region or a reference to a CLI profile using this format. For access control, at AWS we love our IAM policies. Code Commit enforces the access control of the policy attached to your IAM identity. This is how we could create a policy that allows an identity to push to a feature branch, but not to merge to a main branch, for example. I can interact with this repository exactly how I would always work with Git. Let's create a main branch. And now I want to create a README file. I can add this file to the Git index and create a commit. And finally, push the commit. Returning to the console and viewing the code again, we now see the code in the repository. If I click commits, I see the commit I created just a few seconds ago. I can now sleep a little bit better at night knowing that my code is being securely and durably stored using AWS infrastructure.
Hello, and welcome to your first exercise. It's time to get hands-on with our sample application. You will start the exercise by creating an AWS Cloud 9 environment for your dev environment. In the AWS Cloud 9 environment, you will download and unzip the source code you will be using in this course. The backend infrastructure will be deployed with the AWS SAM CLI, or AWS Serverless Application Model Command Line Interface. This creates all the resources for the application backend. which are an API gateway endpoint, the necessary Lambda functions, a DynamoDB table, and a step functions state machine. You will also deploy the front end, which is a React web application to an S3 bucket. So S3 will act as the web server. Once everything is all up and running, it is time to start using AWS Code Commit for adding source control capabilities to the application. It is your turn. Let us know if you experience any problems when doing this exercise. Please use the forums or discussion groups to get back to us.
We've spoken about collaborating between software engineers using source control, and I have my code committed to a source repository. So what comes next? Well, I'll most likely want to be sure my code is in a good state and it builds successfully. But what do we mean by a successful build? A build is going to take your source, compile it, retrieve dependency packages from a repository like Node Package Manager or NPM modules, or Java Maven artifact. The output of the build will be a packaged artifact ready for a deployment. Maybe this is a Linux RPM package, a Java WAR file, a Docker image, a Windows MSI installer, or many others. This is a package that can be passed onto your deployment process to roll out an update. A build will usually include automated testing to check the quality of the code, and unit tests to exercise the code and make sure it's doing what we expect it to. We'll talk more about testing later. Now, if any of these steps, such as retrieving dependencies, compiling, packaging, or testing, fail, we will have broken the build. This is something we want to catch as early as possible. If I commit something that is breaking to source control, I'm impacting others on the team. I can run a build in my local development environment, and when I do that, I can be pretty confident my code is in a good state. This is referred to as it works on my machine. To get some extra confidence, we can perform the build in a clean environment off my laptop, somewhere to automate the build and test of my code. But how often should we be checking that our code is successfully building? Well, why not do it on every commit? By doing this, we are now following continuous integration, or CI practices. In every dev team I've worked in, a broken build takes the highest priority. When the code is in a good state, everyone on the team is confident they can pull the code and start working on their new features. If the code isn't in a good state, we're blocking others from integrating their changes. The team has decided on AWS Code Build for our continuous integration. This is the place where we can compile source, run tests, and create deployment packages. Code Build is a service. Unlike managing build machines yourself, Code Build will scale up and run multiple builds instead of leaving your builds in a queue. With Code Build, you only pay for the service when you're using it. But how do we get our build processes into Code Build? There are two things that we need to configure: a build project and a build spec file. The build project contains information about your build, like the source, or location of your project, the environment, which will configure the project with a Docker image and specs of the build environment, and then Code Build will provision that and run your build. It will also include an IAM role. Remember, roles are how services authenticate to services. If your build talks to an AWS service, this is the identity that will be used. And logging. Seeing the log output of the build is absolutely needed to debug your builds. We can configure Code Build to write logs to Amazon CloudWatch logs and S3. So now that you have an understanding about what Code Build is, I'll pass it to Russ to give you more information about how to work with the service.
Now let's look at a build spec file for a very simple project written in Go. This isn't a comprehensive review of every setting in a build spec file. Let's just start with a simple build. I have a code commit repository that contains 3 files: buildspec.yaml, helloworld.go, and a readme file. Helloworld.go is very simple. I just have 2 print calls. I plan to print the source version used to build the application. Hold on to that thought. I'll come back to this. The build spec contains all the steps that we need to configure and run builds. I specify a version where version 0.2 is the current version of the build spec format. I configure some environment variables. I can also use values retrieved from AWS Systems Manager Parameter Store and AWS Secrets Manager. The environment variables I have set are telling the Go compiler to build a macOS 64-bit binary. Next, we have the 4 build phases. The install phase is where I would install any prerequisite tools I need for my build. I don't have anything here because the container image supplied by CodeBuild has everything I need. The build phase is where my application is getting built. I'm using a little bit of scripting to replace the placeholder that we just saw. CodeBuild provides several environment variables with information about the build. I'm replacing the placeholder with the environment variable that contains the source version. For us, this will be the git commit hash. In the report section, we can point CodeBuild to the output of unit tests and code coverage reports. Let's talk more about this when we come back to testing. Next, in the artifacts section, we are telling CodeBuild the output we want packaged and delivered to the artifacts S3 bucket. I want to grab the README and my newly built binary. And we have a setting to name the file hello app and the date.zip. CodeBuild does support some caching features. For builds that are CPU or network expensive, you can cache parts of your build in S3 or locally on the build server. We don't need this for a small project. Now we can go to the console and create a build project for this repository. I choose Create Build Project. I give the project a name. Several different source providers are supported. My project is in code commit, so I can select my code commit repository and branch. I configure my environment settings. I want the Ubuntu standard image. I could supply my own Docker image here. I would do this if the supplied images don't have the tools I want for my build. I also let the console create a role for me. My build will be writing to CloudWatch logs and sending artifacts to S3. This role will be used to authenticate requests to those services. My build spec is called buildspec.yaml. That's actually the default. My build does have an artifact, so I select an S3 bucket as the destination for my artifact. And I enable semantic versioning because I want to use the artifact name from the build spec. I also ask CodeBuild to zip the artifact for me. Logging is enabled, so I'll be able to see the output of my build in CloudWatch logs. I can go ahead and click Create Project. My project is created. I can start a build and tail the output logs. We see some information about the build here. The details are listed here. It has been submitted, it has been queued, and it's currently provisioning. I see the output from my build. Here are the test echo statements that I had in my install and pre-build phases, and my build was successful. Now I can navigate to the build details and find the artifact that was just created. Here it is here in S3. Let's copy that to my laptop where we can execute it. I have downloaded that. Let's unzip it. And there is the binary that was just built for me inside of CodeBuild. If I run the executable, I see the git commit hash that was used for this build because my build script substituted this into the code before it was built. Now we've seen CodeBuild complete a very simple compile and package for us. Can you think of a build in your organization that could use code build? Using a fully managed service like code build would free you from maintaining your own build servers and will scale as your requirements grow.
As a development team, we'll need to decide on a branching strategy. This will help us answer some questions every dev team needs to answer, like, what code are we running in production right now? That information can be very handy to have, so we know what is currently deployed or can reproduce a bug that is happening in production. Where should I put my commits for something that isn't ready to go to production? If I'm working on a feature, but it is going to take several weeks to complete, I don't want it to be included in any upcoming production deployments. Our solution to this question needs to scale to the multiple engineers working on multiple features. Conversely, where do I put my commits for something that needs to go to production immediately? We might need to roll out a feature to production in a fast production hotfix. If we don't have a way of doing this, we run the risk of having a broken product until the next production deploy, or not being able to react quickly to a security issue. We're going to walk through one way of approaching this, and we can see how this answers the questions we've raised. Again, this is something that you will decide on as a team and work on a process that works best for the team. Before we get too deep into our strategies here, let's take a second to remember what branches are in Git. A branch in Git is a pointer to a commit, and that's it. When we make commits in a branch, the pointer automatically moves forward. One more thing to remember, your commits form a DAG, or directed acyclic graph. A commit can also have multiple parents. In fact, this is exactly what a merge commit does. When you merge a feature branch into main, the merge commit has two parents. The main branch now points at this merge commit, and commits from both parents are now in the branch history. All right, I'm going to pass this off to Russ so he can get a bit deeper into these branching strategies.
Let's define some conventions for our branching strategy. We start with the main branch. We have commits on a main branch. Everything in main is in production or about to be deployed very soon. When a production deploy happens, we tag the commit that was deployed. This tag answers the question, what is the code that is running in production right now? I've talked to a product manager about an update to our application. Let's say we're going to improve the user registration process. Where do I put the commits for this? As a team, we've decided to create feature branches. We branch from the tip of main. I can continue committing to my feature branch. I might have continuous integration, testing the code quality, and continuous deployment, deploying to a staging environment where stakeholders can see the work in progress. I've finished on my feature. Now let's get this in front of customers. It's time to get my commits into the main branch ready for deployment. I want to give others on the team an opportunity to review and comment on the update, so I create a pull request in code commit. From my repository, I click Create Pull Request. The destination for my new feature is main, and the source is the feature branch. I'm being told what I have is mergeable. Let's remember, I'm not the only one on the team who is merging to main. While I was working on my feature branch, someone else may have made a change to the same file as me. This would create a merge conflict, and I would need to resolve the conflict by selecting from the overlapping changes. This hasn't happened here, so I'm free to enter a title and create the pull request. Everyone on the team can come into code commit and review the changes. On the activity and changes tabs, we can leave some comments and reply to other comments. Someone might suggest a neater way of coding what I'm doing. While the pull request is open, I'm free to keep pushing commits to the source branch, and the pull request will be updated. We've decided we are happy to go ahead with the pull request, so I can go ahead and merge. I have three options for the merge. Fast forward merge. This will only be enabled if the branches have not diverged. If there haven't been any commits on main since I branched, I can fast forward merge. A fast forward just moves the branch pointer along to include the source commits. Squash and merge combines all the commits from my source branch as a single commit added to the destination branch. Three-way merge. A merge commit is created with two parents in the destination branch. The commits from the source branch are now included in the destination branch. I'm going to pick squash and merge. This will also delete my source branch. The team has decided this is easier to read. The changes for this feature will appear as one commit. My work is now on the main branch. I'm ready to go to production. CI/CD will kick off, build, test, and deploy my code, and we are in production. We can go out for a celebratory takeaway. The process that we have described here also works for our hotfix requirements. Let's say we've found an issue in production. A library used in the application has a suspected security vulnerability. It doesn't seem fair. We didn't even cause the bug, but we want to work quickly to get a bug fix into production. Everyone else in the team can continue to work on their features. A hotfix branch is created from the main branch. I'm branching from the commit that is currently in production. We make the hotfix commits. We want to be sure we aren't introducing anything bad or have caused a regression. Automated tests are run on the hotfix build. We might deploy to a staging environment for testing to make sure we have fixed the issue and we haven't broken anything in the process. We merge back to main and CI/CD deploys our hotfix. This is a good example of how having a good DevOps practice and automation in place also is best for the security of our applications. Let's walk through one more scenario in the branching strategy. I have a big project. I've been working on a feature branch for several weeks. Other engineers have been working on features and bug fixes, so my branch is now from an old commit. I've diverged pretty far from main. I have a big merge in my future, and there is bound to be conflicts, and I don't know if my changes are going to be compatible with the current production code. To avoid this situation, I can bring the commits from main into my feature branch by merging or rebasing in my feature branch. If I git rebase main, first git is going to take my new commits that are not in main and save them in a temporary area. The feature branch is reset to main. This means the branch is now pointing to the same commit as the main branch. Then all the commits from the temporary area are replayed on the feature branch. A merge conflict could occur here and we would need to resolve the conflicts. There's a little word of warning here. The replayed commits are new commits. When you rebase, you are rewriting history. If the commits have already been pushed, then you will need to force the push to the feature branch. This will impact anyone who is working in the same feature branch. If you are the only one working on the branch, then this only impacts you. Again, this is going to be a team decision whether you're going to allow a force push. As an alternative, I can always git merge main in my feature branch. A merge commit will appear in my feature branch, and now the commits I was missing from the main branch will be included in my branch history. Okay, that was a lot of information about branching. Ultimately, you and the team you are working with will decide the best approach for you. Git is a very powerful tool for this. The more you work with Git, the more this will become natural. Let's take a look at completing the exercises in your own environment. The exercise instructions we have supplied include steps for getting everything working in the Cloud 9 environment. Developers like to personalize their IDE and dev environments. Maybe you'd like to attempt the exercises in your own local environment. It doesn't take too much modification to do this. This is a bit of an advanced approach. If the concepts in this course are new to you, you might want to follow the supplied instructions first. If you're pretty familiar with the AWS Serverless application model, Python, and the AWS CLI, then follow along. I'm going to go through the process of debugging the application in Visual Studio Code. The requirements are actually pretty simple. This is a completely new setup. All I have installed is Python 3, Node, Visual Studio Code, and the AWS CLI. This will be exactly the same on macOS and Linux. We start by downloading the exercise source we supplied in the first exercise. I can unzip this and move this to my documents folder. Now that that's done, I can open a command window and I'll install the AWS SAM CLI with pip3 install AWS SAM CLI. Next, I'm going to configure the AWS CLI with AWS configure. I need to configure the CLI with an AWS identity and a default region. I'm going to paste in an access key ID and secret access key. They belong to an AWS Identity and Access Management or IAM user that I want to use for authentication on my laptop. I need to supply a region, so I'm going to use US West 2. Now let's go to the Documents folder where Trivia app is unzipped. There is the template YAML that I can use to build and deploy the SAM application. This is the same commands that we used in exercise 1, SAM build and SAM deploy guided. I give the application a name, and I'm just going to go with the defaults for everything else. That has completed. We begin exercise 2 by installing the pip requirements for the backend code and the unit tests. We can do the same here. Now let's open the backend code in Visual Studio Code. I've opened up the code. This is a Python application, and I already have the Python extensions installed here for Visual Studio Code. There's one more thing I need to set up here. In exercise 2, the integration test expects an environment variable. So let's add a .env file, and we'll add the environment variable. There we go. I've set AWS stack name, AWS SAM stack name equal to Trivia app. That's what our integration test expects. I need to tell the IDE about the tests that we have. So I can open the command palette here and I search for Python configure tests. There it is there. We are using the PyTest framework, and my tests are in the tests folder. That has added a configuration to our project over here in settings.json, and we can see PyTest is enabled. Now I can open tests from the activity bar here, and the IDE has discovered all the unit tests and integration tests in my project. Let's go into the test here that is calculating the scores. I can set a breakpoint over here and click the little debug icon. And now I can step over code, I can step into code. In the testing activity on the left, back here, I can select all unit tests and hit play. And we see that they all pass. That's just one way of getting the project to run in a local environment. I'm sure developers in the audience all have their favorite IDEs and environments for testing. Please come over to the forums and share with us how you are setting up your own environments.
Next, we can talk about testing and how testing fits into a continuous integration and continuous delivery pipeline. By performing testing at different stages of our development cycle, we are creating a measure of quality. When you write code, that code is going to do exactly what you tell it to do. The important question is, are we telling it to do the right thing? For example, I've added a purchasing feature to our application. The code now calculates tax for every purchase. The important question here is, are we calculating tax correctly? There can be many variables that go into this calculation. How much was the purchase? Where in the world did the purchase originate? Taking this example, how have you tested application features like this in the past? When I first started coding, I would make the changes locally, click around in a build in my local environment. I would also roll the updated application out to a staging environment for stakeholders to perform some testing. Manual testing like this comes with some serious disadvantages. Where do we document the tests that were performed? Are those documents kept up to date? And if we discover an issue with tax calculation in production that I thought we tested, that might leave us wondering, how did it get through? Take a moment to think how expensive it would be to fix an issue that made it all the way into production. Consider the scenario where we have been miscalculating tax for a few weeks. Now we need to issue refunds or charge extra, amend tax documentation, and take resources away from other projects for the cleanup and fix. Pretty expensive. But let's say we fix it, and we're now happy with this new purchasing feature. We can roll it out and stop testing it now, right? Well, not quite. We're going to keep adding features to our application, so we want to be sure we aren't breaking any existing features. We need to regression test. This is where we go back through the application test to be sure all the existing functionality hasn't been broken with a new change. It's easy to say, I'm changing X, so there is no way that will break Y. Those words could come back to haunt you if you aren't testing for regressions. If we were doing this manually, we would need to maintain documentation of scripts for testers to run through for every regression test. This becomes pretty resource intensive and slows us down from getting a feature in front of users. So how can we apply some automation here? One thing we can do is use a testing framework for the application language to start writing some automated tests. For Python, you might be familiar with PyUnit or the unit test package, which is part of the standard library. Java programmers might be using JUnit or similar. .NET developers will be using xunit.net. Each of these frameworks provides the same basic functionality, a framework to write and run your test cases in code. The popular frameworks all come with some IDE integration, so running and debugging tests can be as easy as clicking a button in your IDE. We'll be looking at two different types of testing: integration testing and unit testing. An integration test tests multiple modules working together. Completing a game in the sample trivia game app in a production-like environment tests everything in the application. Is a new game getting written to the database? Are scores being calculated correctly? Are questions getting sent to players? A unit test is testing functionality in isolation. That is, are we calculating our scores correctly? This might be a bit different to how you're coding now, but this is a very good thing. It's a good goal to write your code in a way that a piece of functionality can be tested in isolation. Here, we can also take advantage of mocking frameworks. The routine that needs to calculate scores needs to read the most recent answer from the database. We also need to update the score in the database and send updated scores to all the players connected to the game. If I wanted to isolate the calculate scores from the external systems, I can use a library to mock the conversations from these external systems. When this is mocked, I can simulate different responses from the external systems for different scenarios. If I wanted to be sure some error handling is working, I can mock a simulated failure from the database. Russ will be going into more detail here and look at the unit test included in the sample. This course, again, focuses more on DevOps practices. So if you aren't familiar with Python coding, that's perfectly fine. What is most important here are the concept we have discussed: integration tests for testing multiple modules working together, unit tests for testing a module in isolation, and using mocking to simulate modules outside of the module under test. All right, take it away, Russ.
Starting with the scores event variable, we have an object that looks a lot like the event that is going to get passed to the calculate scores Lambda function. The event contains a game ID, a single question and answer, and our position within the questions, currently 0. The test down here, test trivia calculate scores correct, begins using the mock object to patch two variables inside the application. Table is the DynamoDB client. Management is an API gateway API used to handle the WebSocket communications. The patched DynamoDB client is being set up to return some simulated game information. Then we enter into the implementation of trivia calculate scores over here. We grab some information from the event parameter. In the production application, this will be called by step functions. Now we query the DynamoDB table for the connections that belong to this game, but we aren't talking to Dynamo. This is a unit test, so we are getting the mocked response back from the DynamoDB object. We just want to focus on the implementation of one thing. We iterate over the connected players here and compare the answer from the Dynamo table to the correct answer. If it's good, we increment the score and call the Dynamo client to update the score here. We have patched the Dynamo client with a mock, so our tests will assert that this call happened and pass the correct parameters, in this case the score that we expect. We build a list of connection IDs, players, and scores, and pass this to send broadcast to update the connected players with the score. When we return to the unit test, you'll see there's an assert checking for the calls that send broadcast makes. Next, there's some logic to update the data structure that tracks the current question position, and a test to see if we need to send a game over message. Back inside the unit test, we have two asserts, checking to see if the DynamoDB client was called with the expected parameters, and again here for the API gateway management client. That was a very quick introduction to the types of automated testing we have added to our workflow. Our goals with all testing are the same. We want an indication on the code quality that starts at the beginning of the project and captures the knowledge and edge cases that we are testing in the application. Once this is automated, we can easily run tests at any time.
It's time for exercise 2. In this exercise, you will return to the AWS Cloud 9 instance and run the local build for the project. The local build contains linting, which is a static analysis of the code, and unit tests. Imagine the development team of this project would use the local build script to verify their code before doing a commit. Next, you will run an integration test. The integration test finds the API Gateway WebSocket endpoint and simulates a player completing a game. This is the type of test we are using to verify a deployment to a staging environment. But as always, there is plenty of room for your own experimentation. So think about what could be other implementations for validating that. Once you are happy with the tests, if the code looks good, you will add a simple feature to the application by making changes to the code. For user experience purposes, project managers realized that players are happier with big scores. So they asked if the game can give 20 points for each correct answer instead of the original 10 points. Next, you will make changes to the code and run the local build. The unit tests will fail. This is expected because the functionality of scoring was changed. And the initial test is checking scores as being incremented by 10. When you fix up the unit tests and rerun the build, you will see success, which is always a good indicator.
We have our set of tests running in our local environment. As a new developer coming on board to our project, you can clone the source code and run tests. That way, you're confident you have the code in a good state. As you work on the code, you can keep adding to the tests and running existing tests to be sure that they aren't causing any regression. This is really just a test for it works on my machine. For example, I might forget to include a library in the source, but the library is present in my environment, so the build passes. But another developer clones the source and encounters errors because the library isn't present. Breaking the build like this can have a pretty significant impact on your team productivity while we trace through errors that are happening here, but not happening there. So we need to build and test in a clean environment off our laptops. We've already seen AWS Code Build for building and packaging an application and running our tests. Code Build will provision a clean and consistent environment to install our test prerequisites, tools, and run tests. Here's Russ to show you a bit more about this.
Let's compare the local build script and the build spec used to run the same steps inside Code Build. The local build first runs pylint with a single parameter. That's the location of the Lambda function code. Pylint is a static analyzer or linter for Python code. This tests that we are writing code to the same standardized conventions. Things like variable naming and unused code will be detected here. Having a team coding convention will make the code less individualized. If we are all sticking to the same convention, code will be more predictable and easier to read for others on the team. Next, the code runs PyTest. The parameters for PyTest give the directory location of the unit tests. Then the type of report we want. In this case, a HTML report. The last two parameters include code coverage in the tests. Code coverage will give us a report of which lines of code are being exercised by the tests. If I'm adding some conditional code to the application, this will show that the condition isn't being tested if the code isn't being exercised. Now let's look at how this would move to a build spec file. This is going to look very similar to the steps you did manually in the unit testing exercise. In the install phase, we install two packages. We need to test the code. This is exactly what we did manually in our local environments. In the build phase, just like the local build, we have pylint and pytest. This is very similar to the local build, but we're passing different parameters for the unit tests and the coverage report. Previously, we were building a HTML report for a human to read. This time we want an XML report. The consumer of this report is going to be Code Build. Here in the report section, we have settings that use the XML unit test report and the coverage report. Code Build supports several test file formats, for example, Cucumber, JUnit, and Unit. With this, we'll be able to see the results of our tests in the Code Build console. Now is a good time to talk about debugging and troubleshooting anything we are doing inside of Code Build. We are looking at a failed build. The first step of any debugging will be checking the logs. From inside the console, we've seen that we can see the output of a build. The output here is going to be the number one source of help when debugging. Okay, I've seen the output from my build. I think I have a fix. I could just commit the fix, but I want to get confident the fix will work before I push anything to the code repository. Code Build builds are run with a Docker image you configure. The Docker files used to create Code Build images are made available in a GitHub repository on your screen. I'll include a link to this in the course readings. You can build the same image code build is using to run your builds, and then launch this image locally to test your build. Let's see what this looks like. I clone the Git repository. I'm interested in the Ubuntu standard 5 image that is being used in the exercises. I can build the image on my laptop. There is a lot going into that image, but I already have it built on my laptop, so it completes pretty quickly. Let's launch a bash shell inside of the container. I want to use my source inside the container, so I'll use a -v mount for my code. Inside the container, I have lots of build tools available like Java, Python, Go, and Node on here. I can change over to the app directory where I have my code mounted. From here, I can test my build commands like go build. I see the same error I was seeing in the code build console. I can make a test fix in the container before I push anything to Git. Testing builds in a local Docker container makes it easy to test our builds in the same consistent environment that will be used by code build. What steps would you take if you still cannot reproduce your issue locally? Now I would be thinking about using a session manager feature to connect to a running build. Code build supports pausing the build and using session manager to connect to the build container. To do this, there are 3 things I need in my build. To pause the build, I add a code build breakpoint command in the build phase of my build spec file. I need to make sure the role associated with my build has permissions to create and open channels in AWS Systems Manager. Lastly, I need to launch the build with session connections enabled. Back inside the code build console, I can start build with overrides, advanced build overrides, and under environment, I enable session connection. The build will be submitted, queued, and provisioned. And once we're in the build phase, we'll pause the build and we'll be able to connect to it. I see a message telling me the build has paused, and I can connect to it with using Session Manager. Now in my browser, I'm inside a shell in the container running my build. I'm going to launch a bash shell. If I look at the environment variables, I see the environment variables that was set by code build. If I list the files in this directory, I see my code. I can use the commands that I would use in my build. I can now debug my build interactively. When I'm finished with my debugging, I can code build, resume, and the build will continue. Let's go over the 3 methods we use to debug a build. We have logged output from builds. We can run the same containers code build users in a local environment. And finally, we can pause the running build and use Session Manager to connect to the build.
Hello all, it's time for our next exercise. Currently, we have a build in our local environment. Now it's time to run exactly the same build inside of code build. We'll create a build spec file that contains the same tests we are performing in the local build, linting with pylints and unit tests with pytest. We'll then commit the build spec file to the code commit repository. With this in place, we can configure a code build project. The code build project needs to know where the source code is, in this case your code commit repository, and the environment where your build will run. For this, we will use the Ubuntu image managed by code build. We won't configure an artifact for this project, as we are just running tests. We'll simply start a build and see the output from build logging as it happens. When the build completes, we can see the reports that are generated from the output for unit test and code coverage. So let's get started with exercise 3. At this point, the application is source controlled, and I have automated tests I can run to make sure my code is in a good state. Pretty cool. But I want to run these tests every single time I commit code. This way, I receive immediate feedback that the code I've committed still works. So if I wanted to automate these tests to run on every commit, how do I do it? Ideally, I need some kind of workflow or orchestrator that will do this for me, that will control the 2 different steps and decide when to go from the first step to the second step. Now, there's quite a few services on the market that were created to orchestrate steps of a pipeline, but the one we'll be talking about today is AWS Code Pipeline. Code Pipeline will let us establish a consistent set of steps that every code commit will run through. In our case, once we commit our code to a repository, we'll kick off another step that will run tests. So we'll have a 2-step pipeline. First step is commit to repository. Second step, run automated tests. The beauty of this is that once you set up your pipeline to include both of these steps, the pipeline is configured to detect any new commits to the repository. And then it will restart the pipeline whenever those changes are detected. That means that all I have to do is push code to my repository, and that's it. Code Pipeline will recognize there was a change and kick off the test phase, running my tests of choice. Code Pipeline doesn't do all of this alone, though. Like I said, it's an orchestrator, and it teams up with other services like Code Commit and Code Build. It also integrates with third-party tools, so while we might use Code Commit for source control, you can also use GitHub in its place. Or if you'd like to use Jenkins to build your code on every commit, you can do that as well. So if you take the example of an orchestra, Code Pipeline is the conductor, whereas all the services it integrates with, like Code Commit, Code Build, GitHub, Jenkins, they're the musicians. They're doing the work, and Code Pipeline is instructing them on how to do that work. As an example, let's see how Code Commit, Code Build, and Code Pipeline all work together. In Code Pipeline, each workflow you create is called a pipeline. Each pipeline is made up of a series of stages. This is just a logical container that describes a phase in your pipeline, such as source, build, test, and deploy. So for our pipeline, we'll have 2 stages, source and test. For every stage, you have to decide what actions take place at that stage. This is where you can choose which service will be performing the action. For example, in my source stage, I might have a source action that uses AWS Code Commit. I'll then specify the specifics of what repository I want Code Pipeline to monitor and how I want it to monitor it for those changes. I also have a stage called test, with an action called test that uses Code Build. This will enable Code Pipeline to kick off the appropriate build project when it receives a new commit in the repository. This build project will point to the correct build spec that will specify my tests. And that's really all I'll need for this very simple pipeline. When my pipeline runs, I can view my progress in real time. I can also see the status of each stage, whether it has succeeded or not. And if it's failed for whatever reason, I can go ahead and look at the action details, or I can even retry that action, or even kickstart the pipeline manually if needed. Now, if I choose to, I can make this pipeline more complex using other Code Pipeline features. For example, maybe after my test stage, I'll create a deploy stage like what I just showed. But before we deploy, I want to manually approve the output of my tests. In Code Pipeline, I can do this by creating an approval action, but to my testing stage that will require me to manually approve or reject the action before it moves on to another stage. Using an orchestrator like Code Pipeline is important to DevOps because it can increase the speed and quality of your updates. For example, with our pipeline, now every commit gets tested without any manual intervention. And when we automate build and test for every commit, that enables us to achieve true continuous integration. That's all for this time, and I'll see you soon.
Hello! Welcome back. It's time for you to build your own continuous integration pipeline. In the previous exercise, you created a code build project to run tests. But with everything you learned so far, you determined that the right thing to do is to run tests for every code push. In this exercise, you will create a pipeline with a source action, which in this case will be code commit, followed by the tests powered by code build. Starting with the commit and the push to the dev environment, you will create a feature branch in your AWS Code Commit repository. This branch will be called Feature Bonus Scores. Then you will edit the code to implement a bonus score feature. The change will be made in the new branch that you created, and after that, your application will now have a feature that will have bonus points for the questions in the Trivia app. When the code is ready to go, you will create a pull request to the Code Commit repository. That pull request will allow other team members to have the chance to comment on that change before it gets merged. Once the pull request is approved, the merge will get created. Alright, now it is your turn to get hands-on and try it out on the application's first pull request. If this is the last exercise you are doing as part of this course, don't forget to delete all the lab resources as indicated on the very last instruction of the exercise. You just completed a pipeline in the previous exercise, meaning that you are now meeting the continuous integration requirements. It is nice to see the pushes to the main branch result in starting a pipeline that runs tests. From now on, we are getting quick feedback on our code with every commit. Let's think about how could we extend this to continuous delivery. In a previous exercise, you manually used the AWS SAM CLI to deploy the backend, npm to install the React application and dependencies, and the AWS CLI to copy the web app code to an S3 bucket. The good thing is that you can do all of this automatically as part of the pipeline with the same tools you were already familiar with. Russ is going to show you now.
Let's start by looking at the new deploy spec YAML. In the install phase, we use the pyenv utility to install the version of Python that we want. In the build phase, we're running some very similar commands to the commands that we used in the exercises. SAM build prepares the backend resources. SAM deploy deploys the AWS SAM application. We are passing an extra parameter here, no fail on empty change set, because we don't want a no changes deployment to break the build. Then we get into the npm install. This is pulling down the node dependencies for the application. npm run build prepares the production HTML. AWS S3 sync delivers the React application to our S3 bucket. This is very similar to the steps we had in the exercises. We're just handing this over to code build. I can commit and push this. So now I have the new deploy build spec in the code commit repository. Next, we create a code build project that will run this for us. Back in the console, I go to code build and I choose create project. I'm going to call this project Trivia Deploy. For the source, I'm going to choose code commit, the repository name, and the branch is main. For the environment, I'm going to use the Ubuntu standard image. I have already created a role for this project. Remember, the project is going to deploy Lambda functions, a Dynamo table, API gateway, and step functions. We need a role that has permissions to create and update these resources. The build spec file is the file that we just created. There are no artifacts for this project. I can click Create Build Project. Now to add this to our pipeline. From the console, I can go to the trivia pipeline. I want to edit the pipeline and add a stage. Let's call this stage deploy. Inside that stage, we create a single action. I'm going to call that deploy. Also, the action provider is code build. There are more ways to deploy your application. For what we are doing with a serverless application, code build works for us. If my application were being deployed to Elastic Compute Cloud or Amazon EC2, I would consider using Codedeploy. My input artifact is taken from the source artifact, which is the output of the source action. The project is trivia deploy. I can leave everything else and choose done. I can save my pipeline. Save. Let's see this run our pipeline by adding a commit to the application back in Cloud9. I'm going to make an obvious change to the application JavaScript. Instead of saying get started down here, let's change this to let's get started, like that. I need to commit my change and push that to the repo. Adding the commit is going to initiate a build on the pipeline. Let's take a look at code pipeline. Already it has detected a change in the source. Let's give the pipeline some time to complete, and we'll come back when the deploy action has completed. The brand new deploy action has completed. I can click through to the details here, and I see the output logs from the deployment. At the start here, it is installing Python. The AWS SAMS CLI is running the deploy for the backend changes here. I can see there was no changes to deploy down here. That's because we didn't make any changes to the backend. The change was just to the front end code. That has completed. One of the last things that we'll see it do is here when we S3 sync to deliver everything to the S3 bucket. So we can return to the application, refresh, and there we see the change automatically deployed for us. We've built a continuous deployment pipeline. We have added to the source control all the knowledge that we need for a consistent, repeatable deployment. In a production environment, maybe we would add a few more controls in place to make sure we are very confident with the deploy. But in dev or staging, we can work fast. Testers and stakeholders can always see the build that is up to date with the latest code branch.
Hello, we've made it to the end of the course. Thank you for coming along on the journey. The most important thing we covered here is the philosophy and practice of DevOps automation. Hopefully, we have equipped you with the knowledge you need to make some decisions about the philosophy and practice in your own organizations. Investing your time in automation results in better work and better software for everyone involved. DevOps itself isn't really intended to be prescriptive. You will make the decision of where to best invest in process improvement and the tools that are right for your team. Remember, DevOps teaches us to move away from siloed teams. Maybe your role has traditionally never had to think about deployment or security. Moving out of these silos can only expose you to a more varied and fulfilling role, developing new skills and sharing your skills with others. I hope to see you in the future courses where we will focus on applying these DevOps practices to the unending steps of release, deploy, operation, and monitoring of your software. Stay tuned for the other DevOps courses as part of this series. On behalf of Alana and Russ, thank you for watching our content so far. See you soon.
Hi there, and welcome to the second course in the AWS DevOps series, Release and Deploy. When you hear that your code is getting deployed, how does that usually make you feel? Anxious? Sweaty? Excited? Maybe all of the above? Well, these nerves might be partially caused by the way your organization is doing deployments. It may be a very brittle process, prone to errors, and you might always feel certain that something will go wrong. In this course, we talk about how to improve the deployment process with DevOps methodology, and also some tools that might make deployments easier, such as Infrastructure as Code, or IAC, and AWS Codedeploy. But to do this, it's important that you have some background experience or knowledge on source control and continuous integration. We discussed this largely in the previous course, Code, Build, Tests. In that course, we discussed continuous integration, and we left off with a scenario that looks a little like this. You've written code and tests for the critical parts of your application, and you have somewhere to put this code, in this case, a code commit repository, as well as a strong branching strategy. You also have a CI service, in this case code build, that monitors the repository and runs tests automatically for every commit that is pushed. Also, you learned how to deploy a serverless application. In summary, you have a pipeline that has built and tested your code, and you've deployed from your local environment manually. We'll take this scenario a step further in this course. We'll orchestrate automatic deployments. Since we focused on a serverless app last time, we'll be mixing it up and deploying to Amazon Elastic Compute Cloud, or Amazon EC2 instances instead. So you'll be familiar with both compute platforms. By the end of the course, you'll be able to answer the question, how do we actually get our features out to production in an automated and safe way? To help me out, we have Russ Sayers from the previous course here to break down some of the deployment-related topics, and also my friend Raf Lopez, who will guide us through Infrastructure as Code. Raf will also be leading the third course in the series. So stay tuned for more release and deploy content. From all of us here at AWS, we hope you learned something, and most of all, we hope you have fun. Thanks, and see you soon. Welcome to week 1 of the course. Let's imagine that there are multiple people working on an application hosted on Amazon Elastic Compute Cloud, or Amazon EC2. They're constantly creating new features and fixing bugs, but they're manually deploying these features to get them in front of testers and customers. They're also getting these features out pretty slowly on a 2-month cycle. That means if they miss the release cycle, their code is delayed for another 2 months. They also know that manual deployment can be very error-prone. In fact, the team experienced this when they accidentally shipped an incorrect version of software. Bottom line is, it's easy to make mistakes when humans are overseeing large deployments. Not ideal. Instead, the team wants to be more agile, have a more reliable process, and automate when possible to prevent some of those human errors. And they already do this to an extent. In fact, they practice continuous integration and automate build and test to ensure that each commit to the main branch doesn't break their application. But they want to take it a step further and extend their pipeline to include not only continuous integration, but also continuous delivery. That means on top of automating the build and testing, they would also be automating the release process. With continuous delivery, every code change is built, tested, and then pushed to a non-production testing or staging environment. And from there, a manual approval is required to push that code to production. If they wanted no manual steps in their pipeline, they could take this a step further with continuous deployment. That's right, not continuous delivery. 2 different things. Continuous delivery requires manual approval to release to production. Continuous deployment automates that too. No explicit approval required. And in theory, continuous delivery or continuous deployment eases a lot of their problems, like an increase in speed. The team of engineers will be able to release far more often now because it's all automated. We're not relying as extensively on people. This also reduces labor hours, gives them a faster time to market, and ideally, they're releasing safely and gradually. So now we know what the team wants: continuous integration and continuous delivery, or CI/CD. So how do we get them there? What tools do we use? That's what week 1 is all about. Let's get started. Hello, and welcome back. It's time to talk about deploying our application. How often do you think a deployment should be happening? Quarterly, weekly, daily, multiple times a day? The answer to this is going to be different for everyone. One thing I think we can agree on is that a deployment shouldn't be a scary event. If we automate our deployments and are doing this with some regular cadence, deployment becomes an event that we have more and more confidence in. Now, deployment doesn't just go to production. We have multiple stages like dev, staging, testing, and multiple branches of development getting deployed. We can easily see this won't scale to any manual process. We are all going to have different requirements for deployments, and there are many ways to deploy our applications, each with their own advantages and disadvantages. Here's Russ to run you through some different deployment scenarios, starting with something very simple.
Let's go over some deployment options. The simplest deployment is just 3 steps. First, we terminate the existing application on each of the hosts where it's running. Next, we deploy a new version to the same hosts. The disadvantage to this approach would be the downtime between terminating the application and the deployment. The advantage would be how simple this approach is. You could have an application where this isn't an issue. Maybe the users of your application are only online during business hours for a single time zone. Bringing the application down at 10 p.m. would have minimal impact. Nice and easy. How would you roll back this simple deployment? It's 10 p.m., we've rolled out the new version. Some testing has been performed on the new version of the application and we've encountered an error. Not great. We can roll back by returning to the original version of the application. This is effectively the same steps as the initial deployment using the previous version of the application. You might have kept a copy of the previous version on the hosts, so we can terminate our new version and reinstate the old version. Remember, it's important to have a plan for rollback. Deployments may not go according to plan. We don't want to come up with the rollback plan in the middle of the deployment, especially not at the 10 p.m. outage window. What if zero downtime is a requirement for our deployment? Let's take an application that has been deployed to 4 hosts behind a load balancer. We can look at metrics like CPU usage and see that we have enough resources to remove 1 or 2 hosts from the load balancer during deployment. So I deregister 1 host from my load balancer. The goal here is to stop the traffic going to the application on the host. My application continues to work happily on the remaining hosts while I deploy to the deregistered host. I can do exactly the same steps on the deregistered host as my replacement deployment. Stop the application, install the new version, start the application, and now register with the load balancer. My deployment looks good. I can move on to the remaining hosts. Let's call this a ramped deployment, as we're slowly ramping up the hosts that serve the new version of the application. We have zero downtime. It's a little bit more complex than the replacement deployment as we need to coordinate with the load balancer. But it's the same steps that we're using for our replacement deployment, so it's not that much more complex. When the first host is serving version 2 of the application, we can start gathering metrics on how the application is performing. Are we seeing fatal exceptions coming from the application? There is a variation on this type of deployment called a canary deployment, where we stop at a small number of hosts and gather the results running version 2 with a percentage of production traffic. We might discover an issue with the deployment. We don't go ahead with the deployment on our remaining hosts. Rollback will be similar to our replacement deployment. We need to reinstate the previous version of the application on the hosts running version 2. This is going to take time and potentially impact our users while we are removing hosts to redeploy the previous version of the application. We can roll back, it'll just take time. The deployment options we have covered reuse the application hosts. They are a type of in-place deployment, but we are working in the cloud where we don't really need to have long-lived hosts. We can turn on instances and have them ready super quick. Let's take advantage of this with a blue-green deployment. With a blue-green deployment, we turn on a new environment that can handle production load. We refer to this as the green environment. The existing production environment is called the blue environment. We deploy the application to the green hosts. No production traffic is going to the green hosts just yet. This gives us a chance to perform some acceptance tests or smoke tests on the newly deployed version 2. We decide we're happy with the deployment. We can start sending production traffic to the green hosts. This can be done with a DNS switch or registering and deregistering hosts from a load balancer. You control the batch size of hosts in the green environment that start receiving production traffic. Maybe we want to add traffic to hosts 1 at a time or 2 at a time, or all of the hosts at once. Once we have deployed, what do we do with the blue hosts that still have version 1 of the application? Now is a good time to talk about rollback. With the blue-green deployment, we can roll back very quickly by sending traffic back to the blue hosts. We can keep those hosts available until we are confident they won't be needed for a rollback. Before we wrap up, let's go over some considerations for your deployments. Sometimes your application may not lend itself to all forms of deployment. Blue-green deployments mean newly provisioned hosts. What if your application needs to store state or data on the same host as the application? This isn't a good practice. Ideally, all applications should store state external to the hosts, but some of us are working with legacy applications that may not lend themselves to this type of deployment. In this case, we would need to look at in-place deployment. Zero downtime sounds great and something we want for all of our applications. Keep in mind during a zero downtime deployment, we're going to have version 1 and 2 running in parallel. Maybe just for a short time, but we need to consider this. We need to make sure changes remain compatible with other systems we're talking to, like a database or an API. So good luck with all of your future deployments.
Hello, and welcome back. Our development team is getting to the end of a sprint. Some exciting new features are coming to the application. Now we have to start thinking about how we are going to deploy the application to get those features in front of our customers. We've spoken about different deployment strategies for the application, and the team has decided they want to use the service AWS Codedeploy to take our build artifact, getting built by CodeBuild, and deploy this to our application instances. Codedeploy supports deploys to EC2 instances, on-premises physical servers, AWS Lambda, and Amazon ECS. Our application is hosted on EC2 instances. To get started with Codedeploy, we will need to create an application and 1 or more deployment groups. Let's go through what each of these means. An application defines the compute platform we're deploying to. This is a choice of the supported platforms, EC2/on-premises, Lambda, and ECS. I'm deploying to EC2 instances, so I would use the EC2/on-premises compute platform. An application can have multiple deployment groups. For an EC2 server deployment, the deployment group needs to know information about several things, like the IAM role that Codedeploy will use to authenticate to other services, the deployment style, whether it's in place or blue-green. In place will replace the application on our instances, and blue-green will create new green instances to deploy the application. Then we have to specify the deployment configuration. For an EC2 deploy, this controls the number or percentage of healthy hosts we want available during a deployment. We also have to specify how to find our instances by tags, autoscaling group, or even on-premises tagged instances. For a blue-green deploy, we can configure an autoscaling group that Codedeploy will copy to provision the green instances. Specifically, for a blue-green deploy, you have control over when to route the traffic to the green instances. It can be automatic, or the deploy can wait for you to continue the deployment when you're happy to go ahead. You also control how long the original, or blue instances, are kept after a successful deploy. Optionally, you can also select a load balancer, so Codedeploy knows where to register and deregister instances during the deployment. We can also associate CloudWatch alarms. A deployment can be halted if any of the configured CloudWatch alarms go into an alarm state. And finally, auto rollback. If we want to automatically roll back on a deployment failure. A rollback is just going to redeploy the last successful deployment for you. With an application and deployment group in place, I'm ready to create a deployment. A deployment for EC2 just needs to know my application, the deployment group, and the revision of my application. The revision is the artifact we want to deploy. This will contain all the files and instructions run on each host during the deployment. These instructions are configured in an AppSpec file. We will go into a lot more detail on the AppSpec file and the hooks you have to run your commands during a deployment later. How exactly are these commands run on my instances, though? Well, this is the job of the Codedeploy agent. We need to have the agent installed and running on all of the instances where we plan to deploy the application. The link on your screen goes to more details on how to install the Codedeploy agent. I'll also include this link in the course readings. An EC2 deployment from Codedeploy can pick up this artifact from S3 or from a GitHub commit. When Codedeploy is added as part of an AWS code pipeline action, the revision can be picked up from the output of another code pipeline action. For example, the artifact created from a pipeline build phase. Here's Russ to show you more about this in the console.
Let's jump into the console and see how all of this works with a simple deployment. From inside the console, I can create a Codedeploy application. This is just the application name and the compute platform. We are deploying to EC2 instances. Now I create the deployment group. We give it a name. I choose the service role. This is the role it will use to authenticate to other AWS services. Our deployment type. Let's start simple with an in-place deployment. Codedeploy needs to know which instances that we want to deploy to, so I'm going to give it an EC2 instance name tag. We are given an option to install the Codedeploy agent on our instances. I don't need to do this because I already have this set up. For deployment settings, let's do all at once. This will mean an outage for our application, but I'm deploying to a dev environment and I want to deploy as fast as I can. I have a load balancer set up, so I can tell Codedeploy about my load balancer target group here. I now have an application and a deployment group set up. I have everything I need to create a deployment. This will send an application revision to the deployment group we just created. Let me show you what a simple revision looks like. I have a revision open in an editor here. The revision contains a simple AppSpec file, the scripts I have specified to run with each of the hooks, and a single source file I want to deploy on my instances. Back in the code build console, from my deployment group, I can choose Create Deployment. All I need to supply here is the location of my revision. I have zipped up the contents of my revision and copied this to an S3 bucket. I can enter the S3 location of my revision. I can override some deployment group settings here. I'll just keep this set to all at once and then choose Create Deployment. My deploy completed in about a minute and a half. If I choose View Events here for one of my instances, I see the sequence of events that happen during the deploy. Block traffic is the event that deregistered the instance from the load balancer. Allow traffic is the event that registered it back. Application stop and before install are the two steps where my revision scripts ran. These events all ran simultaneously on my instances. We're using the all-at-a-time deployment configuration for this deployment. If we were to use one at a time for the deployment configuration, one instance would be selected, all of the events we see here would complete, only then would Codedeploy move to the next instance. That was a pretty quick introduction to Codedeploy. We have spoken about Codedeploy's application, deployment group, deployments, and revisions. We saw the deployment run against my 5 instances, where the Codedeploy agent followed the instructions in my app spec file to get my applications installed.
We walked you through the core components of AWS Codedeploy in a previous video, but it's time to get a bit deeper into one of them, the app spec file. It's important to have a good understanding of this file as Codedeploy relies on it heavily. This app spec is a YAML or JSON file that contains locations for all the installation files, scripts, and when to initiate specific actions. This is where you get to control how your revision deployments are actually managed and how you determine a deployment was successful. Let's take a look at the app spec file that we'll be using later in the labs. Note that this is an app spec file that's used for Amazon EC2-based deployments. If you're looking for more information on serverless app spec files, check out the reading following this video. All right, so this app spec file is a YAML file, and it's pretty simplistic in nature. A lot of app spec files can get pretty complicated, but I'll talk you through all your options and why we chose the ones we did for this specific file. So this file is broken out into 4 sections: version, OS, files, and hooks. We could additionally have another section called the permission section, which we'll talk about a bit later. Out of all the sections, the version and the OS are the simplest parts. The version refers to the Codedeploy app spec version and not the version of your specific application or deployment. And currently, the only accepted value is 0.0. The OS section, as you may have already guessed, stands for operating system, and it only accepts 2 possible values, Linux or Windows. The EC2 instance you'll be working with in the lab is a Linux box, so we chose Linux. Now, all the rest of the sections are optional. That means the hooks, files, and the permission sections are not required. So let's talk about why. The files section is only necessary if you're going to be copying files to your instance during the deployment. It has a source and destination subsection. The source subsection identifies a file or directory from your revision to copy. The destination identifies the location on this instance of where the file or directory should be copied. So for our app spec file, we want the index.html file to be copied to the var/www/html directory on our instance. The next section we are going to review is the hooks section. The hooks direct the Codedeploy agent as to what it needs to do and in what sequence. Some of the main hooks that you can use are before install, after install, application start, application stop, and validate service. Each of these is used to run scripts that you specify when the hook is initiated. You'll notice that each of these hooks is structured the same way. You specify the location of the script, the timeout you want to allow for it to run, and if you're running a Linux deployment, run as refers to the level at which you want to run the script. Or in other words, the user on your Linux instance you want to use to run the script, such as root. Note that we're not using every one of these hooks. In our file, we're only using 3 of these hooks: before install, application stop, and application start. That's because they're the only ones necessary for this deployment, so we've completely omitted the other options from the file. Let's talk about each of these hooks in detail. The before and after install hooks are used for the scripts that you need to run before the installation happens and after the installation is complete. For example, here we're linking to a script that installs the dependencies needed to run our application. If I look at this script, you can see that I'm installing an Apache web server here, which is needed for the site. Going back to the app spec file, the application stop and application start hooks are used to run any scripts needed to stop and start the application. We're using these hooks to start and stop our Apache server. So looking at the start server script in a text editor, you can see we're doing just that, starting the server. And in the stop server script, you can see that I'm checking to see if the Apache web server is running, and if it is, I stop it. Now, there is another hook that you cannot use to initiate a script, and it's called install. In Codedeploy, the install stage is just the stage where it copies over the files from the source to the destination on your behalf. Lastly, you can use the validate service hook to run any scripts that you will use to test and make sure that everything has been installed and started correctly. After the hooks, that leaves us with one last section, the permission section. I'll go ahead and paste in a permission section to this file so that you can see some of the settings. The permission section is only valid if the OS setting is set to Linux. It refers to the permissions you want to apply to the files being copied in the file section. If you're specifying permissions, then the file section is required. I won't go through every part of the permissions, but I do want to state that if you use permissions, the one required part within permissions that you must include is the object section. Object refers to the set of system files, folders, or directories that the specified permissions are applied to after the file system objects are copied to the instance. There's a lot more to the AppSpec file that I can cover in this video, so make sure to check out the notes section for more information and resources. I'll also provide examples of how you can use the permission section for your deployments. Welcome to exercise 1. In this exercise, you'll be using your own AWS accounts to create an EC2 instance that you'll later deploy to with Codedeploy. If you don't have an AWS account, refer to the reading before this video called Create Your Own AWS Account. Here's how this will work. Your EC2 instance is what we'll refer to as your test environment. You'll be creating this. In exercise 2, you will use Codedeploy to eventually deploy code to this test environment. And that code will be stored in Amazon Simple Storage Service, or Amazon S3, which is an object storage service. Sounds simple enough, right? But there's a lot that needs to happen behind the scenes to make this work. For example, all these services need to communicate with each other, and none of that communication is allowed or enabled by default. That means Codedeploy needs to communicate with EC2, and EC2 needs to communicate with S3, and we have to set all of this up. To do this, we'll do a few things. The first is we'll create AWS Identity and Access Management, or IAM roles, for the services to enable communication. So for EC2, we'll create an IAM role that has permissions to S3 and assign it to our instance when we create it. That will enable the EC2 instance to grab the code from S3. We'll also assign a policy that has permissions to AWS Systems Manager Session Manager, which will enable us to remotely connect to our instance without having to manage SSH keys. Then we'll create a service role for Codedeploy, which will allow Codedeploy to call other AWS services, including Amazon EC2. So that's great. 2 roles that will enable communication to flow between the services. We're done, right? Well, not so fast. For Codedeploy to communicate with EC2, we not only need a role, we also need to install the Codedeploy agent on EC2 as well. So in the lab, after you create your EC2 instance, or your test environment, you'll connect to your instance and install the agent. And that enables Codedeploy to use this instance for future deployments. You'll also need to install the AWS Systems Manager agent on your instance as well, to ensure that you can remotely connect to your instance. So you'll be creating roles, creating an instance, and connecting to that instance to deploy an agent. And all of this will be built upon in the second lab. If you have any questions, feel free to post in the forums and get help from one another. If you see a question in the forums that you know the answer to, I encourage you to respond to others. The instructors will also be monitoring the forums as well. All right, go ahead and get started. In the last exercise, you got an EC2 instance up and running with a Codedeploy agent installed. You also created 2 IAM roles, one for the Codedeploy service and one for EC2 to communicate with S3. In this exercise, we take this a step further. You'll first create the S3 bucket where you'll upload your application code. We'll be providing you this code in a zip file format. And if you open up the zip file, you'll see you have a few different files. The first is an HTML file. Which contains the application you'll be using, which in this case is just a static site that looks like a blog. This index.html file is what you'll be hosting on your EC2 instance. We also provide you with an AppSpec file. Codedeploy will use this file to install the application dependencies and start and stop the server using scripts that we've created in the scripts folder of the zip file. Once you have your code uploaded to S3, you'll set up an application and a deployment group in Codedeploy. You'll then create a deployment that ships the code to the instance. After you see that your application works as expected, you'll change the code in any way you'd like, whether you change the color of an element or the text of the website, or both. And then you'll create another deployment, shipping out these revisions to your EC2 instance. You'll confirm the changes were made by viewing them on the instance, and then you'll be done with the lab. Remember, if you have any questions, you can seek help from one another or from the instructors in the forums or discussion groups. Happy learning! In the beginning of the week, I referenced a situation where a team of engineers wanted to practice continuous delivery on top of the continuous integration system they already had in place. At this point, we've spent most of the week learning how to get code deployed. However, we've still been performing these deployments manually, which doesn't really solve the scenario I presented earlier. The goal of that team of engineers was to automate their build, test, and then deploy that code to a staging environment before it gets released. All automated. So let's figure out how to do that with the information and services we know so far. So here I am in the AWS Management Console, and I've already set up a sample pipeline that looks like what the team already has in place. For this, I use AWS Code Pipeline to model and configure the different stages of the team's software release process. Since they're already practicing continuous integration, it's likely that the team had a source phase and a test phase. As you can see, I've already set up the source stage to use AWS Code Commit and a test stage to run unit tests on their site. Now we just need to configure a deploy stage to automate the deployment all the way from the repository to their staging environment. Okay, so to make this quick, I've already created an application and a deployment group for Codedeploy. So I'll go ahead and edit the pipeline, and I'm going to add in a deployment. I'll click Add Stage in the pipeline after the test stage and call it Staging, and then click Add Stage again. From here, I'll go ahead and click Add Action Group, and this is where I'll specify what kind of action I want to take here and which service I'm going to use to do it. I'll give it a name, call it something like Deploy to Staging. I'll select the service I want to use, which in this case will be Codedeploy. And then I'll specify the input artifact that flows through the pipeline. If you remember in an earlier video where we walked you through Codedeploy, we used the service by itself. When we used it as a standalone service, we had to specify the location of the artifact in an S3 bucket that we created. When you create a pipeline with Code Pipeline, it creates an artifact bucket by default and uses this bucket to store input and output artifacts and also transfers them from stage to stage on your behalf. In fact, we can go into the S3 console and see this bucket. I'll go ahead and search for this bucket with Code Pipeline in the title. And then I'll choose the one for the region I'm in. In this case, it'll be US West 2, and I'll click on it. I can select which pipeline I want here, and in this case, I'm using the CD pipeline in this demo, and then I can view the files in it. As you can see here, there's a folder that has our source artifact, which Code Pipeline will transfer from stage to stage. All right, so let's go back to the Code Pipeline console, where we're back to creating a deploy to staging action. If we use Codedeploy with Code Pipeline, as we're doing here, we'll simply specify the artifact that's in the bucket, and it takes care of the rest. I'll select the details about the application name and the deployment group, and then I'll click Done. All right. From here, I'll click Save, and then Save again. Okay. And then we'll kick off the pipeline once more. So I'll go into my terminal here. I'll find my application, which is index.html here. I'll make a change to the file, such as changing the font size. Save the file. And then I will git add the file, git commit with a message such as change the font size. and git push. Okay, so once we've updated the file, we can go back to our pipeline here, and I will give it a bit to run. All right, so it looks like everything's succeeded here, and we've automated much of the process already, so everything is good to go. Now, if we wanted a pipeline that released to production, we could simply add another stage here to deploy to prod. I've already created a pipeline that adds onto this that does just that. So I'll go ahead and find that pipeline. Click on it, and we can view the entire thing. Here is my source, test, the deploy to staging, and then the deploy to prod. But notice in the middle of these two deploy stages, I have a manual approval action. This is the point where I want the pipeline to stop so that someone can manually approve or reject this action. If everything looks good, it can be released. Otherwise, we'll need to troubleshoot and fix. This entire pipeline here is continuous delivery in action. It automates the deployment to the staging environment and includes a manual step here to deploy to prod. So with this pipeline in place, the team is now practicing continuous delivery.
When you sit down to write an automated deployment, it very, very rarely works first time. When I'm doing this, I generally test some deployment commands manually. I get confident the deploy is going to work how I planned. I start small and gradually add to the build scripts. That way I can isolate debugging down to just the changes I made in my small updates. When I do hit an error in a Codedeploy deployment, where do I start with my debugging? Number one, I can see all the deployment details via the console. I'm looking at a failed deployment in the console right now, and I'm seeing the message, some instances in your deployment group are experiencing problems. I can further drill down into the instance details down here. And I see the deploy failed at the very first event, application stop. I'm thinking I don't have the Codedeploy agent running on the instance. We need the Codedeploy agent to be installed in the instance for any deployments to work. Maybe you are installing this with your user data scripts on your instances, or maybe you use AWS Systems Manager to do this for you. I'll include some links in the course readings with details on how to install the Codedeploy agent. I've connected to the instance via Session Manager. I can check the status of the Codedeploy agent with this command, sudo service Codedeploy agent status. And that is telling me the service cannot be found. That's a sign I need to get the agent installed. What other types of errors can occur in our deployments? I have fixed my Codedeploy agent on my instance. I've reattempted the deployment and I see a failure. Again, in the console, I can see the details of the deployment. If I view the instance details down here, I'm being told scripts start server run as root failed with exit code 5. If I view more on this, there is the output of the script. It looks like I have a typo in there. Codedeploy makes the log tail available to me via the console and via the APIs. What if all my scripts ran, nothing returned an error back to Codedeploy, but there is something wrong in my deployment logic and I don't see my application working? Now I would look at the logs on the instance itself. Again, in a Session Manager connection to my instance, I can see the deployment log at this location. Opt Codedeploy agent deployment root deployment logs, and there is a Codedeploy agent deployments log. At the very end here, I can see the same error that I was seeing in the console. I have a typo there in service HTTPD start. There is also a deployment archive on the instance at this location. It is in opt Codedeploy agent deployment root. In here is the ID of my deployment group ID. And under that is all of the deployment IDs that have occurred on this instance. Let's choose one of them. And if I look here, I will see the deployment archive that was downloaded to my instance and a scripts.log for this particular deploy. The script logs are going to capture the output of my commands in my deployment scripts and any logging I've included. This should point me to some clues of why my deployment isn't going to plan. So where are you going to start your deployment detective work? We can see a lot of information in the console. Do you need some extra debugging details? We can always retrieve Codedeploy logs from our deployment instances.
Hey everyone, and welcome to the second and final week of the course. I know it's been a while, but I want you to think back to the beginning of this course, where we started out talking about a scenario of a team of engineers. The team wanted to use continuous delivery and automate the creation of their deployments. We also talked about why automation was a good practice in general, as it removes human error and increases speed and productivity. In the exercises you completed in week 1, you manually created a test environment, in this case an EC2 instance, to deploy your application to. And this week, we get to take automation a step further and consider how to automate the creation of this test environment, like our EC2 instance, and any infrastructure that supports that, such as IAM roles and a network. In a real production system, we might also have other environments we want to automate the creation of as well. Let's take the same scenario of a team of engineers that are working on their pipeline and releasing code, and they want to automate everything as much as possible. Let's say that team hired a bunch of new developers to work on their application, and now those developers need development environments. How do we get each new hire a development environment? Do we A, hand the developer a document with requirements and let the developers create it themselves? Or B, hand them a template of code to create the environment with all configurations already set? Well, the problem with answer A is that it's a very manual process, and we really need all development environments to look the same. It's possible with human error the developer might misconfigure something, which might lead to their environment being out of sync. Or even if they were to do everything the document says correctly, it's possible that the document itself is out of date or wrong. There's too many issues with this option, so let's talk about option B. Handing over a template of code to build the dev environment enables the team to treat this environment like code, meaning you can store it in version control, you can do code reviews, and even ship it through a pipeline. And that same template, with some changes, can be used to create your test environment and prod environment, so that every environment looks as similar as possible. This idea of treating our infrastructure as code is a fundamental principle of DevOps. It enables your team to apply the same rigor of application development to provisioning infrastructure. During this week, we'll talk about some of the key services AWS offers that enable you to properly use infrastructure as code, which is also known as IAC. These services will not only help your team provision dev, test, and prod environments, but they can also enable you to provision the entire pipeline itself, and even think about your pipeline as code. I know that's a little meta, but pretty soon, every time you look at a piece of infrastructure in the AWS Management Console, you'll think, this can just be a piece of code in a template. And thinking like that will help you build your DevOps culture. Get ready for week 2, where we talk infrastructure as code.
Hi there, I'm Ref. In the previous videos, Alana started the conversation about continuous integration and the AWS services you can use to leverage a way to develop something in a collaborative manner, from the source code to build and test. She also talked about Code Pipeline, the AWS service that can be used to orchestrate your continuous integration workflow, stitching together code commit and code build to automatically have the build done and tested according to the pushes in a Git repository. In this video, I am going to talk about the next steps to move your pipeline to the next level with the usage of infrastructure as code. Logging in the AWS Management Console and manually provisioning your environments is not ideal due to many reasons. It gets easier if you were the only one managing a simple environment in your personal account. But as you start working professionally with it as a part of a DevOps team, it rapidly becomes more challenging. Automation is key, and infrastructure as code is the process of managing and provisioning environments through code in a declarative way. Let me ask Alana something, and you will understand what I mean by using the words declarative here in the infrastructure as code context. Alana, I have something to ask you. What do you do when you go to a coffee shop looking for an espresso? Option A, you ask the cashier, I would like to have an espresso, please. Or option B, you start giving detailed instructions to the barista in terms of what they should do in order to get your espresso. Like, you start giving instructions like getting the coffee beans, grinding with a specific granularity, temper, put in the portafilter, turn on the machine for 25 seconds, etc.
Well, if the barista is capable of making an espresso, I would definitely prefer option A.
So do I, right? That's what I mean by using infrastructure as code in a declarative way. The reason why I am saying all this is because since you can interact with AWS services programmatically by using the AWS SDKs or the AWS CLIs, you can create your infrastructure through shell scripts. Although it gives you more control because you are exactly specifying the very fine details of what you want, it is way less convenient because you also need to concern with complexity, such as managing changes, auditing, rollbacks in case of failures, infrastructure consistency, and much more. AWS CloudFormation is a service that allows you to declare your infrastructure in a text file. In that file, you say what you want, pass it to the service, and CloudFormation brews the environment for you. This file can be authored in JSON or YAML. Once you input a file and ask CloudFormation to create a stack, CloudFormation starts creating the infrastructure for you. In the CloudFormation nomenclature, we call that file a template and the infrastructure components a stack. So, a template is something you define, and a stack is the infrastructure that actually gets created. This is what a CloudFormation template looks like. The resources part is where you declare what AWS services you want. If you want to create an S3 bucket, you can declare a resource of the type AWS S3 bucket. The CloudFormation documentation has a list of the supported properties for every single AWS service that supports CloudFormation, which is almost every service. This is the documentation page for the resource AWS S3 bucket. I prefer using YAML because it's simple for me to read. And you can see that a bucket can be created simply by specifying the bucket name as a property. All right, a CloudFormation template can be as simple as that. Just creating a bucket, pretty simple. You can submit that to CloudFormation and ask it to create a stack out of it. Once the stack finishes with no errors, you will have the bucket created as declared in the template. Now, here comes one of the coolest part. What if, in addition to that S3 bucket, you also want to have a DynamoDB table? Pretty simple. You just edit the template, add the resource AWS DynamoDB table, and submit it again to CloudFormation. But this time, you will do an update stack operation. Update stacks are awesome. CloudFormation receives the updates from the template and says, now in addition to the bucket, the user wants a DynamoDB table. Let me create it, and voila, it updates the infrastructure for you. Same thing with deletions. If you want to remove something from your infrastructure, you can remove from the template and do an update stack. CloudFormation will calculate the delta and make the infrastructure match what is desired on the template.
But Raf, S3 buckets and DynamoDB tables may contain data from your users. What if you want to delete a stack but retain some of the resources? Because when you delete a stack, CloudFormation will erase all the resources associated with the stack. And sometimes you want to erase some resources but not others, right?
That's right. When you delete a stack, CloudFormation erases every resource defined on that stack. And that's why some of the resources allow you to define an action when you delete the stack. For example, this S3 bucket has a deletion policy defined as retain, which will make CloudFormation preserve that specific resource upon stack deletion. The usage of this is actually a best practice every time you define a resource that will be used as a database, like an RDS instance, an Elasticsearch cluster, or a DynamoDB table. CloudFormation is very powerful. We could spend hours and hours talking about its features, but we have to move on in our DevOps journey. So I strongly recommend you taking a look at the CloudFormation documentation. Having the ability to write a template and have the infrastructure created is super powerful. Since we are talking about having a CI/CD pipeline, you can have CloudFormation templates in a code commit repository, and whenever you do a push with a change, Code Pipeline orchestrates the environment change by executing an update stack as part of the deployment. When we start doing this practice, we have developers operating the infrastructure. And this is actually where the word DevOps comes from. Developers who also operate. And because developers are good with code, when we talk about infrastructure as code, developers are the expert.
As Raf and I mentioned earlier, a pipeline is also programmable infrastructure. For example, take Codedeploy. In exercise 2 of the course, you created an application and a deployment group in the console manually. While you were doing that, I created an application and deployment group in a CloudFormation template. Here's what it looks like. We have our application declared at the top of the screen here. We gave it a name, and we also determined that we're deploying to Amazon EC2 as our compute platform. So overall, 6 lines of code to declare this resource. Not bad. If I scroll down, you can also see my deployment group and all of its properties. So not only do we have the name of the deployment group, which application it belongs to, our configuration settings, and the deployment style, we also declare which EC2 instance we'll be deploying to. In this case, the instance that's tagged as code pipeline blog. And you can also see that it references the application. So that means when I run this template through the CloudFormation console, CloudFormation won't build the deployment group until after it builds the application. This makes sense because we need an application before we can create a deployment group. I also, in the same template, created a service role for Codedeploy and an EC2 instance that has the Codedeploy agent installed. So basically, everything you did in exercise 1 and 2 is now in this one template. To build off of all that, I also created all the other components of a pipeline, including code commit and code build. And then I created a code pipeline with a source stage, a deploy stage, and an acceptance test stage. So let's see this run. I'll go to the AWS Management Console, search for CloudFormation, click Create Stack, upload this template file called Final Pipeline, and click Next. Here I'll have to name the stack. I'll call it Final Pipeline Stack. And then I'll call the pipeline Final Pipeline. So I'll go ahead and keep all the other defaults, click Next, keep the defaults again, and Next again. Acknowledge that it might create IAM resources, and click Create Stack. However, I've already created this CloudFormation stack earlier to save us some waiting time, which is why we got this error here. So I'll go ahead and cancel out of this and click on the stack that I created earlier to find all of its resources. All right, so this CloudFormation template has already been provisioned and everything looks good. And if I click on this resources tab here, we can see all the resources that were created when I ran this template. So let's jump over to our pipeline that was created by this template by going to the Code Pipeline console. As you can see, the pipeline has already started running, but here's what happened behind the scenes. If I go back to the template, when I wrote the code to create code commits, as you can see here, I chose to propagate the repo with code from an S3 bucket. So the commit was made, which kicked off the deployment, which if I go back to the console, I can see has succeeded. If I click on the details and scroll down, I can find that the instance that it deployed to is right here. So I'll go ahead and click it, which brings me to the EC2 console. Select the instance, copy the public IP address, and paste it into my browser. And it looks like the deploy worked. My app is up and running. Okay, let's go back to the pipeline and see the final stage, the acceptance test. All this test does is access the instance and check if it can access the landing page. If we click details of this stage, we can look at the commands we ran in the build spec and the output of those commands. As you can see here, it pulls the HTML from our landing page, and that's exactly what we wanted to accomplish. So everything looks good. So that's how I automated a pipeline with CloudFormation. If you're looking for this template to download so you can try it yourself, I'll be providing it to you in exercise 3 of the course, along with the build spec file, the app spec file, and the app itself. Now, if I wanted to take it a step further, I could change the HTML file and commit it to my repo, kicking off the pipeline once again, and see my changes in real time. But you'll be doing that in the next exercise. So, see you soon.
Hi, it's me again, Raf here. So, according to everything you have learned so far, CloudFormation is an infrastructure as code service that you can rely in order to build your infrastructure automations. CloudFormation is one of the core components of almost every CI/CD workflow, and you would like to make sure your CloudFormation templates are as reliable as possible. In most cases, when the creation of a stack fails, you will see a detailed error from CloudFormation pointing out where the issue potentially is. The most common error is due to permissions. Resources created or deleted by a stack gets operated on behalf of the user who is operating the stack. So if you have a template that creates an EC2 instance, but your user is not authorized to do so, that step will fail. And if the stack creation is set to roll back in case of failure, everything created so far will be deleted to leave the infrastructure in a consistent state. Another aspect I would like to highlight is that CloudFormation is a service that operates the resources in the given region where the stack is running. So if you create a stack in US East 1 or Virginia, the resources will be created in that region. That being said, some services require a property that only exists in a specific region, such as, for example, EC2 instances and their AMIs. The Amazon Machine Image, or AMI, is the image containing the operating system of the EC2 instance you want to create. Each AMI has an ID, and these IDs are different according to the region you are operating in. If you want to create an EC2 instance and hard-code the AMI ID into the template, you would need to make sure that the specific AMI ID exists in the region you are creating. Otherwise, the creation would fail because CloudFormation would be trying to launch an instance with an AMI that does not exist in that region. CloudFormation has a feature that makes the templates more reliable in terms of cross-region. So if you want to build a template that can run on any given region, you can use a CloudFormation mapping. A mapping is a feature that allows you to choose different values according to which region you were running or any other value. Imagine the mapping as an if statement. For example, if you are running the template in US East 1, then use this specific AMI ID. If you're running in US West 2, then use that other one. That would fix that problem and make your templates more resilient. That can also be applied for parameters, such as if a parameter has environment equals prod, then choose a specific instance type. If the parameter has environment equals dev, then choose another instance type, which could be a smaller one. Okay, cool. With the use of mappings, you can create a more flexible template. But how about the resource creation sequence? For example, what if you have an application that needs an RDS database up and running before creating the EC2 instance? Another common troubleshooting topic is the dependency error. As the name suggests, a dependency error is when CloudFormation tries to create a resource that depends on another resource that hasn't been created yet. CloudFormation creates the resources in parallel to optimize speed, but it may not know the order of precedence needed by your application logic. You can add a property called depends on in the creation of the EC2 instance. That would make CloudFormation hold the creation of the instance and only do it after the RDS instance has been created. In the property, you can specify one or multiple resources you want to depend on. If you're doing serverless, dependency between resources may be more frequent. such as creating an API gateway endpoints and Lambda functions associated with it. That's why the usage of SAM, or Serverless Application Model, brings you good help, because it is an abstraction layer that gives you a serverless-oriented view, so it already knows some obvious dependencies among resources. There are also other troubleshooting topics described in the AWS documentation, but you guess what? Alana told me she will add that link to the course readings so you don't miss anything.
So you're now ready for the next exercise. This is where we put all the pieces of what we learned together. If you took the first class in the series, you'll already be familiar with code commit, code build, and code pipeline. And in this course, you spent time learning about Codedeploy and CloudFormation. So if we're using all of these services, what could this lab possibly be about? Well, you might have already guessed it. You'll be automating the creation of an entire CI/CD pipeline. Here's how this will work. I'll provide you the template that I showed in the automation of a pipeline video. You'll upload this template to CloudFormation, and it will provision every piece of your pipeline, including code commits, code build, and code deploy. It will also kickstart your pipeline initially. Take a look at the template and try to understand each resource that gets created. You can also see some of the CloudFormation features that Raf mentioned earlier, such as the parameters section. For example, one of the parameters is an AMI ID for the EC2 instance. Instead of you specifying an Amazon machine image, or AMI ID, the template grabs the latest AMI ID from AWS Systems Manager Parameter Store, so you don't have to worry about choosing the wrong AMI. After you provision the template, you'll look at the pipeline the code pipeline created and check the output of the pipeline, which is the application on your EC2 instance. In this case, a website that shows a blog. The other output of the pipeline is your acceptance test. We've populated the code commit repository with a build spec that shows the acceptance tests we'll be performing on this application. I'll display that same file on screen. As you can see, we're getting the IP address of the server, using curl to get data from that IP address, and the result we should get is the index.html page when we go to look at the output of this test. That'll tell us that the website is reachable. From there, you'll make a change to the index.html file in the repository, which will kick off the pipeline once again. You'll then check the results of that pipeline by verifying the code on your instance was changed. Once again, feel free to post in the forums if you run into any issues. All right, let's get started with exercise 3. Congratulations on completing, and thank you for taking this course. We covered a lot of topics. In the first week, we covered continuous delivery and some of the tools that help us achieve it, like Codedeploy. You went in depth with this service, learning how to deploy to an EC2 instance manually and how to automate that deployment using code pipeline.
In the second week, we learned how to automate our environment and our pipeline further using infrastructure as code. We focused on the CloudFormation service, giving you an overview of the service, how it can help in the pipeline automation, and how to troubleshoot when things go wrong. At this point, you should feel pretty comfortable with all aspects of a CI/CD pipeline and the AWS services that can help enabling CI/CD. So, you may be asking yourself, where do I go from here? Well, there is another course in this series where we cover monitoring and operation aspects for every single step involved in your pipeline, from the application to the network and the AWS services you use all the way to monitoring the pipeline itself. For all things monitoring and observability, feel free to continue on the next course in this series.
On behalf of Russ, Raf, and I, thank you for taking this course. We hope you've learned some new things and enjoyed our time together.
We hope to see you in the next course. See you soon! Hi there! In previous courses, you should have learned about the other DevOps components, such as plan, code, build, test, release, and deploy, where you learned important aspects on how to get your CI/CD in an automated state for application and infrastructure changes. My name is Rafael Lopez, but you can call me Raf. I am one of the instructors for this AWS course about monitoring and operation, which are the final parts of a full CI/CD DevOps workflow. Monitoring and operation are key aspects for both the release pipeline and production environments, because they will give you instruments that will help you know what's happening, as well as do modifications and enhancements on infrastructure that is currently running. In this course, you will learn how to use AWS services to control your architecture in order to reach a better operational state. And I plan on doing that by dividing the topics into 2 weeks, where I will talk about monitoring in the first week and operations in the second week. For the monitoring week, the content is divided into the cloud, application, and networking environments, with some relevant AWS services for doing monitoring. In regards to the cloud environment, we will be covering CloudWatch metrics, alarms, and logs for monitoring, as well as Amazon Event Bridge and AWS Config for continuous compliance. We will also be talking about CloudTrail and a little bit of machine learning for monitoring operations. For application monitoring, Alana will talk about AWS X-Ray, CloudWatch custom metrics, and CloudWatch synthetics. And for network monitoring, Alana will talk about VPC flow logs and some other cool features. You may recognize Alana from a previous course as part of the DevOps series here in this platform. She was one of the instructors for a good portion of the CI/CD part of the DevOps workflow, the release and deploy. If you haven't watched that course yet, I recommend pausing and going back, because many of the components we will be talking about here require some prerequisites taught in that course. This course will also have hands-on activities brought to you by my friend Russ Sayers, directly from Australia. At the end of the week, we will offer an exercise that will help you use AWS monitoring services to monitor activities made in the AWS code pipeline. That's it. I hope you enjoy it. Welcome to the first week of the DevOps course about monitoring and operations. Ready to instrumentalize and monitor everything? I am. Alright, so you got it working. The CI/CD is working well, and everything seems to operate like a well-oiled machine, meaning that you have fail-safe mechanisms to push things to production whenever needed. But is that everything you need in order to have a real smooth operation? From that stage on, your application has graduated to production, which means it has its doors open to the public. Operating a public-facing infrastructure without monitoring is similar to flying an airplane without instruments, and that's totally not where you want to be. The big question is, how would you know how your systems are performing for the real world? Well, to answer that, I personally like to catalog metrics into 3 major categories, which are environment metrics, application metrics, and network metrics. Let's start with the first, environment metrics, which are metrics that refer to the environments the application is running, such as CPU and memory utilization, disk space, number of read IOs, number of write IOs in your database, and operational things that help you to detect architecture bottlenecks and do optimizations. I also include here the monitoring of operations made by the DevOps team to the environment, such as the state of the CI/CD pipeline, configuration changes, and logging about everything that was made in the environment. Another major monitoring category are application metrics, like how much time do specific routines take to complete, or what routines are more expensive in terms of compute or memory resources. That would be helpful to find slow queries or prioritize code refactoring to make things run faster and cheaper. These metrics could be interesting for developers to troubleshoot issues on the code, or product managers to strategize what part to refactor first. For application metrics, you can count them with the help of AWS X-Ray and CloudWatch custom metrics. These services also allow working with business-related metrics, such as the number of active users per hour, how much time each user spends in the platform, and useful insights for business stakeholders. Last but not least, network metrics. As the name suggests, these are focused on networking. When I say networking, I refer to things like latency measurements, packets per second, and networking aspects of the operation. This is very valuable, especially if you are developing applications mostly consumed by mobile phones. I say that because your users will be using their internet connections to access your endpoints. And because that's something out of your control most times, monitoring is even more instrumental. Network monitoring is also relevant if you have clusters and lots of internal communication between your servers. If your resources are sitting in a VPC like EC2 instances and RDS databases, you can leverage AWS managed services like VPC flow logs in order to have digested information about your networking activity. There are so many options, and I don't want to give you spoilers of what you are about to learn in this course. Among all those options, the last thing you need is to worry. You are in the right course if you came here to learn about AWS and how to monitor things. Alana and I will talk about the AWS services and ideas that can help you to tackle each one of those monitoring areas. Ready to start? I am. Alright, so here we are. Let's talk about AWS services you can use to add instruments to your cloud environment. In this video, I will talk about Amazon CloudWatch, what it is, what it does, and what are the core components. Amazon CloudWatch is a suite for cloud resources and applications. It gives you the instruments to see what's going on, and it can notify you when something doesn't look right. The core components of CloudWatch are metrics, alarms, and logs. Let's talk about the metrics first. CloudWatch metrics are data points collected over time. Some managed AWS services send metrics automatically to CloudWatch, like EC2 instances, for example. If you run an EC2 instance, you can expect to have metrics for CPU utilization, network packets in and out, and some other metrics. Most managed AWS services send metrics to CloudWatch automatically, such as Amazon SQS, Elastic Load Balancing, Amazon RDS, API Gateway, AWS Lambda, and many others. You can also have custom metrics by doing API calls to the service, so you can use CloudWatch to collect metrics from things that are not sent by default, such as the number of connected users and business logic metrics. We will cover custom metrics in another video, so let's stick with the default metrics for now. For example, if you want to see data about the duration of a specific Lambda function, you can go to the CloudWatch console, select Lambda as the service, sort by function name, select the function, and simply hit the box duration. You will see a line chart. You can also check multiple metrics at the same time and see all of them in the same graph, such as duration from multiple Lambda functions. If you have a CI/CD in place and you are working with CloudFormation to deploy identical environments, a good idea is to compare the amount of time across functions on different stages, like dev, test, and prod. Good architectures have excellent metrics, regardless of the scale. So, speaking about good practice, have you heard the term, if you see something, say something? In CloudWatch, you can specify an alarm that triggers an action if something doesn't look right. This alarm gets enabled when values from metrics hit a specific threshold for a specific time. Introducing CloudWatch alarms. The thing is, what threshold should I put for the alarm? What number? Well, if there are two things that are hard for a DevOps person, it is naming variables and choosing thresholds for what is considered good or bad. So, why not let the machine decide? If you want CloudWatch to take a look at your metric and define the thresholds for you, you can use a feature called CloudWatch Anomaly Detection. CloudWatch Anomaly Detection uses machine learning algorithms that continuously analyze metrics of systems and applications, determine normal baselines, and surface anomalies with minimal user intervention. It may look complicated, but look how easy it is to use it. Here is a function that stores items into DynamoDB. It's a core function in an app I made. The app itself is not relevant, so let's focus on the CloudWatch part. Here, I would like to set an alarm if there is a spike in the duration of the Lambda execution, indicating that potentially there is something wrong. We can click on the function's name, then select Graph Metrics for that function, and then click on that little icon to enable anomaly detection for that metric. Some magic happens, look. You can see the expected values. In my case, it was quick because I already have the ML model trained. If you're doing this for the first time, this gray threshold may take some minutes to be created. Here we can see an algorithm defining thresholds for us based on min and max values. To create an alarm for that, simply click the bell icon to create the alarm, and choose anomaly detection to use the band as a threshold. Click Next, and then choose the alarm action, which can be an auto-scaling action, an EC2 action, a notification to an SNS topic, or a systems manager action, which I will talk about next week. Oh, and don't worry, I used the AWS Management Console for that just to illustrate the feature. Of course, you can set up all that programmatically. Last but not least, CloudWatch Logs. CloudWatch Logs is another core component of this service. It allows you to centralize log files from all your systems, applications, and everything you want. Once you have your logs in there, you can basically teach CloudWatch how to parse the log lines and populate metrics out of specific fields of the text. And once you have a metric, you can use anomaly detection and create alarms. If you're running applications on EC2 instances, you can use the CloudWatch agent to push log files to CloudWatch. If you're using Lambda functions, API Gateway, or any other AWS managed service like Code Build, the integration and the logs are already there. All you need to do is use it. For example, if you do a print or console log statement inside your Lambda function, that output will end up showing in the CloudWatch Logs log stream for that Lambda function. That's it. I hope that this video gave you a good idea about how to better understand what CloudWatch is. Don't forget to read the course notes. I will put some more detailed information in there regarding anomaly detection, which is a pretty interesting feature. There is a big trend on applying machine learning capabilities to DevOps components, and anomaly detection is a very easy way to achieve it. So far, you have understood that monitoring is a very important part of the overall CI/CD pipeline. All the monitoring concepts you have learned so far can be applied both to the application serving customers and, why not, to the CI/CD pipeline itself. In this video, I will approach the monitoring that can oversee multiple aspects of your architecture, starting with the CI/CD pipeline monitoring. As part of previous courses in the DevOps series, you learned the components to push code into production by using AWS services to make it happen, like Code Commit, Code Build, Code Pipeline, and other AWS services in the DevOps area. In this video, I will be giving you examples on how to use 2 additional AWS services to monitor code pipeline from different perspectives. I will talk about Amazon Event Bridge and AWS Config. You can monitor code pipeline events in Amazon Event Bridge, which is a service used for delivering real-time data from your own solutions and AWS services. Event Bridge calls events to targets, such as Lambda for code execution and Amazon Simple Notification Service for notifications, and also even AWS partner integrations. Event Bridge was formerly called CloudWatch Events. So if you heard the name CloudWatch Events, you know it's the same thing. You know when you have an if statement in your code, if this, then that? The thing is that in order for the if to satisfy a condition, it must have a comparison. It needs 2 things to compare to each other. And that's where Event Bridge shines. As the name suggests, Event Bridge allows you to take actions in response to an event. In the same way you would have an if operator in a source code, think about a when statement when thinking about Event Bridge. With that in mind, it's now easier to know what AWS service to use if you want to get an alert when a code pipeline execution fails or succeeds. Check how easy it is. You just go to Amazon Event Bridge, click Create Rule, choose a name for the rule, select Event Pattern, which is the when logic, select Predefined Pattern by Service, choose AWS from the service provider, then choose Code Pipeline from the service name. And note how many other AWS services support Event Bridge. Now choose Code Pipeline, Pipeline Execution Stage Change as the event type, and the endpoint failed as the specific state. Notice that the event pattern with JSON that gets populated on the right side changes as you click on the options. Then scroll down and choose a target. And look how many targets are available. You can queue a message into Amazon SQS or send a notification to an SNS topic, which could do an HTTP post for a webhook and post a message into a chat room or open a ticket. For example, if you trigger a Lambda function that fixes the issue, you can bring your pipeline into a self-healing state. Once you are done, just scroll down and click Create to create the rule. And of course, you can and actually should create these rules via CloudFormation by using the AWS Events Rule CloudFormation resource. A best practice is to create separate CloudFormation stacks dedicated for monitoring features. And guess what? You can use a code pipeline to orchestrate that, in the same way you would use to orchestrate any other environment. All right, we explored a little bit of EventBridge, a service that gives you a when capability in terms of doing something when something else happens. But there is another AWS service that I would like to talk about, which plays a key role in the infrastructure compliance. Introducing AWS Config. AWS Config monitors administrative API activity performed to your AWS account and saves a delta between the configuration differences on how the infrastructure was before and after a specific API calls. You can have the option of triggering a Lambda function to evaluate the infrastructure in terms of compliance after the change, and have that function respond back to config to say if the infrastructure was left in a compliant or not compliant state after the change. This is called an AWS config rule. Think about the term infrastructure delta when thinking about AWS config. So if you want to monitor changes in the code pipeline configuration, AWS config can detect these API calls and calculate the difference. Now, if you want to monitor a pipeline stage change, like from running to failed or from running to completed, and then do something when that happens, EventBridge is your way to go. To better clarify the difference, let me give you a practical example on how both config and EventBridge can be used for pipeline monitoring from configuration to execution. If you want your pipelines to be tagged with specific tags, use AWS config to monitor configuration changes, and mark the pipeline as non-compliant if they are not properly tagged. If you want to take an action, such as sending an email to the DevOps team if a specific step of the pipeline fails, use an EventBridge rule to detect and dispatch a notification. Please let us know in the forums how you are using AWS config and EventBridge as part of your monitoring and continue. In the last video, we talked about change monitoring with AWS Config, which is an AWS service that allows you to take actions based on infrastructure changes. In this video, I would like to talk about AWS CloudTrail, an AWS service that also operates on that scope, but in a more granular way. As the name suggests, CloudTrail gives you a trail of API actions made to an AWS account, giving you visibility into user and resource activity. CloudTrail is enabled by default in every AWS account and saves AWS API activity into an Amazon S3 bucket in the form of compressed text files. Did someone create a new instance in your account? CloudTrail stores that. A security group rule was changed, opening a firewall port, CloudTrail logs that. A modification in the code pipeline configuration, it's also captured by CloudTrail. It logs API activity for API calls made to an AWS account, with the corresponding response from the service, no matter if it was successful or not. So what's the difference between AWS Config and AWS CloudTrail? It's simple. While AWS Config gives you the infrastructure delta, AWS CloudTrail will give you the evidence, the specific API call that was used in order to make that change, which is instrumental for forensics, security analysis, and troubleshooting. In addition, at this point, you should be embracing automations, like the start of code pipeline upon push into code commits to make changes in your environments. The more automation you have, the more the S3 bucket used by CloudTrail will be populated. A good practice is to use data visualization tools to visualize the API calls made to your AWS account. That leaves a bit from the DevOps area and enters a little bit more into the data analytics one. But the thing is, once you already have that solution, navigating through the CloudTrail data is way easier than having to manually parse compressed text files in a bucket. I recommend having some sort of data visualization solution on top of CloudTrail data. There are plenty of tutorials around on how to do that, and even a short course made by us here in this platform. I will put more details into the course notes. That's it. And remember that when something changes in your AWS environment, AWS Config gives you the delta. AWS CloudTrail gives you the evidence. Stay safe.
So far, Raf has given us a great background on how to monitor AWS resources from auditing to performance. But in this video, we'll discuss application monitoring. Take the following scenario. Let's say I create an application and run it on an EC2 instance. How do I monitor this application? I want to monitor things like application failures, make sure the app is running as expected. I also want to monitor the usage of the application and learn things like how many users are signing up, how many page views I'm getting, which part of my application is hitting limits. And also, I want to learn any other business relevant information. But because this data is so specific to my application and to my business, the CloudWatch built-in metrics for EC2 aren't going to be as comprehensive as I need them to be. Great for monitoring CPU usage and network packets coming in and out, but not going to work to calculate my user signups. So what do I do? How do I collect this data that is so custom to my application? Well, this is why you need custom CloudWatch metrics. These are the metrics that are specific and important to your application. The best part is you can generate custom metrics by instrumenting them directly in your application code. So if you're running an application on EC2, ECS, or even Lambda, you can use the Put Metrics Data API call to write any custom metric you want. For example, here's a custom metric that gathers data on number of user signups. Once we have our metrics created, we can head to the CloudWatch console and visualize all the built-in and custom metrics that have been generated by our application. I can create line graphs and even visualize my data through a number if I'd like, such as our page view metric. I can see here that I've gotten a few user signups from me and a few of my friends. Now, these metrics are great. They provide me numeric data like request rate, error rate, and more. But what if I want to see an end-to-end view of requests as they flow through my application to get a better idea of what the customer experience is like? Maybe I have an application that looks like this: API gateway, a Lambda function, and a DynamoDB table. I want to see a single user's journey across these multiple stages to identify bottlenecks, latency spikes, and other issues I might need to solve in order to improve the performance of my application. Well, it turns out there's a service for that, called AWS X-Ray. This service enables you to view requests as they go through your application, and provides tools that let you view and understand that data to identify issues. If you want to enable X-Ray for Lambda and API Gateway, all you need to do is check a box in the console. If you want to use X-Ray with EC2, you'll need to install a daemon on the EC2 instance. However, once you enable X-Ray, you can begin to collect data from your application and services to generate what are called segments, which provide details about a request and details about the work done. These segments are then grouped into traces. Here's an example of what a trace looks like. You can see information about the request, response, and duration. These traces are then processed to generate a service map, which allow you to visualize each AWS resource that sends data to X-Ray in a graph. As a result, I can see my application I spoke about earlier visualized here. I have a node for my API, a node for my Lambda function, and a node for my DynamoDB table, all visualized. The more pieces I have of my application and the more complex and distributed it gets, the more helpful the service map becomes. If you want to use CloudWatch and X-Ray and don't want to go to two different places to see all of that data, there's another service that enables you to combine the two. You can use CloudWatch Service Lens to view traces, metrics, logs, alarms, and other resource health information. That means it integrates both CloudWatch and X-Ray, so you can see observability information in just one place. Service Lens also integrates with Amazon CloudWatch Synthetics, which is a fully managed service that enables you to create canaries to monitor your endpoints and APIs from the outside in. These canaries are simply just scripts that you write that run on a schedule. You can use them to mimic customer traffic as it flows through your application so that you can better verify that the customers are having a good experience with your app. The entire idea of this is that you discover issues before your customers do. All right, so lots of great features for monitoring, and we're going to take it a step further when we talk about network monitoring. See you soon. It's time to talk about monitoring your network, specifically through logging. Logging often comes in handy when you want to gather information about requests that are coming into your system. And depending on the way your system is set up and the services you're using, you may have a few options on how to enable logging. Take a look at this architecture. Here we have an Amazon Virtual Private Cloud, or VPC, with a few subnets. We have 2 EC2 instances, a load balancer to distribute traffic to those instances, and an internet gateway so that internet traffic can flow to the subnets, with the appropriate routes dictating that it can do so, of course. If I wanted to enable logging for this architecture to get an idea of the type of requests getting sent through my network into my application, where could I do that? Turns out I have a few options. The first is through VPC flow logs. These are meant as a way to capture information about IP traffic coming into our VPC, our subnets, and any network interface. You might not be familiar with the concept of network interfaces, but you can think of them as virtual network cards that maintain data like IP addresses, MAC addresses, and more. The important thing to know here is that EC2 instances, or resources that run on EC2 instances, such as load balancers and RDS databases, use these network interfaces. So for any of these resources, you can create flow logs. To create a flow log, I'll specify the resource I want it to collect information for, maybe a subnet or an EC2 instance. Then I'll specify the kind of traffic I want to collect, if it was traffic that was accepted, traffic that was rejected, or all of the above. And then where do I want this traffic to be delivered to? For example, we can either send these logs to S3 or CloudWatch logs. After I create it, it'll take a few minutes to start collecting traffic, but pretty soon I can get information like the number of packets and bytes that have been transferred between the start and end timestamp for the request. And I can even get enriched data, like the type of traffic. Was it IPv4, IPv6? Is there TCP flags? All of that information will be sent to either S3 or CloudWatch logs. Again, your choice. So for this architecture, I can enable flow logs for my VPC, my subnets, my EC2 instances, and for my load balancer. For my load balancer, I can take it one step further and enable access logs, which allow me to collect information about requests sent to my load balancer. ELB access logs are disabled by default, but you can choose to enable them to get information about your requests. For example, I can get info like client IP address, latencies, request paths, server responses, and more. Also, if the request gets to the load balancer but never gets to a target, such as an EC2 instance, the request still gets logged. So you can dive in and figure out if it was maybe a malformed request, or if maybe there was no healthy EC2 instance to respond to it. Let's take a look at another architecture, this time a serverless architecture. Here we have a CloudFront distribution, an API gateway, a Lambda function, and a DynamoDB table. No network in sight, no ELB in sight, so where can I enable logging here? The first opportunity is to enable logging with CloudFront. You can log every request that comes into your distribution. There are 2 ways of doing this. The first is that you can enable standard logs, also called access logs sometimes, and it will provide a detailed record of each request, batch those together, and deliver to Amazon S3. The second way of doing it is to enable real-time logs, which, as the name implies, gives you a detailed record of a request and delivers that to you within seconds of getting the request. Now, you don't have to get a detailed record for every request if you don't want that. You can set up a percentage of requests to get records for, or even set up fields the requests have to match in order to be delivered a record of that request. Real-time records are delivered to Kinesis data streams. So that's one place. The next place I can enable logging is with API Gateway. There are also two ways of logging with API Gateway: access logs and execution logs. With access logs, you can find out who has access to your API and how they accessed it. With execution logs, you can get information about errors, execution traces, information about payloads, and so on. Both of these create logs in CloudWatch logs. So those are opportunities for logs with this architecture. Now, on to the real issue, which is, once I have logging turned on for all these services, how do I get real insights from all that data? Short answer is through data analysis tools. If your logs are going to Amazon S3, you can use analytics services like Amazon Athena and Amazon QuickSight to query and visualize your log data, or even put it in an Elasticsearch cluster and use Kibana. On the other hand, if your logs are going to CloudWatch Logs, you can use CloudWatch Logs Insights to search and query your log data so that you can easily filter through your data and better troubleshoot any operational issues. All right, that's it for this one, and I will see you next time.
In this exercise, we start with a simple pipeline created from a CloudFormation template. You may recognize this stack from the earlier course. How can we monitor the state of a pipeline? Like many other AWS services, Code Pipeline generates events that can be delivered to the EventBridge service bus. From EventBridge, we can deliver these events to a target, like Lambda, CloudWatch Logs, and SNS topics. To do that, in this exercise, you will create an SNS topic and subscribe an email. Then go to the EventBridge and create a rule. For filtering the events we are interested in, we apply an event pattern to the rule, which in this exercise, it will be the pipeline execution state change. When configuring the rule, you will need to specify a target, which is the SNS topic you had created. If everything is correctly configured, you will have Code Pipeline delivering events to EventBridge, which then uses a pattern to select the events we are interested in, sending it out to the SNS topic, which will send you an email. You will see that you can have pipeline monitoring with a few clicks in the AWS Management Console. Notice that SNS targets are just one of the possible destinations for this monitoring. A broken build is usually a pretty high priority event because developers may have to wait for it to be fixed in order to continue their work. When a code build fails, it is a sign that productivity is impaired. When doing this exercise, think what else can you trigger to get the team's attention? What about blinking lights with the use of IoT devices? All of this is possible with AWS Lambda and AWS chatbot integrations with our EventBridge patterns, which we will not be covering in this lab, but would be curious to hear from you in the forums. I hope you liked the content and the lab we put together for you for the previous week. Don't forget to use the discussion groups or forums if you had any issue with the lab or if you want to ask something. We will be constantly monitoring the discussion groups and forums to interact with you. In the second week of this course, I will be covering aspects regarding the operational part of your environments. An important aspect of the DevOps workflow is to know that a continuum must be made. That's where the term continuous integration and continuous delivery comes from. A continuum means that the workflow acts as an infinite loop. And in order for that to smoothly succeed, you must think about things that would allow the loop to be completed. Otherwise, it's not a loop, but a dead end. What I mean here is that you need to think about things that will not interrupt the DevOps workflow. And AWS offers a suite of services that you can use to facilitate that. In this week of the course, I will be talking about the AWS services that will help you operationalize your infrastructure. What I mean by operationalize is having your infrastructure operating in a uniform and compliant state. For example, there is a service called AWS Systems Manager that helps a lot with that task, and we will be covering some of the core aspects of it. I will also be talking about CloudFormation best practices. At the end of the week, you will do a hands-on exercise using a feature of AWS Systems Manager called Run Command to troubleshoot production issues. Ready to start operationalizing everything? Stay tuned. So far, you have learned about some concepts in a CI/CD journey, starting with the dev aspects and moving towards the ops part of the operation. You should be familiar with this graphic, which represents a complete DevOps journey for a given application. In this video, Alana and I will talk about some things you need to take care of in order to facilitate the smooth transition between the end and the beginning of this feedback loop. Let's say you applied everything you learned so far, and you have an application created via CloudFormation and orchestrated via code pipeline. If you have that, it is likely that you will have it updated whenever pushes are made to the CloudFormation template hosted on CodeCommit. Although that's awesome, I have a question for Alana. Alana, how would you try to predict a failure due to a hidden bottleneck?
Good question. Let's consider a few examples to visualize that problem. Imagine that you modify your CloudFormation template to separate your environment into different VPCs. So instead of a couple of VPCs, you now may want to use tens of them. Or perhaps your Lambda functions are working pretty hard, and you want to increase the maximum concurrent executions. Well, if you leave everything on the defaults for your AWS account and had never requested a soft limit increase, this update stack operation would potentially fail because there's a limit on the number of VPCs you can have in a region, as well as the number of concurrent Lambda function executions. Depending on how you have your CI/CD configured, that stack update failure could prevent other developers from pushing changes until it's resolved. Now, there is an AWS service called Service Quotas, which gives you a list of the AWS default quota value and the applied quota value in your AWS account. It's always worth checking if you're increasing capacity of a given resource. Of course, you can also do API calls to service quotas to get these numbers programmatically, which might be instrumental to incorporate in the build part of your pipeline. Okay, so let's say you're not facing any limit issues in an update stack operation. What about other things that could break the flow?
Great question, Alana. For the sake of having everything going smoothly with CloudFormation at the end of your CI/CD, I would like to talk about an important feature, CloudFormation change sets. There are 3 ways to change an AWS environment created by CloudFormation. The first one is directly touching the resources, which you should avoid doing, and you will understand why later in this course. The second method is updating the stack directly. And the third one, which is a little bit more sophisticated, is by using that CloudFormation feature called change sets. The advantage of change sets is that you can predict a little bit the result of an update stack operation by having CloudFormation telling you what will be changed, so you can double check if that's really what you want before proceeding. Here you can see the JSON that was generated by submitting a modified template that removes an EC2 instance and adds an auto-scaling group with a launch configuration. It is pretty simple to understand. It gives you what will be changed in the section Changes of the JSON. And here you can clearly see that 2 resources are being added and 1 is being removed, which is the EC2 instance. It is always a good idea to use CloudFormation change sets for production environments. Once you have an original stack running, you submit a change set, view the change set. If everything looks good, you can execute the change set. Otherwise, you do additional change sets or cancel the entire operation.
All right, smooth operator. Let's move on. You ready, Raph?
Yeah, I'm ready. Imagine the following scenario. You have an EC2 instance and 2 subnets that you create via CloudFormation. Subnet A and Subnet B. After creating the stack, you realize that you forgot to add tags in the instance. And let's say you go in the AWS Management Console and add the tags. In this case, tagging strategy is very important because you are running a script that does security checks only on instances marked with specific tags, like environment equals prod. which is the case here. 1 week later, you forgot that you manually added these tags and decide to change that CloudFormation template by doing a modification on the instance. You now want to change the instance subnet from subnet A to subnet B. According to the CloudFormation documentation, a subnet change requires a replacement of the resource. You should always pay attention to updates that require replacements, because the current resource will be deleted and a new one will be created. And guess what? If you forgot to include in the template the tags you manually added, they won't be present in the new resource, making your security checks not check that instance anymore. I like to say that CloudFormation is jealous, and you should not touch the resources it creates. Avoid at all costs manually changing your infrastructure once it was created by CloudFormation. Because if you want to change something in the template, it may override what you have done manually. It may get easier when you are the only one modifying an infrastructure, because you are more likely to remember what you did. But it gets extremely challenging if you have multiple DevOps people interacting with the environment. Although the best practice is never manually touching an environment created by CloudFormation, if you have people having permission to do so, trust me, they will. And this is what we call CloudFormation drift. Drifts happen when the environment gets changed and CloudFormation is not aware of the change. Drifts are not when you change the running code with existing resources. This is called a deployment. Drifts happen when manual infrastructure configuration changes are made, like tags, security groups, instance types. That's potentially dangerous for production environments, because sometimes someone may have done an undocumented action to apply a hotfix on a Friday night, which may be overridden by the next time you update the stack. To get a little help from CloudFormation, you can count on a feature called drift detection. In the described scenario, if I had changed tags, running CloudFormation drift detection for the EC2 resource would point out to me that the current tags of the instance do not match the tags that CloudFormation was instructed to create. You should pay special attention to these drifts, especially if the change you want to do via CloudFormation requires a replacement of the resource, and especially if that resource contains data from your users. The easiest way to avoid drifts and be safer here is not manually changing whatever was created via CloudFormation. And it should be a best practice to incorporate drift detection as part of your CI/CD build process, since everything here can and should be done programmatically. With that many options for operating your cloud infrastructure, you may be asking, is there any place where I can gain centralized operational insights and take actions on AWS resources? The answer for that question is AWS Systems Manager. AWS Systems Manager is an AWS service that you can use to view and control your infrastructure on AWS. You can view operational data from multiple AWS services and automate operational tasks across them. It helps you to maintain the security and compliance by scanning your instances and reporting, or even better, taking corrective action on any policy violation it detects. AWS Systems Manager is a must-have if you have a fleet of EC2 instances, because it helps you on the burden of fleet management. You can group your instances together and run commands on them all at the same time or one by one. You can also securely connect to an instance to have an interactive shell without having to use SSH, logging all the commands and outputs in the CloudWatch Logs log stream. But it does not stop there. You can also use the SSM for your serverless operation, build health dashboards for your resources, securely store parameters used by your application, publish messages for instant response, build response plans, and even enable your teams to interact with chatbots or escalation points during crisis. There are so many things to learn about AWS Systems Manager that I wish I had all the time in the world to create endless videos for you. But I will do my best to take care of your time, and because less is more, I will only focus on the core features. But don't forget to read the course notes as well, because I will add more detailed information in there about this fantastic world called AWS Systems Manager. So, in the next videos, I will be talking about AWS SSM general features and also drilling down a bit on separate operational parts of it, Let's go. As I said earlier, AWS Systems Manager is a suite of features that you can embrace for the operation parts of your DevOps journey. In this video, I will be talking about some Systems Manager features that can be useful for you regardless of whether you have serverless or EC2-based architectures. In this video, I will cover some relevant features of Systems Manager, a vast AWS service with many other features. I will talk about Parameter Store, Change Manager, and shared resources. Let's start with Parameter Store. Parameter Store provides a secure way to store data in a key value fashion. It is ideal for storing things like passwords, database strings, Amazon Machine Image, or AMI IDs to be used by your automation solution, license codes, serial numbers, or any key value data that you would like to programmatically store and retrieve in an encrypted way. For example, if you store database connection strings in Parameter Store, your application backend can get them by doing API calls instead of having them hard-coded. By doing this, you turn connection strings into something detached from your code, preventing you from having to do deployments if you change them. Same thing with passwords. Many customers need to comply with password or credentials rotation. This is also easier to achieve with Parameter Store, because you can simply change the value in there and code your application in a way to query Parameter Store again in case of authentication failure, forcing some sort of automatic refresh. Parameter Store is also accessible from other AWS services, including but not limited to AWS Lambda, CloudFormation, and offloading credentials and sensitive information from Lambda code or a CloudFormation template is always a good idea, especially if you're publishing it somewhere. Another Systems Manager feature that I would like to highlight is the Change Manager, which is instrumental especially if you're using multiple AWS accounts and would like to track what's being changed on them. Change Manager simplifies the way ops engineers track, approve, and implement operational changes to their application configurations and environments. Think about using Change Manager when you want ops to request some sort of elevation in terms of access in order to do something in your account. To use it, you need to create templates, which are a collection of automation runbooks for a user to choose from when creating a change request, SNS topics for notifying approvers about the change, and CloudWatch alarms to monitor the runbook workflow. When a change is needed, someone in the organization creates a change request that must be based in one of the available templates you create. If the change requires manual approvals, Change Manager notifies the designated approvers. Now, an interesting thing to observe regarding Change Manager and CI/CD for releasing code. Change Manager should complement the safety controls of your CI/CD practices. But if you're doing CI/CD for your daily code releases, asking for approval every time may slow down your operational speed, especially for the dev environment. That's why I recommend using Change Manager only for things other than the usual code release, such as the creation of new AWS accounts in your organization or launching instance types that cost more than the instance types the application usually needs. Things like that. Now, last but not least, AWS Systems Manager Shared Resources, also known as AWS SSM documents. An AWS Systems Manager document defines the actions that System Manager performs in your account. Think about a repository of actions that can be taken, where these actions are automations, which are very helpful for taking immediate response at a click of a button. Once you navigate through the Documents part of Systems Manager, you will see a repository of actions that were pre-made by AWS, such as this one, for example, called AWS Closed Security Group. If you click on it, you can see a description of what it does. This one removes any rules from a specified security group. You just need to provide the security group ID, and it does it for you. Here, you can also see what are the permissions needed to do that. By clicking Execute Automation, I can provide the security group ID and the IAM role that will be assumed by this automation. If I scroll down, the page gives me the CLI commands that corresponds to that action, facilitating the creation of a script to do that. I can also provide multiple security group IDs and execute this automation gradually or by doing one target at a time. Take a look at the Documents section in your AWS Systems Manager console and imagine what you can do with it right now in your account. There are many interesting blueprints, like enabling S3 bucket logging, attaching IAM roles to specific instances, and much more. You can treat these as small components part of something bigger, or perhaps an approval workflow from a change manager template. In this video, I will highlight one of the most important features of Systems Manager that can be used when you have a fleet of servers and wants to run remote commands without having to connect on them one by one. One of the core features of Systems Manager is the run command. With run command, you can remotely and securely manage configurations of your managed instances. A managed instance is any EC2 instance or on-premises server in your hybrid environment that has been configured for Systems Manager. In other words, they have the SSM agent up and running with proper credentials. You can use IAM roles for EC2 instances or IAM credentials for on-premises servers. Run command allows you to automate common administrative tasks and perform one-time configuration changes at scale. You can use run command from the AWS Management Console, the AWS Command Line Interface, or the AWS CLI, and AWS tools for Windows PowerShell, or the AWS SDKs. Run command is useful for running non-interactive commands remotely, like adjusting all your instances' time zones, cleaning up old log files, or configuring log rotate to do so. You can do all that without having to connect over SSH or messing up with Bayesian hosts. When you go to the Run Command screen on the AWS Management Console, you can see some blueprints and get an idea of the possibilities. For example, there is one that does Windows updates, another one that configures Docker, another one that configures the CloudWatch agent, so on and so forth. The list is long. You can specify parameters for running the command and also how and where you want that command to be run among your instances. We call them targets. These targets can be a group of instances with specific tags, manual instances where you provide the instance ID, or resource groups, which is a collection of resources where you can manually add instances. You can add parameters to the command, allowing to input custom information that gets passed. You can also choose how you are going to roll it out. If it is gradually, one by one, a % of your fleet, or all at the same time. If you want to install packages in your operating system, you can run a command to do so using the specific package manager available in the OS. Or you can offload that to run command. There is an option where you can declare what you want to install, and the run command takes care of the rest. So you don't need to know the specific package manager such as apt or yum. This creates more maintenance resiliency across the operation. For the sake of auditing, all these generate a trail. And because there are commands that can take longer to run, you can follow up the status by doing API calls to the service. There are also third-party solutions that can be used to operate. If that's the case and you already have a solution based on Chef, Puppet, or any other framework, you can use run commands to install and configure the agents of your choice. In the hands-on exercise at the end of this week, you will have the chance to follow a guide that shows you how to use run commands to troubleshoot ongoing issues in a production server. And the best part, run command is offered at no additional cost. In this video, I am going to tell you about features mostly regarding to what System Manager can do for your EC2-based workloads. I am going to talk about Session Manager, Patch Manager, and State Manager. If you are someone who wants to improve your security and audit standards, reduce operational overhead by centralizing access control on instances, and reduce administrative instance access, Session Manager is for you. Instead of using SSH to connect to your instances, you can assume IAM roles and initiate shell sessions to your instances. It gives you access in your browser, it logs the command in a CloudWatch logs log stream, and audits session activity into CloudTrail. The access is given with just one click from the browser or the AWS CLI, all without having to provide SSH keys, like I will show you. In order to have it working, you have to do 3 simple things. First, create an IAM role that allows EC2 instances to call other AWS services, and have permission to call AWS Systems Manager. Luckily, we have a pre-built policy called Amazon SSM Managed Instance Core, which already does that. You don't need to create one role per instance, since roles can be reused by many AWS instances. So give that role a generic name, like EC2 SSM role. Second, have the Systems Manager agent running in the OS of your choice. If you are running Amazon Linux, you can skip that part because it is already there. If you are running another OS, you can download and install the agent by looking to the AWS documentation on where to get the installation files. Most of the features for System Manager requires that agent to be up and running. Third, select your instance and click Connect. The AWS Management Console will offer you some options. Choose Session Manager and Connect. Done. You will have a shell session in your browser. And of course, this can also be done from your command line if you don't want to touch the AWS Management Console. Because you have mechanisms to integrate IAM with single sign-on and federation using common identity providers such as Microsoft Active Directory, this has great value because you can avoid using yet another one authentication method to your servers, which in this case would be SSH. In fact, you can even close the SSH port in your security group, since Session Manager doesn't use that protocol under the hood. It is an HTTPS socket from the instance to the Session Manager service. Now, remember the documents feature from the previous video, which are like blueprints in terms of actions? How about creating a blueprint that adds the role to a given EC2 instance and another one that removes it, so you don't leave the role enabled all the time? Can you see how the pieces start to build together for DevOps solutions? Little by little, we learn how to assemble the puzzle. Now, imagine you have a fleet of tens of instances and you need to urgently apply a security patch on the OS for every single one. Although Session Manager makes it easier for you to connect to an instance, it is not a feature that would scale in our scenario. Sometimes, you can just launch new instances with the new patch, but sometimes the instances contain data, like a database or part of a Hadoop cluster, so they are in use and can't be turned off. If that's the case, Patch Manager to the rescue. As the name suggests, Patch Manager automates the processes of patching managed instances with both security-related and other types of updates. You can use Patch Manager to apply patches for both operating systems and even applications. Patch Manager allows you to perform the patch all at the same time or in a rolled-out fashion. There are many best practices around, and I suggest taking a look at the AWS documentation, AWS blogs, and course readings for more information about them. The most interesting best practice is to integrate Patch Manager with AWS Security Hub to receive alerts when instances in your fleet go out of compliance and monitor the patching status of your fleets from a security point of view. And last but not least, State Manager, a feature to automate the processes of keeping your EC2 instances and hybrid infrastructure in a state that you define. You can run on-demand or schedule actions driven by SSM documents in your managed instances. If you're using open-source frameworks for OS management, like Chef or Puppet for example, you can use State Manager to certify that these agents are up, running, and updated. With State Manager, you can, for example, bootstrap instances with specific software at startup, configure network settings, join instances to one Active Directory domain, run scripts or Linux, macOS, and Windows instances throughout their lifecycle, and many more features. Let us know in the forums or discussion groups if you're using any of these features in your EC2 fleet. We are curious to know how you're using it as part of the operational part of your DevOps workflow. For this exercise, imagine you have a running application with issues in production. The issue is that the app has missing images and users are getting 404 errors. The phone starts ringing, the pager starts beeping, and everybody is reporting the issue. Whenever that happens, the most convenient thing to do is to access the production service to take a look into the log files. But Is this a good practice? Probably not. As a security best practice, the governance team has locked off the instances from any terminal access, and the servers don't even have SSH enabled. Since no arbitrary commands can be run on these servers, we need to make sure we have exhausted our options. The first option is, can we debug that very same issue on a dev environment? In the lab scenario, unfortunately not, because this is not an issue happening in the dev environment. So it is something particular to the prod environment. Okay, if we can't SSH into the servers and this is not happening in the dev environment, how about having the logs shipped to CloudWatch logs with the help of CloudWatch agent? Absolutely! Planning to use CloudWatch for that is awesome, but in order for that to work, it must already be installed and configured, which unfortunately it's not the case here. Alright, so we have a prod issue, and we need to move quickly to investigate. Let's explore another alternative. In that scenario, the best thing to do is to securely run a command on the servers by using AWS Systems Manager run command. That would satisfy the requirements of getting data from production servers without accessing them via SSH per se. Do we have a plan? I think yes. So go ahead and start the exercise, where you will deploy a CloudFormation template and use AWS Systems Manager run command to troubleshoot potential production issues. Congratulations on completing this course. We covered lots of topics. In the first week, we talked about monitoring by dividing the topics into environment, application, and network monitoring. For the environment monitoring, we covered CloudWatch metrics, alarms, and logs. I also talked about how and what to do when something changes in your cloud environment, covering AWS services like Amazon Event Bridge, AWS Config, AWS CloudTrail, and the differences between them and when to use each one. Next, we talked about instrumentalizing your applications with the help of AWS X-Ray and CloudWatch custom metrics. These are the services that can help you to monitor things that go beyond the infrastructure scope. Then, we covered network monitoring by approaching ELB access logs, VPC flow logs, and some ideas on how to take insights from that information. The first week ended with a simple hands-on exercise, where you worked with Amazon SNS and Event Bridge to receive notifications whenever there are changes in the pipeline workflow. The second week of the course talked about some aspects regarding operations for the sake of completing the CI/CD loop. We talked about important things to keep in mind for a smooth operation, such as the observation of soft limits with the help of service quotas and CloudFormation change sets. We also talked about CloudFormation drift detection and dove a little deeper into AWS Systems Manager by covering its core features such as Change Manager, Shared Resources, Application Management, Operations Management, Sessions Manager, Fleet Manager, Patch Manager, Parameter Store, and State Manager. Last but not least, the course ended with a hands-on exercise where you used AWS Systems Manager run command to troubleshoot potential ongoing production issues. That's it. Now we can't wait to see what you have built. Tell us on the forums or discussion groups. On behalf of the AWS team, I thank you for taking this course. I hope you learned some new things and enjoyed our time together. I also hope to see you on the next one. See you soon.